Section 50 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 16 of Empirical Laws. Part 1. Scientific inquirers give the name of empirical laws to those uniformities which observation or experiment has shown to exist, but on which they hesitate to rely in cases varying much from those which have been actually observed, for want of seeing any reason why such a law should exist. It is implied, therefore, in the notion of an empirical law that it is not an ultimate law, that if true at all, its truth is capable of being, and requires to be, accounted for. It is a derivative law, the derivation of which is not yet known. To state the explanation, the why of the empirical law would be to state the laws from which it is derived, the ultimate causes on which it is contingent. And if we knew these, we should also know what are its limits, under what conditions it would cease to be fulfilled. The periodical return of eclipses, as originally ascertained by the persevering observation of the early Eastern astronomers, was an empirical law until the general laws of the celestial motions had accounted for it. The following are empirical laws still waiting to be resolved into the simpler laws from which they are derived. The local laws of the flux and reflux of the tides in different places. The succession of certain kinds of weather to certain appearances of sky. The apparent exceptions to the almost universal truth that bodies expand by increase of temperature. The law that breeds, both animal and vegetable, are improved by crossing. That gases have a strong tendency to permeate animal membranes. That substances containing a very high proportion of nitrogen, such as hydrocyanic acid and morphia, are powerful poisons. That when different metals are fused together, the alloy is harder than the various elements, that the number of atoms of acid required to neutralize one atom of any base is equal to the number of atoms of oxygen in the base, that the solubility of substance in one another depends, at least in some degree, on the similarity of their elements. Footnote. Thus, water, of which 8/9 in weight are oxygen, dissolves most bodies which contain a high proportion of oxygen, such as all the nitrates, which have more oxygen than any others of the common salts, most of the sulfates, many of the carbonates, and so on. Again, bodies largely composed of combustible elements, like hydrogen and carbon, are soluble in bodies of similar composition. Resin, for instance, will dissolve in alcohol, tar in oil of turpentine. This empirical generalization is far from being universally true, no doubt because it is a remote and therefore easily defeated result of general laws too deep for us at present to penetrate, but it will probably in time suggest processes of inquiry leading to the discovery of those laws. End footnote. An empirical law, then, is an observed uniformity, presumed to be resolvable into simpler laws, but not yet resolved into them. The ascertainment of the empirical laws of phenomena often precedes by a long interval the explanation of those laws by the deductive method, and the verification of a deduction usually consists in the comparison of its results with empirical laws previously ascertained. Part 2. From a limited number of ultimate laws of causation, there are necessarily generated a vast number of derivative uniformities, both of succession and coexistence. Some are laws of succession or of coexistence between different effects of the same cause. Of these we had examples in the last chapter. Some are laws of succession between effects and their remote causes, resolvable into the laws which connect each with the intermediate link. Thirdly, when causes act together and compound their effects, the laws of those causes generate the fundamental law of the effect, namely, that it depends on the coexistence of those causes. And finally, the order of succession or of coexistence which obtains among effects necessarily depends on their causes. If they are effects of the same cause, it depends on the laws of that cause. If on different causes, it depends on the laws of those causes severally and on the circumstances which determine their coexistence. If we inquire further when and how the causes will coexist, that, again, depends on their causes, and we may thus trace back the phenomena higher and higher until the different series of effects meets in a point, and the whole is shown to have depended ultimately on some common cause, or until, instead of converging to one point, they terminate in different points, and the order of the effects is proved to have arisen from the collocation of some of the primeval causes or natural agents. For example, the order of succession and of coexistence among the heavenly motions, which is expressed by Kepler's laws, is derived from the coexistence of two primeval causes, the sun and the original impulse or projectile force belonging to each planet. Footnote. Or, according to Laplace's theory, the sun and the sun's rotation. End footnote. Kepler's laws are resolved into the laws of these causes and the fact of their coexistence. Derivative laws, therefore, do not depend solely on the ultimate laws into which they are resolvable. They mostly depend on those ultimate laws and an ultimate fact, namely, the mode of coexistence of some of the component elements of the universe. The ultimate laws of causation might be the same as at present, and yet the derivative laws completely different. If the causes coexisted in different proportions, or with any difference in those of their relations by which the effects are influenced. If, for example, the sun's attraction and the original projectile force had existed in some other ratio to one another than they did, and we know of no reason why this should not have been the case, the derivative laws of the heavenly motions might have been quite different from what they are. The proportions which exist happen to be such as to produce regular elliptical motions. Any other proportions would have produced different ellipses, or circular, or parabolic or hyperbolic motions, but still regular ones, because the effects of each of the agents accumulate according to a uniform law, and two regular series of quantities, when their corresponding terms are added, must produce a regular series of some sort, whatever the quantities themselves are. Part 3. Now this last mentioned element in the resolution of a derivative law, the element which is not a law of causation, but a collocation of causes, cannot itself be reduced to any law. There is, as formerly remarked, no uniformity, no norma, principle, or rule perceivable in the distribution of the primeval natural agents through the universe. Footnote. See section 34 of this work, Book 3, Chapter 5, Part 7. End footnote. The different substances composing the earth, the powers that pervade the universe, stand in no constant relation to one another. One substance is more abundant than others. One power acts through a larger extent of space than others, without any pervading analogy that we can discover. We not only do not know of any reason why the sun's attraction and the force in the direction of the tangent coexist in the exact proportion they do, but we can trace no coincidence between it and the proportions in which any other elementary powers in the universe are intermingled. The utmost disorder is apparent in the combination of the causes, which is consistent with the most regular order in their effects. For when each agent carries on its own operations according to a uniform law, even the most capricious combination of agencies will generate a regularity of some sort, as we see in the kaleidoscope, where any casual arrangement of coloured bits of glass produces, by the laws of reflection, a beautiful regularity in the effect. Part 4. In the above considerations lies the justification of the limited degree of reliance which scientific inquirers are accustomed to place in empirical laws. A derivative law which results wholly from the operation of some one cause will be as universally true as the laws of the cause itself. That is, it will always be true except where some one of those effects of the cause on which the derivative law depends is defeated by a counteracting cause. But when the derivative law results not from different effects of one cause, but from effects of several causes, we cannot be certain that it will be true under any variation in the mode of coexistence of those causes, or of the primitive natural agents on which the causes ultimately depend. The proposition that coal beds rest on certain descriptions of strata exclusively, though true on the earth, so far as our observation has reached, cannot be extended to the moon or the other planets, supposing coal to exist there, because we cannot be assured that the original constitution of any other planet was such as to produce the different depositions in the same order as in our globe. The derivative law, in this case, depends not solely on laws, but on a collocation, and collocations cannot be reduced to any law. Now, it is the very nature of a derivative law which has not yet been resolved into its elements, in other words, an empirical law, that we do not know whether it results from the different effects of one cause or from effects of different causes. We cannot tell whether it depends wholly on laws or partly on laws and partly on a collocation. If it depends on a collocation, it will be true in all the cases in which that particular collocation exists. But since we are entirely ignorant, in case of its depending on a collocation, what the collocation is, we are not safe in extending the law beyond the limits of time and place in which we have actual experience of its truth. Since within those limits the law has always been found true, we have evidence that the collocations, whatever they are, on which it depends, do really exist within those limits. But knowing of no rule or principle to which the collocations themselves conform, we cannot conclude that, because a collocation is proved to exist within certain limits of place or time, it will exist beyond those limits. Empirical laws, therefore, can only be received as true within the limits of time and place in which they have been found true by observation, and not merely the limits of time and place, but of time, place, and circumstance. For since it is the very meaning of an empirical law that we do not know the ultimate laws of causation on which it is dependent, we cannot foresee, without actual trial, in what manner or to what extent the introduction of any new circumstance may affect it. Part 5. But how are we to know that a uniformity ascertained by experience is only an empirical law, since, by the supposition, we have not been able to resolve it into any other laws? How do we know that it is not an ultimate law of causation? I answer that no generalization amounts to more than an empirical law when the only proof on which it rests is that of the method of agreement. For it has been seen that by that method alone we never can arrive at causes. The utmost that the method of agreement can do is to ascertain the whole of the circumstances common to all cases in which a phenomenon is produced. And this aggregate includes not only the cause of the phenomenon, but all phenomena with which it is connected by any derivative uniformity, whether as being collateral effects of the same cause, or effects of any other cause which, in all the instances we have been able to observe, coexisted with it. The method affords no means of determining which of these uniformities are laws of causation, and which are merely derivative laws, resulting from those laws of causation and from the collocation of the causes. None of them, therefore, can be received in any other character than that of derivative laws, the derivation of which has not been traced. In other words, empirical laws, in which light all results obtained by the method of agreement, and therefore almost all truths obtained by simple observation without experiment, must be considered until either confirmed by the method of difference or explained deductively. In other words, accounted for a priori. These empirical laws may be of greater or less authority according as there is reason to presume that they are resolvable into laws only or into laws and collocations together. The sequences which we observe in the production and subsequent life of an animal or a vegetable, resting on the method of agreement only, are mere empirical laws. But though the antecedents in those sequences may not be the causes of the consequence, both the one and the other are doubtless, in the main, successive stages of a progressive effect originating in a common cause, and therefore independent of collocations. The uniformities, on the other hand, in the order of superposition of strata on the earth, are empirical laws of a much weaker kind, since they not only are not laws of causation, but there is no reason to believe that they depend on any common cause. All appearances are in favour of their depending on the particular collocation of natural agents which, at some time or other, existed on our globe, and from which no inference can be drawn as to the collocation which exists or has existed in any other portion of the universe. Part 6. Our definition of an empirical law, including not only those uniformities which are not known to be laws of causation, but also those which are, provided that there be reason to presume that they are not ultimate laws. This is the proper place to consider by what signs we may judge that even if an observed uniformity be a law of causation, it is not an ultimate but a derivative law. The first sign is, if between the antecedent a and the consequent b, there be evidence of some intermediate link, some phenomenon of which we can surmise the existence, though from the imperfection of our senses or of our instruments we are unable to ascertain its precise nature and laws. If there be such a phenomenon, which may be denoted by the letter x, it follows that even if a be the cause of b, it is but the remote cause, and that the law a causes b is resolvable into at least two laws. A causes x, and x causes b. This is a very frequent case, since the operations of nature mostly take place on so minute a scale that many of the successive steps are either imperceptible or very indistinctly perceived. Take, for example, the laws of the chemical composition of substances, as that hydrogen and oxygen being combined, water is produced. All we see of the process is that the two gases being mixed in certain proportions and heat or electricity being applied, an explosion takes place, the gases disappear and water remains. There is no doubt about the law or about its being a law of causation, but between the antecedent, the gases in a state of mechanical mixture, heated or electrified, and the consequent, the production of water, there must be an intermediate process which we do not see. For if we take any portion whatever of the water and subject it to analysis, we find that it always contains hydrogen and oxygen, nay, the very same proportions of them, namely, 2/3 in volume of hydrogen and 1/3 oxygen. This is true of a single drop. it is true of the minutest portion which our instruments are capable of appreciating. Since, then, the smallest perceptible portion of the water contains both these substances, portions of hydrogen and oxygen smaller than the smallest perceptible must have come together in every such minute portion of space, must have come closer together than when the gases were in a state of mechanical mixture, since, to mention no other reasons, the water occupies far less space than the gases. Now, as we cannot see this contact or close approach of the minute particles, we cannot observe with what circumstances it is attended, or according to what laws it produces its effects. The production of water, that is, of the sensible phenomena which characterizes the compound, may be a very remote effect of those laws. There may be innumerable intervening links, and we are sure that there must be some. Having full proof that corpuscular action of some kind takes place previous to any of the great transformations in the sensible properties of substances, we can have no doubt that the laws of chemical action, as at present known, are not ultimate, but derivative laws, however ignorant we may be, and even though we should forever remain ignorant of the nature of the laws of corpuscular action from which they are derived. In like manner, all the processes of vegetative life, whether in the vegetable properly so called or in the animal body, are corpuscular processes. Nutrition is the addition of particles to one another, sometimes merely replacing other particles separated and excreted, sometimes occasioning an increase of bulk or weight so gradual that only after a long continuance does it become perceptible. Various organs, by means of peculiar vessels, secrete from the blood fluids, the component particles of which must have been in the blood, but which differ from it most widely, both in mechanical properties and in chemical composition. Here, then, are abundance of unknown links to be filled up, and there can be no doubt that the laws of the phenomena of vegetative or organic life are derivative laws, dependent on properties of the corpuscles and of those elementary tissues which are comparatively simple combinations of corpuscles. The first sign, then, from which a law of causation, though hitherto unresolved, may be inferred to be a derivative law, is any indication of the existence of an intermediate link or links between the antecedent and the consequent. The second is when the antecedent is an extremely complex phenomenon, and its effects, therefore, probably in part at least, compounded of the effects of its different elements, since we know that the case in which the effect of the whole is not made up of the effects of its parts is exceptional, the composition of causes being by far the more ordinary case. We will illustrate this by two examples, in one of which the antecedent is the sum of many homogeneous, in the other of heterogeneous, parts. The weight of a body is made up of the weights of its minute particles, a truth which astronomers express in its most general terms when they say that bodies at equal distances gravitate to one another in proportion to their quantity of matter. All true propositions, therefore, which can be made concerning gravity are derivative laws, the ultimate law into which they are all resolvable being that every particle of matter attracts every other. As our second example, we may take any of the sequences observed in meteorology. For instance, a diminution of the pressure of the atmosphere, indicated by a fall of the barometer, is followed by rain. The antecedent is here a complex phenomenon made up of heterogeneous elements, the column of the atmosphere over any particular place consisting of two parts, a column of air and a column of aqueous vapour mixed with it, and the change in the two together manifested by a fall of the barometer and followed by rain must be either a change in one of these, or in the other, or in both. We might then, even in the absence of any other evidence, form a reasonable presumption from the invariable presence of both these elements in the antecedent, that the sequence is probably not an ultimate law, but a result of the laws of the two different agents, a presumption only to be destroyed when we had made ourselves so well acquainted with the laws of both as to be able to affirm that those laws could not by themselves produce the observed result. There are but few known cases of succession from very complex antecedents which have not either been actually accounted for from simpler laws, or inferred with great probability from the ascertained existence of intermediate links of causation not yet understood, to be capable of being so accounted for. It is therefore highly probable that all sequences from complex antecedents are thus resolvable, and that ultimate laws are in all cases comparatively simple. If there were not the other reasons already mentioned for believing that the laws of organized nature are resolvable into simpler laws, it would be almost a sufficient reason that the antecedents in most of the sequences are so very complex. Part 7. In the preceding discussion we have recognized two kinds of empirical laws, those known to be laws of causation but presumed to be resolvable into simpler laws, and those not known to be laws of causation at all. Both these kinds of laws agree in the demand which they make for being explained by deduction, and agree in being the appropriate means of verifying such deduction, since they represent the experience with which the result of the deduction must be compared. They agree, further, in this, that until explained and connected with the ultimate laws from which they result, they have not attained the highest degree of certainty of which laws are susceptible. It has been shown on a former occasion that laws of causation which are derivative and compounded of simpler laws are not only, as the nature of the case implies, less general, but even less certain than the simpler laws from which they result, not in the same degree to be relied on as universally true. The inferiority of evidence, however, which attaches to this class of laws is trifling compared with that which is inherent in uniformities not known to be laws of causation at all. So long as these are unresolved, we cannot tell on how many collocations, as well as laws, their truth may be dependent. We can never, therefore, extend them with any confidence to cases in which we have not assured ourselves by trial that the necessary collocation of causes, whatever it may be, exists. It is to this class of laws alone that the property, which philosophers usually consider as characteristic of empirical laws, belongs in all its strictness, the property of being unfit to be relied on beyond the limits of time, place, and circumstance in which the observations have been made. These are empirical laws in a more emphatic sense, and when I employ that term, except when the context manifestly indicates the reverse, I shall generally mean to designate those uniformities only, whether of succession or of coexistence, which are not known to be laws of causation. End of section 50. Section 51 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 17 of Chance and its Elimination. Part 1. Considering, then, as empirical laws only those observed uniformities respecting which the question whether they are laws of causation must remain undecided until they can be explained deductively, or until some means are found of applying the method of difference to the case, it has been shown in the preceding chapter that until a uniformity can, in one or the other of these modes, be taken out of the class of empirical laws, and brought either into that of laws of causation or of the demonstrated results of laws of causation, it cannot with any assurance be pronounced true beyond the local and other limits within which it has been found so by actual observation. It remains to consider how we are to assure ourselves of its truth even within those limits. After what quantity of experience a generalization which rests solely on the method of agreement can be considered sufficiently established, even as an empirical law. In a former chapter, when treating of the methods of direct induction, we expressly reserved this question, and the time is now come for endeavouring to solve it. Footnote. See section 42 of this work, Book 3, Chapter 10, Part 2. End footnote. We found that the method of agreement has the defect of not proving causation, and can, therefore, only be employed for the ascertainment of empirical laws. But we also found that besides this deficiency, it labours under a characteristic imperfection, tending to render uncertain even such conclusions as it is in itself adapted to prove. This imperfection arises from plurality of causes. Although two or more cases in which the phenomenon a has been met with may have no common antecedent except A, this does not prove that there is any connection between a and A, since a may have many causes and may have been produced in these different instances not by any thing which the instances had in common, but by some of those elements in them which were different. We nevertheless observed that in proportion to the multiplication of instances pointing to A as the antecedent, the characteristic uncertainty of the method diminishes, and the existence of a law of connection between A and a more nearly approaches to certainty. It is now to be determined after what amount of experience this certainty may be deemed to be practically attained, and the connection between A and a may be received as an empirical law. This question may be otherwise stated in more familiar terms. After how many and what sort of instances may it be concluded that an observed coincidence between two phenomena is not the effect of chance? It is of the utmost importance for understanding the logic of induction that we should form a distinct conception of what is meant by chance and how the phenomena which common language ascribes to that abstraction are really produced. Part 2. Chance is usually spoken of in direct antithesis to law. Whatever it is supposed cannot be ascribed to any law is attributed to chance. It is, however, certain that whatever happens is the result of some law, is an effect of causes, and could have been predicted from a knowledge of the existence of those causes and from their laws. If I turn up a particular card, that is a consequence of its place in the pack. Its place in the pack was a consequence of the manner in which the cards were shuffled, or of the order in which they were played in the last game, which, again, were effects of prior causes. At every stage, if we had possessed an accurate knowledge of the causes in existence, it would have been abstractedly possible to foretell the event. An event occurring by chance may be better described as a coincidence from which we have no ground to infer a uniformity, the occurrence of a phenomenon in certain circumstances, without our having reason on that account to infer that it will happen again in those circumstances. This, however, when looked closely into, implies that the enumeration of the circumstances is not complete. Whatever the fact be, since it has occurred once, we may be sure that if all the same circumstances were repeated, it would occur again, and not only if all, but there is some particular portion of those circumstances on which the phenomenon is invariably consequent. With most of them, however, it is not connected in any permanent manner. Its conjunction with those is said to be the effect of chance, to be merely casual. Facts casually conjoined are separately the effects of causes, and therefore of laws, but of different causes, and causes not connected by any law. It is incorrect, then, to say that any phenomenon is produced by chance, but we may say that two or more phenomena are conjoined by chance, that they coexist or succeed one another only by chance, meaning that they are in no way related through causation, that they are neither cause and effect, nor effects of the same cause, nor effects of causes between which there subsists any law of coexistence, nor even effects of the same collocation of primeval causes. If the same casual coincidence never occurred a second time, we should have an easy test for distinguishing such from the coincidences which are the results of a law. As long as the phenomena had been found together only once, so long, unless we knew some more general laws from which the coincidence might have resulted, we could not distinguish it from a casual one. But if it occurred twice, we should know that the phenomena so conjoined must be in some way connected through their causes. There is, however, no such test. A coincidence may occur again and again and yet be only casual. Nay, it would be inconsistent with what we know of the order of nature to doubt that every casual coincidence will, sooner or later, be repeated, as long as the phenomena between which it occurred do not cease to exist or to be reproduced. The recurrence, therefore, of the same coincidence more than once, or even its frequent recurrence, does not prove that it is an instance of any law, does not prove that it is not casual, or, in common language, the effect of chance. And yet, when a coincidence cannot be deduced from known laws, nor proved by experiment to be itself a case of causation, the frequency of its occurrence is the only evidence from which we can infer that it is the result of a law, not, however, its absolute frequency. The question is not whether the coincidence occurs often or seldom in the ordinary sense of those terms, but whether it occurs more often than chance will account for, more often than might rationally be expected if the coincidence were casual. We have to decide, therefore, what degree of frequency in a coincidence chance will account for, and to this there can be no general answer. We can only state the principle by which the answer must be determined. The answer itself will be different in every different case. Suppose that one of the phenomena, A, exists always, and the other phenomenon, B, only occasionally. It follows that every instance of B will be an instance of its coincidence with A, and yet the coincidence will be merely casual, not the result of any connection between them. The fixed stars have been constantly in existence since the beginning of human experience, and all phenomena that have come under human observation have, in every single instance, coexisted with them. Yet this coincidence, though equally invariable with that which exists between any of those phenomena and its own cause, does not prove that the stars are its cause, nor that they are in any wise connected with it. As strong a case of coincidence, therefore, as can possibly exist, and a much stronger one in point of mere frequency than most of those which prove laws, does not here prove a law. Why? Because, since the stars exist always, they must coexist with every other phenomenon, whether connected with them by causation or not. The uniformity, great though it be, is no greater than would occur on the supposition that no such connection exists. On the other hand, suppose that we were inquiring whether there be any connection between rain and any particular wind. Rain, we know, occasionally occurs with every wind. Therefore, the connection, if it exists, cannot be an actual law. But still, rain may be connected with some particular wind through causation, that is, though they cannot be always effects of the same cause, for if so they would regularly coexist, there may be some causes common to the two, so that insofar as either is produced by those common causes, they will, from the laws of the causes, be found to coexist. How then shall we ascertain this? The obvious answer is, by observing whether rain occurs with one wind more frequently than with any other. That, however, is not enough, for perhaps that one wind blows more frequently than any other, so that its blowing more frequently in rainy weather is no more than would happen, although it had no connection with the causes of rain, provided it were not connected with causes adverse to rain. In England, westerly winds blow during about twice as great a portion of the year as easterly. If, therefore, it rains only twice as often with a westerly as with an easterly wind, we have no reason to infer that any law of nature is concerned in the coincidence. If it rains more than twice as often, we may be sure that some law is concerned. Either there is some cause in nature which, in this climate, tends to produce both rain and a westerly wind, or a westerly wind has itself some tendency to produce rain. But if it rains less than twice as often, we may draw a directly opposite inference. The one, instead of being a cause or connected with causes of the other, must be connected with causes adverse to it, or with the absence of some cause which produces it. And though it may still rain much oftener with a westerly wind than with an easterly, so far would this be from proving any connection between the phenomena, that the connection proved would be between rain and an easterly wind, to which, in mere frequency of coincidence, it is less allied. Here then are two examples. In one, the greatest possible frequency of coincidence, with no instance whatever to the contrary, does not prove that there is any law. In the other, a much less frequency of coincidence, even when non-coincidence is still more frequent, does prove that there is a law. In both cases, the principle is the same. In both, we must consider the positive frequency of the phenomena themselves, and how great frequency of coincidence that must of itself bring about, without supposing any connection between them, provided there be no repugnance, provided neither be connected with any cause tending to frustrate the other. If we find a greater frequency of coincidence than this, we conclude that there is some connection. If a less frequency, that there is some repugnance. In the former case, we conclude that one of the phenomena can, under some circumstances, cause the other, or that there exists something capable of causing them both. In the latter, that one of them, or some cause which produces one of them, is capable of counteracting the production of the other. We have thus to deduct from the observed frequency of coincidence as much as may be the effect of chance, that is, of the mere frequency of the phenomena themselves, and if anything remains, what does remain is the residual fact which proves the existence of a law. The frequency of the phenomena can only be ascertained within definite limits of space and time, depending as it does on the quantity and distribution of the primeval natural agents, of which we can know nothing beyond the boundaries of human observation, since no law, no regularity can be traced in it, enabling us to infer the unknown from the known. But for the present purpose this is no disadvantage, the question being confined within the same limits as the data. The coincidences occurred in certain places and times, and within those we can estimate the frequency with which such coincidences would be produced by chance. If then we find from observation that A exists in one case out of every 2, and B in one case out of every 3, then, if there be neither connection nor repugnance between them, or between any of their causes, the instances in which A and B will both exist, that is to say, will coexist, will be one case in every 6. For A exists in 3 cases out of 6, and B, existing in 1 case out of every 3 without regard to the presence or absence of A, will exist in 1 case out of those 3. There will therefore be, of the whole number of cases, 2 in which A exists without B, 1 case of B without A, 2 in which neither B nor A exists, and 1 case out of 6 in which they both exist. If then, in point of fact, they are found to coexist oftener than in 1 case out of 6, and consequently A does not exist without B so often as twice in 3 times, nor B without A so often as once in every twice, there is some cause in existence which tends to produce a conjunction between A and B. Generalizing the result, we may say that if A occurs in a larger proportion of the cases where B is than of the cases where B is not, then will B also occur in a larger proportion of the cases where A is than of the cases where A is not, and there is some connection, through causation, between A and B. If we could ascend to the causes of the 2 phenomena, we should find at some stage, either proximate or remote, some cause or causes common to both, and if we could ascertain what these are, we could frame a generalization which would be true without restriction of place or time, but until we can do so, the fact of a connection between the 2 phenomena remains an empirical law. Part 3. Having considered in what manner it may be determined whether any given conjunction of phenomena is causal or the result of some law, to complete the theory of chance, it is necessary that we should now consider those effects which are partly the result of chance and partly of law, or, in other words, in which the effects of causal conjunctions of causes are habitually blended in one result with the effects of a constant cause. This is a case of composition of causes, and the peculiarity of it is that instead of 2 or more causes intermixing their effects in a regular manner with those of one another, we have now one constant cause producing an effect which is successively modified by a series of variable causes. Thus, as summer advances, the approach of the sun to a vertical position tends to produce a constant increase of temperature, but with this effect of a constant cause there are blended the effects of many variable causes, winds, clouds, evaporation, electric agencies, and the like, so that the temperature of any given day depends in part on these fleeting causes, and only in part on the constant cause. If the effect of the constant cause is always accompanied and disguised by effects of variable causes, it is impossible to ascertain the law of the constant cause in the ordinary manner by separating it from all other causes and observing it apart. Hence arises the necessity of an additional rule of experimental inquiry. When the action of a cause A is liable to be interfered with, not steadily by the same cause or causes, but by different causes at different times, and when these are so frequent or so indeterminate that we cannot possibly exclude all of them from any experiment, though we may vary them, our resource is to endeavour to ascertain what is the effect of all the variable causes taken together. In order to do this, we make as many trials as possible, preserving A invariable. The results of these different trials will naturally be different, since the indeterminate modifying causes are different in each. If, then, we do not find these results to be progressive, but, on the contrary, to oscillate about a certain point, one experiment giving a result a little greater, another a little less, one a result tending a little more in one direction, another a little more in the contrary direction, while the average or middle point does not vary, but different sets of experiments, taken in as great a variety of circumstances as possible, yield the same mean, provided only they be sufficiently numerous, then that mean or average result is the part in each experiment which is due to the cause A, and is the effect which would have been obtained if A could have acted alone. The variable remainder is the effect of chance, that is, of causes the coexistence of which with the cause A was merely casual. The test of the sufficiency of the induction in this case is, when any increase of the number of trials from which the average is struck does not materially alter the average. This kind of elimination, in which we do not eliminate any one assignable cause, but the multitude of floating unassignable ones, may be termed the elimination of chance. We afford an example of it when we repeat an experiment in order, by taking the mean of different results, to get rid of the effects of the unavoidable errors of each individual experiment. When there is no permanent cause, such as would produce a tendency to error peculiarly in one direction, we are warranted by experience in assuming that the errors on one side will, in a certain number of experiments, about balance the errors on the contrary side. We therefore repeat the experiment until any change which is produced in the average of the whole by further repetition falls within limits of error consistent with the degree of accuracy required by the purpose we have in view. Footnote: in the preceding discussion, the mean is spoken of as if it were exactly the same thing with the average, but the mean, for purposes of inductive inquiry, is not the average or arithmetical mean, though in a familiar illustration of the theory the difference may be disregarded. If the deviations on one side of the average are much more numerous than those on the other, these last being fewer but greater, the effect due to the invariable cause, as distinct from the variable ones, will not coincide with the average, but will be either below or above the average, the deviation being toward the side on which the greatest number of the instances are found. This follows from a truth ascertained both inductively and deductively, that small deviations from the true central point are greatly more frequent than large ones. The mathematical law is, quote, that the most probable determination of one or more invariable elements from observation is that in which the sum of the squares of the individual aberrations, or deviations, shall be the least possible. End quote. See this principle stated and its grounds popularly explained by Sir John Herschel in his review of Quetelet on Probabilities, Essays, page 395 and following. End footnote. Part 4. In the supposition hitherto made, the effect of the constant cause A has been assumed to form so great and conspicuous a part of the general result that its existence never could be a matter of uncertainty, and the object of the eliminating process was only to ascertain how much is attributable to that cause. What is its exact law? Cases, however, occur in which the effect of a constant cause is so small compared with that of some of the changeable causes with which it is liable to be casually conjoined, that of itself it escapes notice, and the very existence of any effect arising from a constant cause is first learned by the process which, in general, serves only for ascertaining the quantity of that effect. This case of induction may be characterized as follows. A given effect is known to be chiefly, and not known not to be wholly, determined by changeable causes. If it be wholly so produced, then, if the aggregate be taken of a sufficient number of instances, the effects of these different causes will cancel one another. If, therefore, we do not find this to be the case, but on the contrary, after such a number of trials has been made that no further increase alters the average result, we find that average to be not zero, but some other quantity, about which, though small in comparison with the total effect, the effect nevertheless oscillates, and which is the middle point in its oscillation. We may conclude this to be the effect of some constant cause, which cause, by some of the methods already treated of, we may hope to detect. This may be called the discovery of a residual phenomenon by eliminating the effects of chance. It is in this manner, for example, that loaded dice may be discovered. Of course, no dice are so clumsily loaded that they must always throw certain numbers, otherwise the fraud would be instantly detected. The loading, a constant cause, mingles with the changeable causes which determine what cast will be thrown in each individual instance. If the dice were not loaded, and the throw were left to depend entirely on the changeable causes, these, in a sufficient number of instances, would balance one another, and there would be no preponderant number of throws of any one kind. If, therefore, after such a number of trials that no further increase of their number has any material effect upon the average, we find a preponderance in favour of a particular throw, we may conclude with assurance that there is some constant cause acting in favour of that throw, or, in other words, that the dice are not fair, and the exact amount of the unfairness. In a similar manner, what is called the diurnal variation of the barometer, which is very small compared with the variations arising from the irregular changes in the state of the atmosphere, was discovered by comparing the average height of the barometer at different hours of the day. When this comparison was made, it was found that there was a small difference which, on the average, was constant. However, the absolute quantities might vary, and which difference, therefore, must be the effect of a constant cause. This cause was afterward ascertained deductively to be the rarefaction of the air occasioned by the increase of temperature as the day advances. Part 5. After these general remarks on the nature of chance, we are prepared to consider in what manner assurance may be obtained that a conjunction between two phenomena, which has been observed a certain number of times, is not casual, but a result of causation, and to be received, therefore, as one of the uniformities of nature, though, until accounted for a priori, only as an empirical law. We will suppose the strongest case, namely, that the phenomenon B has never been observed except in conjunction with A. Even then, the probability that they are connected is not measured by the total number of instances in which they have been found together, but by the excess of that number above the number due to the absolute frequency of A. If, for example, A exists always, and therefore coexists with everything, no number of instances of its coexistence with B would prove a connection, as in our example of the fixed stars. If A be a fact of such common occurrence that it may be presumed to be present in half of all the cases that occur, and therefore in half the cases in which B occurs, it is only the proportional excess above half that is to be reckoned as evidence toward proving a connection between A and B. In addition to the question, what is the number of coincidences which, on an average of a great multitude of trials, may be expected to arise from chance alone, there is also another question, namely, of what extent of deviation from that average is the occurrence credible, from chance alone, in some number of instances smaller than that required for striking a fair average? It is not only to be considered what is the general result of the chances in the long run, but also what are the extreme limits of variation from the general result, which may occasionally be expected as the result of some smaller number of instances. The consideration of the latter question, and any consideration of the former beyond that already given to it, belong to what mathematicians term the doctrine of chances, or, in a phrase of greater pretension, the theory of probabilities. End of section 51. Section 52 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 18 of the Calculation of Chances. Part 1. Quote, Probability, says Laplace, has reference partly to our ignorance, partly to our knowledge. Footnote. Essai philosophique sur les probabilités, 5th Paris edition, page 7. End footnote. We know that among 3 or more events, one and only one must happen, but there is nothing leading us to believe that any one of them will happen rather than the others. In this state of indecision, it is impossible for us to pronounce with certainty on their occurrence. It is, however, probable that any one of these events, selected at pleasure, will not take place, because we perceive several cases, all equally possible, which exclude its occurrence, and only one which favours it. The theory of chances consists in reducing all events of the same kind to a certain number of cases equally possible, that is, such that we are equally undecided as to their existence, and in determining the number of these cases which are favourable to the event of which the probability is sought. The ratio of that number to the number of all the possible cases is the measure of the probability, which is thus a fraction, having for its numerator the number of cases favourable to the event, and for its denominator the number of all the cases which are possible. End quote. To a calculation of chances, then, according to Laplace, 2 things are necessary. We must know that of several events some one will certainly happen, and no more than one. And we must not know, nor have any reason to expect, that it will be one of these events rather than another. It has been contended that these are not the only requisites, and that Laplace has overlooked, in the general theoretical statement, a necessary part of the foundation of the doctrine of chances. To be able, it has been said, to pronounce 2 events equally probable, it is not enough that we should know that one or the other must happen, and should have no grounds for conjecturing which. Experience must have shown that the 2 events are of equally frequent occurrence. Why, in tossing up a halfpenny, do we reckon it equally probable that we shall throw cross or pile? Because we know that in any great number of throws, cross and pile are thrown about equally often, and that the more throws we make, the more nearly the equality is perfect. We may know this, if we please, by actual experiment, or by the daily experience which life affords of events of the same general character, or, deductively, from the effect of mechanical laws on a symmetrical body acted on by forces varying indefinitely in quantity and direction. We may know it, in short, either by specific experience or on the evidence of our general knowledge of nature. But in one way or the other, we must know it to justify us in calling the 2 events equally probable, and if we knew it not, we should proceed as much at haphazard in staking equal sums on the result as in laying odds. This view of the subject was taken in the first edition of the present work, but I have since become convinced that the theory of chances, as conceived by Laplace and by mathematicians generally, has not the fundamental fallacy which I had ascribed to it. We must remember that the probability of an event is not a quality of the event itself, but a mere name for the degree of ground which we, or someone else, have for expecting it. The probability of an event to one person is a different thing from the probability of the same event to another, or to the same person after he has acquired additional evidence. The probability to me that an individual of whom I know nothing but his name will die within the year is totally altered by my being told the next minute that he is in the last stage of a consumption. Yet this makes no difference in the event itself, nor in any of the causes on which it depends. Every event is in itself certain, not probable. If we knew all, we should either know positively that it will happen, or positively that it will not. But its probability to us means the degree of expectation of its occurrence, which we are warranted in entertaining by our present evidence. Bearing this in mind, I think it must be admitted that even when we have no knowledge whatever to guide our expectations, except the knowledge that what happens must be some one of a certain number of possibilities, we may still reasonably judge that one supposition is more probable to us than another supposition, and if we have any interest at stake, we shall best provide for it by acting conformably to that judgment. Part 2. Suppose that we are required to take a ball from a box, of which we only know that it contains balls both black and white, and none of any other colour. We know that the ball we select will be either a black or a white ball, but we have no ground for expecting black rather than white, or white rather than black. In that case, if we are obliged to make a choice and to stake something on one or the other supposition, it will, as a question of prudence, be perfectly indifferent which, and we shall act precisely as we should have acted if we had known beforehand that the box contained an equal number of black and white balls. But though our conduct would be the same, it would not be founded on any surmise that the balls were, in fact, thus equally divided. For we might, on the contrary, know by authentic information that the box contained 99 balls of one colour and only one of the other. Still, if we are not told which colour has only one and which has 99, the drawing of a white and of a black ball will be equally probable to us. We shall have no reason for staking anything on the one event rather than on the other. The option between the two will be a matter of indifference. In other words, it will be an even chance. But let it now be supposed that instead of two there are three colours, white, black, and red, and that we are entirely ignorant of the proportion in which they are mingled. We should then have no reason for expecting one more than another, and if obliged to bet, should venture our stake on red, white, or black, with equal indifference. But should we be indifferent whether we betted for or against some one colour, as for instance white? Surely not. From the very fact that black and red are each of them separately equally probable to us with white, the two together must be twice as probable. We should in this case expect not white, rather than white, and so much rather that we would lay 2 to 1 upon it. It is true there might, for aught we knew, be more white balls than black and red together, and if so, our bet would, if we knew more, be seen to be a disadvantageous one. But so also, for aught we knew, might there be more red balls than black and white, or more black balls than white and red, and in such case the effect of additional knowledge would be to prove to us that our bet was more advantageous than we had supposed it to be. There is in the existing state of our knowledge a rational probability of 2 to 1 against white, a probability fit to be made a basis of conduct. No reasonable person would lay an even wager in favour of white against black and red, though against black alone or red alone he might do so without imprudence. The common theory, therefore, of the calculation of chances appears to be tenable. even when we know nothing except the number of the possible and mutually excluding contingencies, and are entirely ignorant of their comparative frequency, we may have grounds, and grounds numerically appreciable, for acting on one supposition rather than on another, and this is the meaning of probability. Part 3. The principle, however, on which the reasoning proceeds is sufficiently evident. It is the obvious one that when the cases which exist are shared among several kinds, it is impossible that each of those kinds should be a majority of the whole. On the contrary, there must be a majority against each kind, except one at most, and if any kind has more than its share in proportion to the total number, the others collectively must have less. Granting this axiom, and assuming that we have no ground for selecting any one kind as more likely than the rest to surpass the average proportion, it follows that we cannot rationally presume this of any, which we should do if we were to bet in favour of it, receiving less odds than in the ratio of the number of the other kinds. Even, therefore, in this extreme case of the calculation of probabilities, which does not rest on special experience at all, the logical ground of the process is our knowledge, such knowledge as we then have, of the laws governing the frequency of occurrence of the different cases. But in this case the knowledge is limited to that which, being universal and axiomatic, does not require reference to specific experience, or to any considerations arising out of the special nature of the problem under discussion. Except, however, in such cases as games of chance, where the very purpose in view requires ignorance instead of knowledge, I can conceive no case in which we ought to be satisfied with such an estimate of chances as this, an estimate founded on the absolute minimum of knowledge respecting the subject. It is plain that, in the case of the coloured balls, a very slight ground of surmise that the white balls were really more numerous than either of the other colours would suffice to vitiate the whole of the calculations made in our previous state of indifference. It would place us in that position of more advanced knowledge, in which the probabilities, to us, would be different from what they were before. And in estimating these new probabilities, we should have to proceed on a totally different set of data, furnished no longer by mere counting of possible suppositions, but by specific knowledge of facts. Such data it should always be our endeavour to obtain, and in all inquiries, unless on subjects equally beyond the range of our means of knowledge and our practical uses, they may be obtained, if not good, at least better than none at all. Footnote. It even appears to me that the calculation of chances, where there are no doubt grounded either on special experience or on special inference, must, in an immense majority of cases, break down from sheer impossibility of assigning any principle by which to be guided in setting out the list of possibilities. In the case of the coloured balls, we have no difficulty in making the enumeration, because we ourselves determine what the possibilities shall be. But suppose a case more analogous to those which occur in nature. Instead of 3 colours, let there be in the box all possible colours, we being supposed ignorant of the comparative frequency with which different colours occur in nature or in the productions of art. How is the list of cases to be made out? Is every distinct shade to count as a colour? If so, is the test to be a common eye or an educated eye, a painter's, for instance? On the answer to these questions would depend whether the chances against some particular colour would be estimated at 10, 20, or perhaps 500 to 1, while if we knew from experience that the particular colour occurs on an average a certain number of times in every 100 or 1,000, we should not require to know anything either of the frequency or of the number of the other possibilities. End footnote. It is obvious, too, that even when the probabilities are derived from observation and experiment, a very slight improvement in the data by better observations or by taking into fuller consideration the special circumstances of the case, is of more use than the most elaborate application of the calculus to probabilities founded on the data in their previous state of inferiority. The neglect of this obvious reflection has given rise to misapplications of the calculus of probabilities, which have made it the real opprobrium of mathematics. It is sufficient to refer to the applications made of it to the credibility of witnesses and to the correctness of the verdicts of juries. In regard to the first, common sense would dictate that it is impossible to strike a general average of the veracity and other qualifications for true testimony of mankind or of any class of them, and even if it were possible, the employment of it for such a purpose implies a misapprehension of the use of averages, which serve, indeed, to protect those whose interest is at stake against mistaking the general result of large masses of instances, but are of extremely small value as grounds of expectation in any one individual instance, unless the case be one of those in which the great majority of individual instances do not differ much from the average. In the case of a witness, persons of common sense would draw their conclusions from the degree of consistency of his statements, his conduct under cross-examination, and the relation of the case itself to his interests, his partialities, and his mental capacity, instead of applying so rude a standard, even if it were capable of being verified, as the ratio between the number of true and the number of erroneous statements which he may be supposed to make in the course of his life. Again, on the subject of juries or other tribunals, some mathematicians have set out from the proposition that the judgment of any one judge or juryman is, at least in some small degree, more likely to be right than wrong, and have concluded that the chance of a number of persons concurring in a wrong verdict is diminished the more the number is increased, so that if the judges are only made sufficiently numerous, the correctness of the judgment may be reduced almost to certainty. I say nothing of the disregard shown to the effect produced on the moral position of the judges by multiplying their numbers, the virtual destruction of their individual responsibility, and weakening of the application of their minds to the subject. I remark only the fallacy of reasoning from a wide average to cases necessarily differing greatly from any average. It may be true that, taking all causes one with another, the opinion of any one of the judges would be oftener right than wrong. But the argument forgets that in all but the more simple cases, in all cases in which it is really of much consequence what the tribunal is, the proposition might probably be reversed. Besides which, the cause of error, whether arising from the intricacy of the case, or from some common prejudice or mental infirmity, if it acted upon one judge, would be extremely likely to affect all the others in the same manner, or at least a majority, and thus render a wrong instead of a right decision more probable the more the number was increased. These are but samples of the errors frequently committed by men who, having made themselves familiar with the difficult formulae which algebra affords for the estimation of chances under suppositions of a complex character, like better to employ those formulae in computing what are the probabilities to a person half informed about a case, than to look out for means of being better informed. Before applying the doctrine of chances to any scientific purpose, the foundation must be laid for an evaluation of the chances, by possessing ourselves of the utmost attainable amount of positive knowledge. The knowledge required is that of the comparative frequency with which the different events in fact occur. For the purposes, therefore, of the present work, it is allowable to suppose that conclusions respecting the probability of a fact of a particular kind rest on our knowledge of the proportion between the cases in which facts of that kind occur, and those in which they do not occur. This knowledge being either derived from specific experiment or deduced from our knowledge of the causes in operation which tend to produce, compared with those which tend to prevent, the fact in question. Such calculation of chances is grounded on an induction, and to render the calculation legitimate, the induction must be a valid one. It is not less an induction, though it does not prove that the event occurs in all cases of a given description, but only that out of a given number of such cases it occurs in about so many. The fraction which mathematicians use to designate the probability of an event is the ratio of these two numbers, the ascertained proportion between the number of cases in which the event occurs and the sum of all the cases, those in which it occurs and in which it does not occur, taken together. In playing at cross and pile, the description of cases concerned are throws, and the probability of cross is 1/2, because if we throw often enough, cross is thrown about once in every 2 throws. In the cast of a die, the probability of ace is 1/6, not simply because there are 6 possible throws, of which ace is one, and because we do not know any reason why one should turn up rather than another, though I have admitted the validity of this ground in default of a better, but because we do actually know, either by reasoning or by experience, that in 100 or 1,000,000 of throws, ace is thrown about 1/6 of that number, or 1 in 6 times. Part 4. I say, either by reasoning or by experience, meaning specific experience. But in estimating probabilities, it is not a matter of indifference from which of these two sources we derive our assurance. The probability of events as calculated from their mere frequency in past experience affords a less secure basis for practical guidance than their probability as deduced from an equally accurate knowledge of the frequency of occurrence of their causes. The generalization that an event occurs in 10 out of every 100 cases of a given description is as real an induction as if the generalization were that it occurs in all cases. But when we arrive at the conclusion by merely counting instances in actual experience and comparing the number of cases in which A has been present with the number in which it has been absent, the evidence is only that of the method of agreement, and the conclusion amounts only to an empirical law. We can make a step beyond this when we can ascend to the causes on which the occurrence of A or its non-occurrence will depend, and form an estimate of the comparative frequency of the causes favourable and of those unfavourable to the occurrence. These are data of a higher order, by which the empirical law derived from a mere numerical comparison of affirmative and negative instances will be either corrected or confirmed, and in either case we shall obtain a more correct measure of probability than is given by that numerical comparison. It has been well remarked that in the kind of examples by which the doctrine of chances is usually illustrated, that of balls in a box, the estimate of probabilities is supported by reasons of causation, stronger than specific experience. Quote, "What is the reason that in a box where there are 9 black balls and 1 white, we expect to draw a black ball 9 times as much, in other words, 9 times as often, frequency being the gauge of intensity in expectation, as a white? Obviously, because the local conditions are 9 times as favourable, because the hand may alight in 9 places and get a black ball, while it can only alight in 1 place and find a white ball, just for the same reason that we do not expect to succeed in finding a friend in a crowd. The conditions in order that we and he should come together being many and difficult. This, of course, would not hold to the same extent were the white balls of smaller size than the black. Neither would the probability remain the same. The larger ball would be much more likely to meet the hand." End quote. Footnote. Prospective Review for February 1850. End footnote. It is in fact evident that when one causation is admitted as a universal law, our expectation of events can only be rationally grounded on that law. To a person who recognizes that every event depends on causes, a thing's having happened once is a reason for expecting it to happen again, only because proving that there exists, or is liable to exist, a cause adequate to produce it. Footnote. Quote, if this be not so, why do we feel so much more probability added by the first instance than by any single subsequent instance? Why, except that the first instance gives us its possibility, a cause adequate to it, while every other only gives us the frequency of its conditions? If no reference to a cause be supposed, possibility would have no meaning, yet it is clear that, antecedent to its happening, we might have supposed the event impossible, that is, have believed that there was no physical energy really existing in the world equal to producing it. After the first time of happening, which is then more important to the whole probability than any other single instance, because proving the possibility, the number of times becomes important as an index to the intensity or extent of the cause and its independence of any particular time. If we took the case of a tremendous leap, for instance, and wished to form an estimate of the probability of its succeeding a certain number of times, the first instance, by showing its possibility, before doubtful, is of the most importance, but every succeeding leap shows the power to be more perfectly under control, greater and more invariable, and so increases the probability, and no one would think of reasoning in this case straight from one instance to the next, without referring to the physical energy which each leap indicated. Is it not, then, clear that we do not ever, let us rather say that we do not in an advanced state of our knowledge, conclude directly from the happening of an event to the probability of its happening again, but that we refer to the cause regarding the past cases as an index to the cause, and the cause as our guide to the future. End quote. End footnote. The frequency of the particular event, apart from all surmise respecting its cause, can give rise to no other induction than that per enumerationem simplicem, and the precarious inferences derived from this are superseded and disappear from the field as soon as the principle of causation makes its appearance there. Notwithstanding, however, the abstract superiority of an estimate of probability grounded on causes, it is a fact that in almost all cases in which chances admit of estimation sufficiently precise to render their numerical appreciation of any practical value, the numerical data are not drawn from knowledge of the causes, but from experience of the events themselves. The probabilities of life at different ages or in different climates, the probabilities of recovery from a particular disease, the chances of the birth of a male or female offspring, the chances of the destruction of houses or other property by fire, the chances of the loss of a ship in a particular voyage are deduced from bills of mortality, returns from hospitals, registers of births, of shipwrecks, and so on, that is, from the observed frequency, not of the causes, but of the effects. The reason is that in all these classes of facts the causes are either not amenable to direct observation at all, or not with the requisite precision, and we have no means of judging of their frequency except from the empirical law afforded by the frequency of the effects. The inference does not the less depend on causation alone. We reason from an effect to a similar effect by passing through the cause. If the actuary of an insurance office infers from his tables that among 100 persons now living of a particular age, 5 on the average will attain the age of 70, his inference is legitimate, not for the simple reason that this is the proportion who have lived till 70 in times past, but because the fact of their having so lived shows that this is the proportion existing at that place and time between the causes which prolong life to the age of 70 and those tending to bring it to an earlier close. Footnote. The writer last quoted says that the valuation of chances by comparing the number of cases in which the event occurs with the number in which it does not occur, quote, would generally be wholly erroneous and is not the true theory of probability, end quote. It is at least that which forms the foundation of insurance and of all those calculations of chances in the business of life which experience so abundantly verifies. The reason which the reviewer gives for rejecting the theory is that it, quote, would regard an event as certain which had hitherto never failed, which is exceedingly far from the truth, even for a very large number of constant successes, end quote. This is not a defect in a particular theory, but in any theory of chances. No principle of evaluation can provide for such a case as that which the reviewer supposes. If an event has never once failed in a number of trials sufficient to eliminate chance, it really has all the certainty which can be given by an empirical law. It is certain during the continuance of the same collocation of causes which existed during the observations. If it ever fails, it is in consequence of some change in that collocation. Now, no theory of chances will enable us to infer the future probability of an event from the past. If the causes in operation capable of influencing the event have intermediately undergone a change. End footnote. Part 5. From the preceding principles it is easy to deduce the demonstration of that theorem of the doctrine of probabilities which is the foundation of its application to inquiries for ascertaining the occurrence of a given event, or the reality of an individual fact. The signs or evidences by which a fact is usually proved are some of its consequences, and the inquiry hinges upon determining what cause is most likely to have produced a given effect. The theorem applicable to such investigations is the sixth principle in Laplace's Essai philosophique sur les probabilités, which is described by him as the, quote, fundamental principle of that branch of the analysis of chances which consists in ascending from events to their causes. End quote. Footnote. Pages 18 through 19. The theorem is not stated by Laplace in the exact terms in which I have stated it, but the identity of import of the two modes of expression is easily demonstrable. End footnote. Given an effect to be accounted for, and there being several causes which might have produced it, but of the presence of which in this particular case nothing is known, the probability that the effect was produced by any one of these causes is as the antecedent probability of the cause multiplied by the probability that the cause, if it existed, would have produced the given effect. Let M be the effect, and A, B, two causes, by either of which it might have been produced. To find the probability that it was produced by the one and not by the other, ascertain which of the two is most likely to have existed, and which of them, if it did exist, was most likely to produce the effect M. The probability sought is a compound of these two probabilities. Case 1. Let the causes be both alike in the second respect, either A or B when it exists being supposed equally likely, or equally certain, to produce M. But let A be in itself twice as likely as B to exist, that is, twice as frequent a phenomenon. Then it is twice as likely to have existed in this case, and to have been the cause which produced M. For since A exists in nature twice as often as B, in any 300 cases in which one or the other existed, A has existed 200 times and B 100. But either A or B must have existed wherever M is produced. Therefore, in 300 times that M is produced, A was the producing cause 200 times, B only 100, that is, in the ratio of 2 to 1. Thus, then, if the causes are alike in their capacity of producing the effect, the probability as to which actually produced it is in the ratio of their antecedent probabilities. Case 2. Reversing the last hypothesis, let us suppose that the causes are equally frequent, equally likely to have existed, but not equally likely, if they did exist, to produce M. That in 3 times in which A occurs, it produces that effect twice, while B, in 3 times, produces it only once. Since the two causes are equally frequent in their occurrence, in every 6 times that either one or the other exists, A exists 3 times and B 3 times. A, of its 3 times, produces M in 2. B, of its 3 times, produces M in 1. Thus, in the whole 6 times, M is produced only thrice, but of that thrice it is produced twice by A, once only by B. Consequently, when the antecedent probabilities of the causes are equal, the chances that the effect was produced by them are in the ratio of the probabilities that if they did exist, they would produce the effect. Case 3. The third case, that in which the causes are unlike in both respects, is solved by what has preceded. For, when a quantity depends on 2 other quantities, in such a manner that while either of them remains constant it is proportional to the other, it must necessarily be proportional to the product of the 2 quantities, the product being the only function of the 2 which obeys that law of variation. Therefore, the probability that M was produced by either cause is, as the antecedent probability of the cause, multiplied by the probability that, if it existed, it would produce M, which was to be demonstrated. Or we may prove the third case as we proved the first and second. Let A be twice as frequent as B, and let them also be unequally likely, when they exist, to produce M. Let A produce it twice in 4 times, B thrice in 4 times. The antecedent probability of A is to that of B as 2 to 1. The probabilities of their producing M are as 2 to 3. The product of these ratio is the ratio of 4 to 3, and this will be the ratio of the probabilities that A or B was the producing cause in the given instance. For since A is twice as frequent as B, out of 12 cases in which one or the other exists, A exists in 8 and B in 4. But of its 8 cases, A, by the supposition, produces M in only 4, while B of its 4 cases produces M in 3. M therefore is only produced at all in 7 of the 12 cases, but in 4 of these it is produced by A, in 3 by B. Hence the probabilities of it being produced by A and by B are as 4 to 3, and are expressed by the fractions 4/7 and 3/7, which was to be demonstrated. Part 6. It remains to examine the bearing of the doctrine of chances on the peculiar problem which occupied us in the preceding chapter, namely, how to distinguish coincidences which are casual from those which are the result of law, from those in which the facts which accompany or follow one another are somehow connected through causation. The doctrine of chances affords means by which, if we knew the average number of coincidences to be looked for between two phenomena connected only casually, we could determine how often any given deviation from that average will occur by chance. If the probability of any casual coincidence, considered in itself, be 1 divided by m, the probability that the same coincidence will be repeated n times in succession is 1 divided by m raised to the power n. For example, in one throw of a die, the probability of ace being 1 divided by 6, the probability of throwing ace twice in succession will be 1 divided by the square of 6, or 1 divided by 36. For aces thrown at the first throw once in 6, or 6 in 36 times, and of those 6 the die being cast again, ace will be thrown but once, being altogether once in 36 times. The chance of the same cast 3 times successively is, by a similar reasoning, 1 divided by 6 cubed, or 1 divided by 216. That is, the event will happen on a large average only once in 216 throws. We have thus a rule by which to estimate the probability that any given series of coincidences arises from chance, provided we can measure correctly the probability of a single coincidence. If we can obtain an equally precise expression for the probability that the same series of coincidences arises from causation, we should only have to compare the numbers. This, however, can rarely be done. Let us see what degree of approximation can practically be made to the necessary precision. The question falls within Laplace's sixth principle just demonstrated. The given fact, that is to say, the series of coincidences, may have originated either in a casual conjunction of causes or in a law of nature. The probabilities, therefore, that the fact originated in these two modes are, as their antecedent probabilities, multiplied by the probabilities that, if they existed, they would produce the effect. But the particular combination of chances, if it occurred, or the law of nature, if real, would certainly produce the series of coincidences. The probabilities, therefore, that the coincidences are produced by the two causes in question are as the antecedent probabilities of the causes. One of these, the antecedent probability of the combination of mere chances which would produce the given result, is an appreciable quantity. The antecedent probability of the other supposition may be susceptible of a more or less exact estimation according to the nature of the case. In some cases, the coincidence, supposing it to be the result of causation at all, must be the result of a known cause, as the succession of aces, if not accidental, must arise from the loading of the die. In such cases we may be able to form a conjecture as to the antecedent probability of such a circumstance from the characters of the parties concerned, or other such evidence, but it would be impossible to estimate that probability with anything like numerical precision. The counter-probability, however, that of the accidental origin of the coincidence, dwindling so rapidly as it does at each new trial, the stage is soon reached at which the chance of unfairness in the die, however small in itself, must be greater than that of a casual coincidence, and on this ground a practical decision can generally be come to without much hesitation, if there be the power of repeating the experiment. When, however, the coincidence is one which cannot be accounted for by any known cause, and the connection between the two phenomena, if produced by causation, must be the result of some law of nature hitherto unknown, which is the case we had in view in the last chapter, then though the probability of a casual coincidence may be capable of appreciation, that of the counter-supposition, the existence of an undiscovered law of nature, is clearly unsusceptible of even an approximate valuation. In order to have the data which such a case would require, it would be necessary to know what proportion of all the individual sequences or coexistences occurring in nature are the result of law, and what proportion are merely casual coincidences. It being evident that we cannot form any plausible conjecture as to this proportion, much less appreciate it numerically, we cannot attempt any precise estimation of the comparative probabilities. But of this we are sure, that the detection of an unknown law of nature, of some previously unrecognized constancy of conjunction among phenomena, is no uncommon event. If, therefore, the number of instances in which a coincidence is observed over and above that which would arise on the average from the mere concurrence of chances be such that so great an amount of coincidences from accident alone would be an extremely uncommon event, we have reason to conclude that the coincidence is the effect of causation, and may be received, subject to correction from further experience, as an empirical law. Further than this, in point of precision, we cannot go, nor, in most cases, is greater precision required for the solution of any practical doubt. Footnote. For a fuller treatment of the many interesting questions raised by the theory of probabilities, I may now refer to a recent work by Mr. Venn, Fellow of Caius College, Cambridge. The Logic of Chance, one of the most thoughtful and philosophical treatises on any subject connected with logic and evidence which have been produced, to my knowledge, for many years. Some criticisms contained in it have been very useful to me in revising the corresponding chapters of the present work. In several of Mr. Venn's opinions, however, I do not agree. What these are will be obvious to any reader of Mr. Venn's work, who is also a reader of this. End footnote. End of section 52. Section 53 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 19 of the Extension of Derivative Laws to Adjacent Cases. Part 1. We have had frequent occasion to notice the inferior generality of derivative laws, compared with the ultimate laws from which they are derived. This inferiority, which affects not only the extent of the propositions themselves, but their degree of certainty within that extent, is most conspicuous in the uniformities of coexistence and sequence obtaining between effects which depend ultimately on different primeval causes. Such uniformities will only obtain where there exists the same collocation of those primeval causes. If the collocation varies, though the laws themselves remain the same, a totally different set of derivative uniformities may, and generally will, be the result. Even where the derivative uniformity is between different effects of the same cause, it will by no means obtain as universally as the law of the cause itself. If lower a and lower b accompany or succeed one another as effects of the cause upper A, it by no means follows that upper A is the only cause which can produce them, or that if there be another cause, as upper B, capable of producing lower A, it must produce lower B likewise. The conjunction, therefore, of lower A and lower B perhaps does not hold universally, but only in the instances in which lower A arises from upper A. When it is produced by a cause other than upper A, lower A and lower B may be dissevered. Day, for example, is always in our experience followed by night, but day is not the cause of night. Both are successive effects of a common cause, the periodical passage of the spectator into and out of the earth's shadow, consequent on the earth's rotation, and on the illuminating property of the sun. If, therefore, day is ever produced by a different cause or set of causes from this, day will not, or at least may not, be followed by night. On the sun's own surface, for instance, this may be the case. Finally, even when the derivative uniformity is itself a law of causation, resulting from the combination of several causes, it is not altogether independent of collocations. If a cause supervenes capable of wholly or partially counteracting the effect of any one of the conjoined causes, the effect will no longer conform to the derivative law. While, therefore, each ultimate law is only liable to frustration from one set of counteracting causes, the derivative law is liable to it from several. Now, the possibility of the occurrence of counteracting causes which do not arise from any of the conditions involved in the law itself depends on the original collocations. It is true that, as we formerly remarked, laws of causation, whether ultimate or derivative, are in most cases fulfilled even when counteracted. The cause produces its effect, though that effect is destroyed by something else. That the effect may be frustrated is therefore no objection to the universality of laws of causation, but it is fatal to the universality of the sequences or coexistences of effects, which compose the greater part of the derivative laws flowing from laws of causation. When, from the law of a certain combination of causes, there results a certain order in the effects, as from the combination of a single sun with the rotation of an opaque body round its axis, there results, on the whole surface of that opaque body, an alternation of day and night. Then, if we suppose one of the combined causes counteracted, the rotation stopped, the sun extinguished, or a second sun superadded, the truth of that particular law of causation is in no way affected. It is still true that one sun, shining on an opaque revolving body, will alternately produce day and night. But since the sun no longer does shine on such a body, the derivative uniformity, the succession of day and night on the given planet, is no longer true. Those derivative uniformities, therefore, which are not laws of causation, are, except in the rare case of their depending on one cause alone, not on a combination of causes, always more or less contingent on collocations, and are hence subject to the characteristic infirmity of empirical laws, that of being admissible only where the collocations are known by experience to be such as are requisite for the truth of the law, that is, only within the conditions of time and place confirmed by actual observation. Part 2. This principle, when stated in general terms, seems clear and indisputable. Yet many of the ordinary judgments of mankind, the propriety of which is not questioned, have at least the semblance of being inconsistent with it. On what grounds, it may be asked, do we expect that the sun will rise tomorrow? Tomorrow is beyond the limits of time comprehended in our observations. They have extended over some thousands of years past, but they do not include the future. Yet we infer with confidence that the sun will rise tomorrow, and nobody doubts that we are entitled to do so. Let us consider what is the warrant for this confidence. In the example in question, we know the causes on which the derivative uniformity depends. They are the sun giving out light, the earth in a state of rotation and intercepting light. The induction which shows these to be the real causes, and not merely prior effects of a common cause, being complete, the only circumstances which could defeat the derivative law are such as would destroy or counteract one or other of the combined causes. While the causes exist and are not counteracted, the effect will continue. if they exist and are not counteracted tomorrow, the sun will rise tomorrow. Since the causes, namely the sun and the earth, the one in the state of giving out light, the other in a state of rotation, will exist until something destroys them, all depends on the probabilities of their destruction, or of their counteraction. We know by observation, omitting the inferential proofs of an existence for thousands of ages anterior, that these phenomena have continued for, say, 5,000 years. Within that time there has existed no cause sufficient to diminish them appreciably, nor which has counteracted their effects in any appreciable degree. The chance, therefore, that the sun may not rise tomorrow amounts to the chance that some cause, which has not manifested itself in the smallest degree during 5,000 years, will exist tomorrow in such intensity as to destroy the sun or the earth, the sun's light or the earth's rotation, or to produce an immense disturbance in the effect resulting from those causes. Now, if such a cause will exist tomorrow, or at any future time, some cause, proximate or remote, of that cause must exist now, and must have existed during the whole of the 5,000 years. If, therefore, the sun do not rise tomorrow, it will be because some cause has existed, the effects of which, though during 5,000 years they have not amounted to a perceptible quantity, will in one day become overwhelming. Since this cause has not been recognized during such an interval of time by observers stationed on our earth, it must, if it be a single agent, be either one whose effects develop themselves gradually and very slowly, or one which existed in regions beyond our observation, and is now on the point of arriving in our part of the universe. Now, all causes which we have experience of act according to laws incompatible with the supposition that their effects, after accumulating so slowly as to be imperceptible for 5,000 years, should start into immensity in a single day. No mathematical law of proportion between an effect and the quantity or relations of its cause could produce such contradictory results. The sudden development of an effect of which there was no previous trace always arises from the coming together of several distinct causes, not previously conjoined. But if such sudden conjunction is destined to take place, the causes, or their causes, must have existed during the entire 5,000 years, and their not having once come together during that period shows how rare that particular combination is. We have, therefore, the warrant of a rigid induction for considering it probable, in a degree undistinguishable from certainty, that the known conditions requisite for the sun's rising will exist tomorrow. Part 3. But this extension of derivative laws, not causative, beyond the limits of observation, can only be to adjacent cases. If instead of tomorrow we had said this day 20,000 years, the inductions would have been anything but conclusive. That a cause which, in opposition to very powerful causes, produced no perceptible effect during 5,000 years, should produce a very considerable one by the end of 20,000, has nothing in it which is not in conformity with our experience of causes. We know many agents, the effect of which in a short period does not amount to a perceptible quantity, but by accumulating for a much longer period becomes considerable. Besides, looking at the immense multitude of the heavenly bodies, their vast distances, and the rapidity of the motion of such of them as are known to move, it is a supposition not at all contradictory to experience that some body may be in motion toward us, or we toward it, within the limits of whose influence we have not come during 5,000 years, but which, in 20,000 more, may be producing effects upon us of the most extraordinary kind. Or the fact which is capable of preventing sunrise may be, not the cumulative effect of one cause, but some new combination of causes, and the chances favourable to that combination, though they have not produced it once in 5,000 years, may produce it once in 20,000. So that the inductions which authorize us to expect future events grow weaker and weaker the further we look into the future, and at length become inappreciable. We have considered the probabilities of the sun's rising tomorrow as derived from the real laws, that is, from the laws of the causes on which that uniformity is dependent. Let us now consider how the matter would have stood if the uniformity had been known only as an empirical law. If we had not been aware that the sun's light and the earth's rotation, or the sun's motion, were the causes on which the periodical occurrence of daylight depends, we could have extended this empirical law to cases adjacent in time, though not to so great a distance of time as we can now. Having evidence that the effects had remained unaltered and been punctually conjoined for 5,000 years, we could infer that the unknown causes on which the conjunction is dependent had existed undiminished and uncounteracted during the same period. The same conclusions, therefore, would follow as in the preceding case, except that we should only know that during 5,000 years nothing had occurred to defeat perceptibly this particular effect, while when we know the causes, we have the additional assurance that during that interval no such change has been noticeable in the causes themselves as by any degree of multiplication or length of continuance could defeat the effect. To this must be added that when we know the causes, we may be able to judge whether there exists any known cause capable of counteracting them, while as long as they are unknown, we cannot be sure but that if we did know them, we could predict their destruction from causes actually in existence. A bedridden savage who had never seen the cataract of Niagara, but who lived within hearing of it, might imagine that the sound he heard would endure forever. But if he knew it to be the effect of a rush of waters over a barrier of rock, which is progressively wearing away, he would know that within a number of ages which may be calculated, it will be heard no more. In proportion, therefore, to our ignorance of the causes on which the empirical law depends, we can be less assured that it will continue to hold good. And the further we look into futurity, the less improbable is it that some one of the causes, whose coexistence gives rise to the derivative uniformity, may be destroyed or counteracted. With every prolongation of time, the chances multiply of such an event. That is to say, its non-occurrence hitherto becomes a less guarantee of its not occurring within the given time. If, then, it is only to cases which in point of time are adjacent, or nearly adjacent, to those which we have actually observed, that any derivative law, not of causation, can be extended with an assurance equivalent to certainty, much more is this true of a merely empirical law. Happily, for the purposes of life, it is to such cases alone that we can almost ever have occasion to extend them. In respect of place, it might seem that a merely empirical law could not be extended even to adjacent cases, that we could have no assurance of its being true in any place where it has not been specially observed. The past duration of a cause is a guarantee for its future existence, unless something occurs to destroy it. But the existence of a cause in one or any number of places is no guarantee for its existence in any other place, since there is no uniformity in the collocations of primeval causes. When, therefore, an empirical law is extended beyond the local limits within which it has been found true by observation, the cases to which it is thus extended must be such as are presumably within the influence of the same individual agents. If we discover a new planet within the known bounds of the solar system, or even beyond those bounds, but indicating its connection with the system by revolving round the sun, we may conclude with great probability that it revolves on its axis, for all the known planets do so, and this uniformity points to some common cause antecedent to the first records of astronomical observation. And though the nature of this cause can only be matter of conjecture, yet if it be, as is not unlikely, and as Laplace's theory supposes, not merely the same kind of cause, but the same individual cause, such as an impulse given to all the bodies at once, that cause, acting at the extreme points of the space occupied by the sun and planets, is likely, unless defeated by some counteracting cause, to have acted at every intermediate point and probably somewhat beyond, and therefore acted in all probability upon the supposed newly discovered planet. When, therefore, effects which are always found conjoined can be traced with any probability to an identical, and not merely a similar, origin, we may, with the same probability, extend the empirical law of their conjunction to all places within the extreme local boundaries within which the fact has been observed, subject to the possibility of counteracting causes in some portion of the field. Still more confidently may we do so when the law is not merely empirical, when the phenomena which we find conjoined are effects of ascertained causes, from the laws of which the conjunction of their effects is deducible. In that case, we may both extend the derivative uniformity over a larger space, and with less abatement for the chance of counteracting causes. The first, because instead of the local boundaries of our observation of the fact itself, we may include the extreme boundaries of the ascertained influence of its causes. Thus, the succession of day and night, we know, holds true of all the bodies of the solar system except the sun itself. But we know this only because we are acquainted with the causes. If we were not, we could not extend the proposition beyond the orbits of the earth and moon, at both extremities of which we have the evidence of observation for its truth. With respect to the probability of counteracting causes, it has been seen that this calls for a greater abatement of confidence in proportion to our ignorance of the causes on which the phenomena depend. On both accounts, therefore, a derivative law, which we know how to resolve, is susceptible of a greater extension to cases adjacent in place than a merely empirical law. End of section 53. Section 54 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 20 of Analogy. Part 1. The word analogy, as the name of a mode of reasoning, is generally taken for some kind of argument supposed to be of an inductive nature, but not amounting to a complete induction. There is no word, however, which is used more loosely or in a greater variety of senses than analogy. It sometimes stands for arguments which may be examples of the most rigorous induction. Archbishop Whately, for instance, following Ferguson and other writers, defines analogy conformably to its primitive acceptation, that which was given to it by mathematicians, resemblance of relations. In this sense, when a country which has sent out colonies is termed the mother country, the expression is analogical, signifying that the colonies of a country stand in the same relation to her in which children stand to their parents. And if any inference be drawn from this resemblance of relations, as, for instance, that obedience or affection is due from colonies to the mother country, this is called reasoning by analogy. Or, if it be argued that a nation is most beneficially governed by an assembly elected by the people, from the admitted fact that other associations for a common purpose, such as joint stock companies, are best managed by a committee chosen by the parties interested. This, too, is an argument from analogy in the preceding sense, because its foundation is, not that a nation is like a joint stock company, or Parliament like a board of directors, but that Parliament stands in the same relation to the nation in which a board of directors stands to a joint stock company. Now, in an argument of this nature, there is no inherent inferiority of conclusiveness. Like other arguments from resemblance, it may amount to nothing, or it may be a perfect and conclusive induction. The circumstance in which two cases resemble may be capable of being shown to be the material circumstance, to be that on which all the consequences necessary to be taken into account in the particular discussion depend. In the example last given, the resemblance is one of relation, the fundamentum relationis being the management by a few persons of affairs in which a much greater number are interested along with them. Now, some may contend that this circumstance, which is common to the two cases, and the various consequences which follow from it, have the chief share in determining all the effects which make up what we term good or bad administration. If they can establish this, their argument has the force of a rigorous induction. If they cannot, they are said to have failed in proving the analogy between the two cases, a mode of speech which implies that when the analogy can be proved, the argument founded on it cannot be resisted. Part 2. It is on the whole more usual, however, to extend the name of analogical evidence to arguments from any sort of resemblance, provided they do not amount to a complete induction, without peculiarly distinguishing resemblance of relations. Analogical reasoning, in this sense, may be reduced to the following formula. Two things resemble each other in one or more respects. A certain proposition is true of the one, therefore it is true of the other. But we have nothing here by which to discriminate analogy from induction, since this type will serve for all reasoning from experience. In the strictest induction, equally with the faintest analogy, we conclude, because A resembles B in one or more properties, that it does so in a certain other property. The difference is that in the case of a complete induction, it has been previously shown by due comparison of instances that there is an invariable conjunction between the former property or properties and the latter property. But in what is called analogical reasoning, no such conjunction has been made out. There have been no opportunities of putting in practice the method of difference or even the method of agreement. But we conclude, and that is all which the argument of analogy amounts to, that a fact M known to be true of A is more likely to be true of B if B agrees with A in some of its properties, even though no connection is known to exist between M and those properties, than if no resemblance at all could be traced between B and any other thing known to possess the attribute M. To this argument it is of course requisite that the properties common to A with B shall be merely not known to be connected with M, they must not be properties known to be unconnected with it. If, either by process of elimination or by deduction from previous knowledge of the laws of the properties in question, it can be concluded that they have nothing to do with M, the argument of analogy is put out of court. The supposition must be that M is an effect really dependent on some property of A, but we know not on which. We cannot point out any of the properties of A, which is the cause of M, or united with it by any law. After rejecting all which we know to have nothing to do with it, there remain several between which we are unable to decide, of which remaining properties B possesses one or more. This, accordingly, we consider as affording grounds of more or less strength for concluding by analogy that B possesses the attribute M. There can be no doubt that every such resemblance which can be pointed out between B and A affords some degree of probability beyond what would otherwise exist in favour of the conclusion drawn from it. If B resembled A in all its ultimate properties, its possessing the attribute M would be a certainty, not a probability, and every resemblance which can be shown to exist between them places it by so much the nearer to that point. If the resemblance be in an ultimate property, there will be resemblance in all the derivative properties dependent on that ultimate property, and of these M may be one. If the resemblance be in a derivative property, there is reason to expect resemblance in the ultimate property on which it depends, and in the other derivative properties dependent on the same ultimate property. Every resemblance which can be shown to exist affords ground for expecting an indefinite number of other resemblances. The particular resemblance sought will, therefore, be oftener found among things thus known to resemble than among things between which we know of no resemblance. For example, I might infer that there are probably inhabitants in the moon, because there are inhabitants on the earth, in the sea, and in the air, and this is the evidence of analogy. The circumstance of having inhabitants is here assumed not to be an ultimate property, but, as is reasonable to suppose, a consequence of other properties, and depending therefore, in the case of the earth, on some of its properties as a portion of the universe, but on which of those properties we know not. Now, the moon resembles the earth in being a solid, opaque, nearly spherical substance, appearing to contain, or to have contained, active volcanoes, receiving heat and light from the sun in about the same quantity as our earth, revolving on its axis, composed of materials which gravitate, and obeying all the various laws resulting from that property. And I think no one will deny that if this were all that was known of the moon, the existence of inhabitants in that luminary would derive from these various resemblances to the earth a greater degree of probability than it would otherwise have, though the amount of the augmentation it would be useless to attempt to estimate. If, however, every resemblance proved between B and A in any point not known to be immaterial with respect to M forms some additional reason for presuming that B has the attribute M, it is clear, e contra, that every dissimilarity which can be proved between them furnishes a counter-probability of the same nature on the other side. It is not, indeed, unusual that different ultimate properties should, in some particular instances, produce the same derivative property. But on the whole it is certain that things which differ in their ultimate properties will differ at least as much in the aggregate of their derivative properties, and that the differences which are unknown will, on the average of cases, bear some proportion to those which are known. There will therefore be a competition between the known points of agreement and the known points of difference in A and B, and according as the one or the other may be deemed to preponderate, the probability derived from analogy will be for or against B's having the property M. The moon, for instance, agrees with the earth in the circumstances already mentioned, but differs in being smaller, in having its surface more unequal, and apparently volcanic throughout, in having at least on the side next the Earth no atmosphere sufficient to refract light, no clouds, and it is therefore concluded no water. These differences, considered merely as such, might perhaps balance the resemblances, so that analogy would afford no presumption either way. But considering that some of the circumstances which are wanting on the moon are among those which, on the earth, are found to be indispensable conditions of animal life, we may conclude that if that phenomenon does exist in the moon, or at all events on the nearer side, it must be as an effect of causes totally different from those on which it depends here, as a consequence, therefore, of the moon's differences from the earth, not of the points of agreement. Viewed in this light, all the resemblances which exist become presumptions against, not in favour, of the moon's being inhabited. Since life cannot exist there in the manner in which it exists here, the greater the resemblance of the lunar world to the terrestrial in other respects, the less reason we have to believe that it can contain life. There are, however, other bodies in our system, between which and the earth there is a much closer resemblance, which possess an atmosphere, clouds, consequently water, or some fluid analogous to it, and even give strong indications of snow in their polar regions, while the cold or heat, though differing greatly on the average from ours, is in some parts at least of those planets possibly not more extreme than in some regions of our own which are habitable. To balance these agreements, the ascertained differences are chiefly in the average light and heat, velocity of rotation, density of material, intensity of gravity, and similar circumstances of a secondary kind. With regard to these planets, therefore, the argument of analogy gives a decided preponderance in favour of their resembling the earth in any of its derivative properties, such as that of having inhabitants, though when we consider how immeasurably multitudinous are those of their properties which we are entirely ignorant of, compared with the few which we know, we can attach but trifling weight to any consideration of resemblance in which the known elements bear so inconsiderable a proportion to the unknown. Besides the competition between analogy and diversity, there may be a competition of conflicting analogies. The new case may be similar in some of its circumstances to cases in which the fact M exists, but in others to cases in which it is known not to exist. Amber has some properties in common with vegetable, others with mineral products. A painting of unknown origin may resemble, in certain of its characters, known works of a particular master, but in others it may as strikingly resemble those of some other painter. A vase may bear some analogy to works of Grecian and some to those of Etruscan or Egyptian art. We are of course supposing that it does not possess any quality which has been ascertained, by a sufficient induction, to be a conclusive mark either of the one or the other. Part 3. Since the value of an analogical argument inferring one resemblance from other resemblances without any antecedent evidence of a connection between them depends on the extent of ascertained resemblance, compared first with the amount of ascertained difference, and next with the extent of the unexplored region of unascertained properties, it follows that where the resemblance is very great, the ascertained difference very small, and our knowledge of the subject matter tolerably extensive, the argument from analogy may approach in strength very near to a valid induction. If, after much observation of B, we find that it agrees with A in 9 out of 10 of its known properties, we may conclude with a probability of 9 to 1 that it will possess any given derivative property of A. If we discover, for example, an unknown animal or plant resembling closely some known one in the greater number of the properties we observe in it, but differing in some few, we may reasonably expect to find in the unobserved remainder of its properties a general agreement with those of the former, but also a difference corresponding proportionately to the amount of observed diversity. It thus appears that the conclusions derived from analogy are only of any considerable value when the case to which we reason is an adjacent case, adjacent not as before in place or time, but in circumstances. In the case of effects of which the causes are imperfectly or not at all known, when consequently the observed order of their occurrence amounts only to an empirical law, it often happens that the conditions which have coexisted whenever the effect was observed have been very numerous. Now, if a new case presents itself in which all these conditions do not exist, but the far greater part of them do, some one or a few only being wanting, the inference that the effect will occur, notwithstanding this deficiency of complete resemblance to the cases in which it has been observed, may, though of the nature of analogy, possess a high degree of probability. It is hardly necessary to add that, however considerable this probability may be, no competent inquirer into nature will rest satisfied with it when a complete induction is attainable, but will consider the analogy as a mere guidepost, pointing out the direction in which more rigorous investigations should be prosecuted. It is in this last respect that considerations of analogy have the highest scientific value. The cases in which analogical evidence affords in itself any very high degree of probability are, as we have observed, only those in which the resemblance is very close and extensive. But there is no analogy, however faint, which may not be of the utmost value in suggesting experiments or observations that may lead to more positive conclusions. When the agents and their effects are out of the reach of further observation and experiment, as in the speculations already alluded to respecting the moon and planets, such slight probabilities are no more than an interesting theme for the pleasant exercise of imagination. But any suspicion, however slight, that sets an ingenious person at work to contrive an experiment, or affords a reason for trying one experiment rather than another, may be of the greatest benefit to science. On this ground, though I cannot accept as positive truths any of those scientific hypotheses which are unsusceptible of being ultimately brought to the test of actual induction, such, for instance, as the two theories of light, the emission theory of the last century, and the undulatory theory which predominates in the present, I am yet unable to agree with those who consider such hypotheses to be worthy of entire disregard. As is well said by Hartley, and concurred in by a thinker in general so diametrically opposed to Hartley's opinions as Dugald Stuart, quote, "Any hypothesis which has so much plausibility as to explain a considerable number of facts helps us to digest these facts in proper order, to bring new ones to light, and make experimenta crucis for the sake of future inquirers." End quote. Footnote: Hartley's Observations on Man, Volume 1, page 16. The passage is not in Priestley's curtailed edition. End footnote. If an hypothesis both explains known facts and has led to the prediction of others previously unknown and since verified by experience, the laws of the phenomenon which is the subject of inquiry must bear at least a great similarity to those of the class of phenomena to which the hypothesis assimilates it. And since the analogy which extends so far may probably extend further, nothing is more likely to suggest experiments tending to throw light upon the real properties of the phenomenon than the following out such an hypothesis. But to this end it is by no means necessary that the hypothesis be mistaken for a scientific truth. On the contrary, that illusion is in this respect, as in every other, an impediment to the progress of real knowledge, by leading inquirers to restrict themselves arbitrarily to the particular hypothesis which is most accredited at the time, instead of looking out for every class of phenomena between the laws of which and those of the given phenomenon any analogy exists, and trying all such experiments as may tend to the discovery of ulterior analogies pointing in the same direction. End of section 54. Section 55 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 21 of the Evidence of the Law of Universal Causation, Part 1. We have now completed our review of the logical processes by which the laws or uniformities of the sequence of phenomena and those uniformities in their coexistence which depend on the laws of their sequence are ascertained or tested. As we recognized in the commencement, and have been enabled to see more clearly in the progress of the investigation, the basis of all these logical operations is the law of causation. The validity of all the inductive methods depends on the assumption that every event or the beginning of every phenomenon must have some cause, some antecedent, on the existence of which it is invariably and unconditionally consequent. In the method of agreement this is obvious, that method avowedly proceeding on the supposition that we have found the true cause as soon as we have negatived every other. The assertion is equally true of the method of difference. That method authorizes us to infer a general law from two instances, one in which A exists together with a multitude of other circumstances, and B follows another, in which, A being removed and all other circumstances remaining the same, B is prevented. What, however, does this prove? It proves that B, in the particular instance, cannot have had any other cause than A, but to conclude from this that A was the cause, or that A will on other occasions be followed by B, is only allowable on the assumption that B must have some cause, that among its antecedents in any single instance in which it occurs, there must be one which has the capacity of producing it at other times. This being admitted, it is seen that in the case in question that antecedent can be no other than A, but that if it be no other than A, it must be A, is not proved by these instances at least, but taken for granted. There is no need to spend time in proving that the same thing is true of the other inductive methods. The universality of the law of causation is assumed in them all. But is this assumption warranted? Doubtless, it may be said, most phenomena are connected as effects with some antecedent or cause, that is, are never produced unless some assignable fact has preceded them. But the very circumstance that complicated processes of induction are sometimes necessary shows that cases exist in which this regular order of succession is not apparent to our unaided apprehension. If, then, the processes which bring these cases within the same category with the rest require that we should assume the universality of the very law which they do not at first sight appear to exemplify, is not this a petitio principii? Can we prove a proposition by an argument which takes it for granted? And if not so proved, on what evidence does it rest? For this difficulty, which I have purposely stated in the strongest terms it will admit of, the school of metaphysicians who have long predominated in this country find a ready salvo. They affirm that the universality of causation is a truth which we cannot help believing, that the belief in it is an instinct, one of the laws of our believing faculty. As the proof of this, they say, and they have nothing else to say, that everybody does believe it, and they number it among the propositions, rather numerous in their catalogue, which may be logically argued against, and perhaps cannot be logically proved, but which are of higher authority than logic, and so essentially inherent in the human mind that even he who denies them in speculation shows by his habitual practice that his arguments make no impression upon himself. Into the merits of this question, considered as one of psychology, it would be foreign to my purpose to enter here, but I must protest against adducing, as evidence of the truth of a fact in external nature, the disposition, however strong or however general, of the human mind to believe it. Belief is not proof, and does not dispense with the necessity of proof. I am aware that to ask for evidence of a proposition which we are supposed to believe instinctively is to expose oneself to the charge of rejecting the authority of the human faculties, which, of course, no one can consistently do, since the human faculties are all which anyone has to judge by, and inasmuch as the meaning of the word evidence is supposed to be something which, when laid before the mind, induces it to believe. To demand evidence when the belief is ensured by the mind's own laws is supposed to be appealing to the intellect against the intellect. But this, I apprehend, is a misunderstanding of the nature of evidence. By evidence is not meant anything and everything which produces belief. There are many things which generate belief besides evidence. A mere strong association of ideas often causes a belief so intense as to be unshakable by experience or argument. Evidence is not that which the mind does or must yield to, but that which it ought to yield to, namely, that, by yielding to which its belief is kept conformable to fact. There is no appeal from the human faculties generally, but there is an appeal from one human faculty to another, from the judging faculty to those which take cognizance of fact, the faculties of sense and consciousness. The legitimacy of this appeal is admitted whenever it is allowed that our judgments ought to be conformable to fact. To say that belief suffices for its own justification is making opinion the test of opinion. It is denying the existence of any outward standard, the conformity of an opinion to which constitutes its truth. We call one mode of forming opinions right and another wrong because the one does and the other does not tend to make the opinion agree with the fact, to make people believe what really is and expect what really will be. Now, a mere disposition to believe, even if supposed instinctive, is no guarantee for the truth of the thing believed. If indeed the belief ever amounted to an irresistible necessity, there would be no use in appealing from it, because there would be no possibility of altering it. But even then the truth of the belief would not follow. It would only follow that mankind were under a permanent necessity of believing what might possibly not be true. In other words, that a case might occur in which our senses or consciousness, if they could be appealed to, might testify one thing and our reason believe another. But in fact there is no such permanent necessity. There is no proposition of which it can be asserted that every human mind must eternally and irrevocably believe it. Many of the propositions of which this is most confidently stated, great numbers of human beings have disbelieved. The things which it has been supposed that nobody could possibly help believing are innumerable, but no two generations would make out the same catalogue of them. One age or nation believes implicitly what to another seems incredible and inconceivable. One individual has not a vestige of a belief which another deems to be absolutely inherent in humanity. There is not one of these supposed instinctive beliefs which is really inevitable. It is in the power of everyone to cultivate habits of thought which make him independent of them. The habit of philosophical analysis, of which it is the surest effect to enable the mind to command instead of being commanded by the laws of the merely passive part of its own nature, by showing to us that things are not necessarily connected in fact because their ideas are connected in our minds, is able to loosen innumerable associations which reign despotically over the undisciplined or early prejudiced mind. And this habit is not without power, even over those associations which the school of which I have been speaking regard as connate and instinctive. I am convinced that anyone accustomed to abstraction and analysis, who will fairly exert his faculties for the purpose, will, when his imagination has once learned to entertain the notion, find no difficulty in conceiving that in some one, for instance, of the many firmaments into which sidereal astronomy now divides the universe, events may succeed one another at random, without any fixed law. Nor can anything in our experience or in our mental nature constitute a sufficient, or indeed any, reason for believing that this is nowhere the case. Were we to suppose, what is perfectly possible to imagine, that the present order of the universe were brought to an end, and that a chaos succeeded in which there was no fixed succession of events, and the past gave no assurance of the future, if a human being were miraculously kept alive to witness this change, he surely would soon cease to believe in any uniformity, the uniformity itself no longer existing. If this be admitted, the belief in uniformity either is not an instinct, or it is an instinct conquerable, like all other instincts, by acquired knowledge. But there is no need to speculate on what might be, when we have positive and certain knowledge of what has been. It is not true, as a matter of fact, that mankind have always believed that all the successions of events were uniform and according to fixed laws. The Greek philosophers, not even excepting Aristotle, recognized chance and spontaneity, tihê, and tor αυτόματον, as among the agents in nature. In other words, they believed that to that extent there was no guarantee that the past had been similar to itself, or that the future would resemble the past. Even now, a full half of the philosophical world, including the very same metaphysicians who contend most for the instinctive character of the belief in uniformity, consider one important class of phenomena, volitions, to be an exception to the uniformity and not governed by a fixed law. Footnote: I am happy to be able to quote the following excellent passage from Mr. Baden-Powell's Essay on the Inductive Philosophy, in confirmation both in regard to history and to doctrine of the statement made in the text. Speaking of, quote, the conviction of the universal and permanent uniformity of nature, Mr. Powell says, pages 98 through 100, we may remark that this idea in its proper extent is by no means one of popular acceptance or natural growth. Just so far as the daily experience of everyone goes, so far indeed he comes to embrace a certain persuasion of this kind, but merely to this limited extent, that what is going on around him at present in his own narrow sphere of observation will go on in like manner in future. The peasant believes that the sun which rose today will rise again tomorrow, that the seed put into the ground will be followed in due time by the harvest this year as it was last year, and the like, but has no notion of such inferences in subjects beyond his immediate observation. And it should be observed that each class of persons, in admitting this belief within the limited range of his own experience, though he doubt or deny it in everything beyond, is, in fact, bearing unconscious testimony to its universal truth. Nor again is it only among the most ignorant that this limitation is put upon truth. There is a very general propensity to believe that everything beyond common experience, or especially ascertained laws of nature, is left to the dominion of chance or fate or arbitrary intervention, and even to object to any attempted explanation by physical causes if conjecturally thrown out for an apparently unaccountable phenomenon. The precise doctrine of the generalization of this idea of the uniformity of nature, so far from being obvious, natural, or intuitive, is utterly beyond the attainment of the many. In all the extent of its universality, it is characteristic of the philosopher. It is clearly the result of philosophic cultivation and training, and by no means the spontaneous offspring of any primary principle naturally inherent in the mind, as some seem to believe. It is no mere vague persuasion taken up without examination as a common prepossession to which we are always accustomed. On the contrary, all common prejudices and associations are against it. It is preeminently an acquired idea. It is not attained without deep study and reflection. The best informed philosopher is the man who most firmly believes it, even in opposition to received notions. Its acceptance depends on the extent and profoundness of his inductive studies. End quote. End footnote. End of section 55. Section 56 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 21 of the Evidence of the Law of Universal Causation, Parts 2 through 4. Part 2. As was observed in a former place, see section 31 of this work, Book 3, Chapter 3, Part 1, the belief we entertain in the universality throughout nature of the law of cause and effect is itself an instance of induction, and by no means one of the earliest which any of us, or which mankind in general, can have made. We arrive at this universal law by generalization from many laws of inferior generality. We should never have had the notion of causation, in the philosophical meaning of the term, as a condition of all phenomena, unless many cases of causation, or, in other words, many partial uniformities of sequence, had previously become familiar. The more obvious of the particular uniformities suggest and give evidence of the general uniformity, and the general uniformity, once established, enables us to prove the remainder of the particular uniformities of which it is made up. As, however, all rigorous processes of induction presuppose the general uniformity, our knowledge of the particular uniformities from which it was first inferred was not, of course, derived from rigorous induction, but from the loose and uncertain mode of induction per enumerationem simplicem, and the law of universal causation being collected from results so obtained cannot itself rest on any better foundation. It would seem, therefore, that induction, per enumerationem simplicem, not only is not necessarily an illicit logical process, but is in reality the only kind of induction possible, since the more elaborate process depends for its validity on a law itself obtained in that inartificial mode. Is there not, then, an inconsistency in contrasting the looseness of one method with the rigidity of another, when that other is indebted to the looser method for its own foundation? The inconsistency, however, is only apparent. Assuredly, if induction by simple enumeration were an invalid process, no process grounded on it could be valid, just as no reliance could be placed on telescopes if we could not trust our eyes. But though a valid process, it is a fallible one, and fallible in very different degrees. If, therefore, we can substitute for the more fallible forms of the process an operation grounded on the same process in a less fallible form, we shall have effected a very material improvement and this is what scientific induction does. A mode of concluding from experience must be pronounced untrustworthy when subsequent experience refuses to confirm it. According to this criterion, induction by simple enumeration, in other words, generalization of an observed fact from the mere absence of any known instance to the contrary, affords in general a precarious and unsafe ground of assurance, for such generalizations are incessantly discovered on further experience to be false. Still, however, it affords some assurance sufficient in many cases for the ordinary guidance of conduct. It would be absurd to say that the generalizations arrived at by mankind in the outset of their experience, such as these: food nourishes, fire burns, water drowns, were unworthy of reliance. Footnote. It deserves remark that these early generalizations did not, like scientific inductions, presuppose causation. What they did presuppose was uniformity in physical facts. But the observers were as ready to presume uniformity in the coexistence of facts as in the sequences. On the other hand, they never thought of assuming that this uniformity was a principle pervading all nature. Their generalizations did not imply that there was uniformity in everything, but only that as much uniformity as existed within their observation existed also beyond it. The induction, fire burns, does not require for its validity that all nature should observe uniform laws, but only that there should be uniformity in one particular class of natural phenomena, the effects of fire on the senses and on combustible substances. And uniformity to this extent was not assumed anterior to the experience, but proved by the experience. The same observed instances which proved the narrower truth proved as much of the wider one as corresponded to it. It is from losing sight of this fact, and considering the law of causation in its full extent as necessarily presupposed in the very earliest generalizations, that persons have been led into the belief that the law of causation is known a priori and is not in itself a conclusion from experience. End footnote. There is a scale of trustworthiness in the results of the original unscientific induction, and on this diversity, as observed in the 4th chapter of the present book, see section 32 of this work, book 3, chapter 4, depend the rules for the improvement of the process. The improvement consists in correcting one of these inartificial generalizations by means of another. As has been already pointed out, this is all that art can do. To test a generalization by showing that it either follows from or conflicts with some stronger induction, some generalization resting on a broader foundation of experience, is the beginning and end of the logic of induction. Part 3. Now the precariousness of the method of simple enumeration is in an inverse ratio to the largeness of the generalization. The process is delusive and insufficient, exactly in proportion as the subject matter of the observation is special and limited in extent. As the sphere widens, this unscientific method becomes less and less liable to mislead, and the most universal class of truths, the law of causation, for instance, and the principles of number and of geometry, are duly and satisfactorily proved by that method alone, nor are they susceptible of any other proof. With respect to the whole class of generalizations of which we have recently treated, the uniformities which depend on causation, the truth of the remark just made follows by obvious inference from the principles laid down in the preceding chapters. When a fact has been observed a certain number of times to be true, and is not in any instance known to be false, if we at once affirm that fact as a universal truth or law of nature, without either testing it by any of the 4 methods of induction, or deducing it from other known laws, we shall in general err grossly. But we are perfectly justified in affirming it as an empirical law, true within certain limits of time, place, and circumstance, provided the number of coincidence be greater than can with any probability be ascribed to chance. The reasons for not extending it beyond those limits is that the fact of its holding true within them may be a consequence of collocations, which cannot be concluded to exist in one place because they exist in another, or may be dependent on the accidental absence of counteracting agencies, which any variation of time or the smallest change of circumstances may possibly bring into play. If we suppose, then, the subject matter of any generalization to be so widely diffused that there is no time, no place, and no combination of circumstances, but must afford an example either of its truth or of its falsity, and if it be never found otherwise than true, its truth cannot be contingent on any collocations, unless such as exist at all times and places. Nor can it be frustrated by any counteracting agencies, unless by such as never actually occur. It is therefore an empirical law coextensive with all human experience, at which point the distinction between empirical laws and laws of nature vanishes, and the proposition takes its place among the most firmly established as well as largest truths accessible to science. Now, the most extensive in its subject matter of all generalizations which experience warrants respecting the sequences and coexistences of phenomena is the law of causation. It stands at the head of all observed uniformities in point of universality, and therefore, if the preceding observations are correct, in point of certainty. And if we consider not what mankind would have been justified in believing in the infancy of their knowledge, but what may rationally be believed in its present more advanced state, we shall find ourselves warranted in considering this fundamental law, though itself obtained by induction from particular laws of causation, as not less certain, but on the contrary more so, than any of those from which it was drawn. It adds to them as much proof as it receives from them, for there is probably no one even of the best established laws of causation which is not sometimes counteracted, and to which therefore apparent exceptions do not present themselves, which would have necessarily and justly shaken the confidence of mankind in the universality of those laws, if inductive processes founded on the universal law had not enabled us to refer those exceptions to the agency of counteracting causes, and thereby reconcile them with the law with which they apparently conflict. Errors, moreover, may have slipped into the statement of any one of the special laws through inattention to some material circumstance, and instead of the true proposition, another may have been enunciated, false as a universal law, though leading, in all cases hitherto observed, to the same result. To the law of causation, on the contrary, we not only do not know of any exception, but the exceptions which limit or apparently invalidate the special laws are so far from contradicting the universal one that they confirm it, since in all cases which are sufficiently open to our observation we are able to trace the difference of result either to the absence of a cause which had been present in ordinary cases, or to the presence of one which had been absent. The law of cause and effect, being thus certain, is capable of imparting its certainty to all other inductive propositions which can be deduced from it, and the narrower inductions may be regarded as receiving their ultimate sanction from that law, since there is no one of them which is not rendered more certain than it was before, when we are able to connect it with that larger induction, and to show that it cannot be denied, consistently with the law that everything which begins to exist has a cause. And hence we are justified in the seeming inconsistency of holding induction by simple enumeration to be good for proving this general truth, the foundation of scientific induction, and yet refusing to rely on it for any of the narrower inductions. I fully admit that if the law of causation were unknown, generalization in the more obvious cases of uniformity in phenomena would nevertheless be possible, and though in all cases more or less precarious, and in some extremely so, would suffice to constitute a certain measure of probability. But what the amount of this probability might be, we are dispensed from estimating, since it never could amount to the degree of assurance which the proposition acquires when, by the application to it of the four methods, the supposition of its falsity is shown to be inconsistent with the law of causation. We are therefore logically entitled, and by the necessities of scientific induction required, to disregard the probabilities derived from the early rude method of generalizing, and to consider no minor generalization as proved except so far as the law of causation confirms it, nor probable except so far as it may reasonably be expected to be so confirmed. Part 4. The assertion that our inductive processes assume the law of causation, while the law of causation is itself a case of induction, is a paradox, only on the old theory of reasoning, which supposes the universal truth or major premise in a ratiocination to be the real proof of the particular truths which are ostensibly inferred from it. According to the doctrine maintained in the present treatise, the major premise is not the proof of the conclusion, but is itself proved, along with the conclusion from the same evidence. See sections 20 and 21 of this work, Book 2, Chapter 3. All men are mortal is not the proof that Lord Palmerston is mortal, but our past experience of mortality authorizes us to infer both the general truth and the particular fact, and the one with exactly the same degree of assurance as the other. The mortality of Lord Palmerston is not an inference from the mortality of all men, but from the experience which proves the mortality of all men, and is a correct inference from experience, if that general truth is so too. This relation between our general beliefs and their particular applications holds equally true in the more comprehensive case which we are now discussing. Any new fact of causation inferred by induction is rightly inferred if no other objection can be made to the inference than can be made to the general truth that every event has a cause. The utmost certainty which can be given to a conclusion arrived at in the way of inference stops at this point. When we have ascertained that the particular conclusion must stand or fall with the general uniformity of the laws of nature, that is liable to no doubt except the doubt whether every event has a cause, we have done all that can be done for it. The strongest assurance we can obtain of any theory respecting the cause of a given phenomenon is that the phenomenon has either that cause or none. The latter supposition might have been an admissible one in a very early period of our study of nature, but we have been able to perceive that in the stage which mankind have now reached, the generalization which gives the law of universal causation has grown into a stronger and better induction, one deserving of greater reliance than any of the subordinate generalizations. We may even, I think, go a step further than this, and regard the certainty of that great induction as not merely comparative, but, for all practical purposes, complete. The considerations which, as I apprehend, give at the present day to the proof of the law of uniformity of succession as true of all phenomena without exception, this character of completeness and conclusiveness, are the following. First, that we now know it directly to be true of far the greatest number of phenomena, that there are none of which we know it not to be true, the utmost that can be said being that of some we cannot positively from direct evidence affirm its truth, while phenomenon after phenomenon, as they become better known to us, are constantly passing from the latter class into the former, and in all cases in which that transition has not yet taken place, the absence of direct proof is accounted for by the rarity or the obscurity of the phenomena, our deficient means of observing them, or the logical difficulties arising from the complication of the circumstances in which they occur. Insomuch that, notwithstanding as rigid a dependence on given conditions as exists in the case of any other phenomenon, it was not likely that we should be better acquainted with those conditions than we are. Besides this first class of considerations, there is a second, which still further corroborates the conclusion. Although there are phenomena the production and changes of which elude all our attempts to reduce them universally to any ascertained law, yet in every such case the phenomenon, or the objects concerned in it, are found in some instances to obey the known laws of nature. The wind, for example, is the type of uncertainty and caprice, yet we find it in some cases obeying with as much constancy as any phenomenon in nature the law of the tendency of fluids to distribute themselves so as to equalize the pressure on every side of each of their particles, as in the case of the trade winds and the monsoons. Lightning might once have been supposed to obey no laws, but since it has been ascertained to be identical with electricity, we know that the very same phenomenon in some of its manifestations is implicitly obedient to the actions of fixed causes. I do not believe that there is now one object or event in all our experience of nature, within the bounds of the solar system at least, which has not either been ascertained by direct observation to follow laws of its own, or been proved to be closely similar to objects and events which, in more familiar manifestations or on a more limited scale, follow strict laws. Our inability to trace the same laws on a larger scale, and in the more recondite instances, being accounted for by the number and complication of the modifying causes, or by their inaccessibility to observation. The progress of experience, therefore, has dissipated the doubt which must have rested on the universality of the law of causation, while there were phenomena which seemed to be sui generis, not subject to the same laws with any other class of phenomena, and not as yet ascertained to have peculiar laws of their own. This great generalization, however, might reasonably have been, as it in fact was, acted on as a probability of the highest order, before there were sufficient grounds for receiving it as a certainty. In matters of evidence, as in all other human things, we neither require nor can attain the absolute. We must hold even our strongest convictions with an opening left in our minds for the reception of facts which contradict them. And only when we have taken this precaution have we earned the right to act upon our convictions with complete confidence when no such contradiction appears. Whatever has been found true in innumerable instances, and never found to be false after due examination in any, we are safe in acting on as universal provisionally, until an undoubted exception appears, provided the nature of the case be such that a real exception could scarcely have escaped notice. When every phenomenon that we ever knew sufficiently well to be able to answer the question had a cause on which it was invariably consequent, it was more rational to suppose that our inability to assign the causes of other phenomena arose from our ignorance, than that they were phenomena which were uncaused, and which happened to be exactly those which we had hitherto had no sufficient opportunity of studying. It must at the same time be remarked that the reasons for this reliance do not hold in circumstances unknown to us and beyond the possible range of our experience. In distant parts of the stellar regions, where the phenomena may be entirely unlike those with which we are acquainted, it would be folly to affirm confidently that this general law prevails, any more than those special ones which we have found to hold universally on our own planet. The uniformity in the succession of events, otherwise called the law of causation, must be received not as a law of the universe, but of that portion of it only which is within the range of our means of sure observation, with a reasonable degree of extension to adjacent cases. To extend it further is to make a supposition without evidence, and to which, in the absence of any ground from experience for estimating its degree of probability, it would be idle to attempt to assign any. Footnote: one of the most rising thinkers of the new generation in France, Monsieur Taine, who has given in the Revue des Deux Mondes the most masterly analysis, at least in one point of view, ever made of the present work, though he rejects on this and similar points of psychology the intuition theory in its ordinary form, nevertheless assigns to the law of causation and to some other of the most universal laws that certainty beyond the bounds of human experience, which I have not been able to accord to them. He does this on the faith of our faculty of abstraction, in which he seems to recognize an independent source of evidence, not indeed disclosing truths not contained in our experience, but affording an assurance which experience cannot give of the universality of those which it does contain. By abstraction, M. Taine seems to think that we are able not merely to analyze that part of nature which we see and exhibit apart from the elements which pervade it, but to distinguish such of them as are elements of the system of nature considered as a whole, not incidents belonging to our limited terrestrial experience. I am not sure that I fully enter into M. Taine's meaning, but I confess I do not see how any mere abstract conception, elicited by our minds from our experience, can be evidence of an objective fact in universal nature beyond what the experience itself bears witness of, or how, in the process of interpreting in general language the testimony of experience, the limitations of the testimony itself can be cast off. Dr. Ward, in an able article from the Dublin Review for October 1871, contends that the uniformity of nature cannot be proved from experience but from transcendental considerations only, and that, consequently, all physical science would be deprived of its basis if such transcendental proof were impossible. When physical science is said to depend on the assumption that the course of nature is invariable, all that is meant is that the conclusions of physical science are not known as absolute truths. The truth of them is conditional on the uniformity of the course of nature, and all that the most conclusive observations and experiments can prove is that the result arrived at will be true if, and as long as, the present laws of nature are valid. But this is all the assurance we require for the guidance of our conduct. Dr. Ward himself does not think that his transcendental proofs make it practically greater, for he believes, as a Catholic, that the course of nature not only has been, but frequently and daily is, suspended by supernatural intervention. But though this conditional conclusiveness of the evidence of experience, which is sufficient for the purposes of life, is all that I was necessarily concerned to prove, I have given reasons for thinking that the uniformity, as itself a part of experience, is sufficiently proved to justify undoubting reliance on it. This Dr. Ward contests for the following reasons. First, supposing it true that there has hitherto been no well authenticated case of a breach in the uniformity of nature, quote, the number of natural agents constantly at work is incalculably large, and the observed cases of uniformity in their action must be immeasurably fewer than 1,000th of the whole. Scientific men, we assume for the moment, have discovered that in a certain proportion of instances, immeasurably fewer than 1,000th of the whole, a certain fact has prevailed. The fact of uniformity, and they have not found a single instance in which that fact does not prevail. Are they justified, we ask, in inferring from these premises that the fact is universal? Surely the question answers itself. Let us make a very grotesque supposition, in which, however, the conclusion would really be tried according to the arguments adduced. In some desert of Africa there is an enormous connected edifice surrounding some vast space, in which dwell certain reasonable beings, who are unable to leave the enclosure. In this edifice are more than 1,000 chambers, which some years ago were entirely locked up, and the keys no one knew where. By constant diligence 25 keys have been found out of the whole number, and the corresponding chambers situated promiscuously throughout the edifice have been opened. Each chamber, when examined, is found to be in the precise shape of a dodecahedron. Are the inhabitants justified on that account in holding with certitude that the remaining 975 chambers are built on the same plan? End quote. Not with perfect certitude, but if the chambers to which the keys have been found are really situated promiscuously, with so high a degree of probability that they would be justified in acting upon the presumption until an exception appeared. Dr. Ward's argument, however, does not touch mine as it stands in the text. My argument is grounded on the fact that the uniformity of the course of nature as a whole is constituted by the uniform sequences of special effects from special natural agencies, that the number of these natural agencies in the part of the universe known to us is not incalculable, nor even extremely great, that we have now reason to think that at least the far greater number of them, if not separately, at least in some of the combinations into which they enter, have been made sufficiently amenable to observation to have enabled us actually to ascertain some of their fixed laws, and that this amount of experience justifies the same degree of assurance that the course of nature is uniform throughout, which we previously had of the uniformity of sequence among the phenomena best known to us. This view of the subject, if correct, destroys the force of Dr. Ward's first argument. His second argument is that many or most persons, both scientific and unscientific, believe that there are well authenticated cases of breach in the uniformity of nature, namely miracles. Neither does this consideration touch what I have said in the text. I admit no other uniformity in the events of nature than the law of causation, and, as I have explained in the chapter of this volume which treats of the grounds of disbelief, a miracle is no exception to that law. In every case of alleged miracle, a new antecedent is affirmed to exist, a counteracting cause, namely, the volition of a supernatural being. To all, therefore, to whom beings with superhuman power over nature are a vera causa, a miracle is a case of the law of universal causation, not a deviation from it. Dr. Ward's last, and as he says, strongest argument, is the familiar one of Reid, Stuart, and their followers, that whatever knowledge experience gives us of the past and present, it gives us none of the future. I confess that I see no force whatever in this argument. Wherein does a future fact differ from a present or a past fact, except in their merely momentary relation to the human beings at present in existence? The answer made by Priestley in his examination of Reid seems to me sufficient, that is, that though we have had no experience of what is future, we have had abundant experience of what was future. The leap in the dark, as Professor Bain calls it, from the past to the future is exactly as much in the dark and no more as the leap from a past which we have personally observed to a past which we have not. I agree with Mr. Bain in the opinion that the resemblance of what we have not experienced to what we have is, by a law of our nature, presumed through the mere energy of the idea, before experience has proved it. This psychological truth, however, is not, as Dr. Ward, when criticizing Mr. Bain, appears to think, inconsistent with the logical truth that experience does prove it. The proof comes after the presumption, and consists in its invariable verification by experience when the experience arrives. The fact, which while it was future could not be observed, having as yet no existence, is always, when it becomes present and can be observed, found conformable to the past. Dr. McCosh maintains, Examination of Mr. J. S. Mill's Philosophy, page 257, that the uniformity of the course of nature is a different thing from the law of causation, and while he allows that the former is only proved by a long continuance of experience, and that it is not inconceivable nor necessarily incredible that there may be worlds in which it does not prevail, he considers the law of causation to be known intuitively. There is, however, no other uniformity in the events of nature than that which arises from the law of causation. So long, therefore, as there remained any doubt that the course of nature was uniform throughout, at least when not modified by the intervention of a new, supernatural cause, a doubt was necessarily implied, not indeed of the reality of causation, but of its universality. If the uniformity of the course of nature has any exceptions, if any events succeed one another without fixed laws, to that extent the law of causation fails. There are events which do not depend on causes. End footnote. End of section 56. Section 57 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 22, of Uniformities of Coexistence Not Dependent on Causation. Part 1. The order of the occurrence of phenomena in time is either successive or simultaneous. The uniformities, therefore, which obtain in their occurrence are either uniformities of succession or of coexistence. Uniformities of succession are all comprehended under the law of causation and its consequences. Every phenomenon has a cause, which it invariably follows, and from this are derived other invariable sequences among the successive stages of the same effect, as well as between the effects resulting from causes which invariably succeed one another. In the same manner with these derivative uniformities of succession, a great variety of uniformities of coexistence also take their rise. Coordinate effects of the same cause naturally coexist with one another. High water at any point on the earth's surface and high water at the point diametrically opposite to it are effects uniformly simultaneous, resulting from the direction in which the combined attractions of the sun and moon act upon the waters of the ocean. An eclipse of the sun to us, and an eclipse of the earth to a spectator situated in the moon, are in like manner phenomena invariably coexistent, and their coexistence can equally be deduced from the laws of their production. It is an obvious question, therefore, whether all the uniformities of coexistence among phenomena may not be accounted for in this manner, and it cannot be doubted that between phenomena which are themselves effects, the coexistences must necessarily depend on the causes of those phenomena. If they are effects immediately or remotely of the same cause, they cannot coexist except by virtue of some laws or properties of that cause. If they are effects of different causes, they cannot coexist unless it be because their causes coexist, and the uniformity of coexistence if such there be, between the effects, proves that those particular causes, within the limits of our observation, have uniformly been coexistent. Part 2. But these same considerations compel us to recognize that there must be one class of coexistences which cannot depend on causation. The coexistences between the ultimate properties of things, those properties which are the causes of all phenomena, but are not themselves caused by any phenomenon, and a cause for which could only be sought by ascending to the origin of all things. Yet, among these ultimate properties, there are not only coexistences, but uniformities of coexistence. General propositions may be, and are, formed, which assert that whenever certain properties are found, certain others are found along with them. We perceive an object, say, for instance, water. We recognize it to be water, of course, by certain of its properties. Having recognized it, we are able to affirm of it innumerable other properties, which we could not do unless it were a general truth, a law or uniformity in nature, that the set of properties by which we identify the substance as water always have those other properties conjoined with them. In a former place, see section 14 of this work, Book 1, Chapter 7, it has been explained in some detail what is meant by the kinds of objects, those classes which differ from one another not by a limited and definite, but by an indefinite and unknown number of distinctions. To this we have now to add that every proposition by which any thing is asserted of a kind affirms a uniformity of coexistence. Since we know nothing of kinds but their properties, the kind, to us, is the set of properties by which it is identified, and which must of course be sufficient to distinguish it from every other kind. Footnote. In some cases, a kind is sufficiently identified by some one remarkable property, but most commonly several are required, each property considered singly being a joint property of that and of other kinds. The colour and brightness of the diamond are common to it with the paste from which false diamonds are made. Its octahedral form is common to it with alum and magnetic iron ore. But the colour and brightness and the form together identify its kind, that is, are a mark to us that it is combustible, that when burned it produces carbonic acid, that it cannot be cut with any known substance, together with many other ascertained properties, and the fact that there exists an indefinite number still unascertained. End footnote. In affirming anything, therefore, of a kind, we are affirming something to be uniformly coexistent with the properties by which the kind is recognized, and that is the sole meaning of the assertion. Among the uniformities of coexistence which exist in nature may hence be numbered all the properties of kinds. The whole of these, however, are not independent of causation, but only a portion of them. Some are ultimate properties, others derivative. Of some no cause can be assigned, but others are manifestly dependent on causes. Thus, pure oxygen gas is a kind, and one of its most unequivocal properties is its gaseous form. This property, however, has for its causes the presence of a certain quantity of latent heat, and if that heat could be taken away, as has been done from so many gases in Faraday's experiments, the gaseous form would doubtless disappear, together with numerous other properties which depend on or are caused by that property. In regard to all substances which are chemical compounds, and which therefore may be regarded as products of the juxtaposition of substances different in kind from themselves, there is considerable reason to presume that the specific properties of the compound are consequent, as effects, on some of the properties of the elements, though little progress has yet been made in tracing any invariable relation between the latter and the former. Still more strongly will a similar presumption exist when the object itself, as in the case of organized beings, is no primeval agent, but an effect which depends on a cause or causes for its very existence. The kinds, therefore, which are called in chemistry simple substances, or elementary natural agents, are the only ones, any of whose properties can with certainty be considered ultimate, and of these the ultimate properties are probably much more numerous than we at present recognize, since every successful instance of the resolution of the properties of their compounds into simpler laws generally leads to the recognition of properties in the elements distinct from any previously known. The resolution of the laws of the heavenly motions established the previously unknown ultimate property of a mutual attraction between all bodies. The resolution, so far as it has yet proceeded, of the laws of crystallization, of chemical composition, electricity, magnetism, and so on, points to various polarities ultimately inherent in the particles of which bodies are composed. The comparative atomic weights of different kinds of bodies were ascertained by resolving into more general laws the uniformities observed in the proportions in which substances combine with one another, and so forth. Thus, although every resolution of a complex uniformity into simpler and more elementary laws has an apparent tendency to diminish the number of the ultimate properties, and really does remove many properties from the list, yet, since the result of this simplifying process is to trace up an ever greater variety of different effects to the same agents, the further we advance in this direction, the greater number of distinct properties we are forced to recognize in one and the same object, the coexistence of which properties must accordingly be ranked among the ultimate generalities of nature. Part 3. There are, therefore, only two kinds of propositions which assert uniformity of coexistence between properties. Either the properties depend on causes, or they do not. If they do, the proposition which affirms them to be coexistent is a derivative law of coexistence between effects, and, until resolved into the laws of causation on which it depends, is an empirical law, and to be tried by the principles of induction to which such laws are amenable. If, on the other hand, the properties do not depend on causes but are ultimate properties, then, if it be true that they invariably coexist, they must all be ultimate properties of one and the same kind, and it is of these only that the coexistences can be classed as a peculiar sort of laws of nature. When we affirm that all crows are black, or that all Negroes have woolly hair, we assert a uniformity of coexistence. We assert that the property of blackness, or of having woolly hair, invariably coexists with the properties which, in common language, or in the scientific classification that we adopt, are taken to constitute the class crow, or the class Negro. Now, supposing blackness to be an ultimate property of black objects, or woolly hair an ultimate property of the animals which possess it. Supposing that these properties are not results of causation, are not connected with antecedent phenomena by any law, then if all crows are black and all Negroes have woolly hair, these must be ultimate properties of the kind crow or Negro, or of some kind which includes them. If, on the contrary, blackness or woolly hair be an effect depending on causes, these general propositions are manifestly empirical laws, and all that has already been said respecting that class of generalizations may be applied without modification to these. Now, we have seen that in the case of all compounds, of all things in short, except the elementary substances and primary powers of nature, the presumption is that the properties do really depend upon causes, and it is impossible in any case whatever to be certain that they do not. We therefore should not be safe in claiming for any generalization respecting the coexistence of properties a degree of certainty to which, if the properties should happen to be the result of causes, it would have no claim. A generalization respecting coexistence, or, in other words, respecting the properties of kinds, may be an ultimate truth, but it may also be merely a derivative one, and since, if so, it is one of those derivative laws which are neither laws of causation nor have been resolved into the laws of causation on which they depend, it can possess no higher degree of evidence than belongs to an empirical law. Part 4. This conclusion will be confirmed by the consideration of one great deficiency which precludes the application to the ultimate uniformities of coexistence of a system of rigorous scientific induction such as the uniformities in the succession of phenomena have been found to admit of. The basis of such a system is wanting. There is no general axiom standing in the same relation to the uniformities of coexistence as the law of causation does to those of succession. The methods of induction applicable to the ascertainment of causes and effects are grounded on the principle that everything which has a beginning must have some cause or other, that among the circumstances which actually existed at the time of its commencement, there is certainly some one combination on which the effect in question is unconditionally consequent, and on the repetition of which it would certainly again recur. But in an inquiry whether some kind, as crow, universally possesses a certain property, as blackness, there is no room for any assumption analogous to this. We have no previous certainty that the property must have something which constantly coexists with it, must have an invariable coexistent, in the same manner as an event must have an invariable antecedent. When we feel pain, we must be in some circumstances under which, if exactly repeated, we should always feel pain. But when we are conscious of blackness, it does not follow that there is something else present of which blackness is a constant accompaniment. There is, therefore, no room for elimination, no method of agreement or difference or of concomitant variations, which is but a modification either of the method of agreement or the method of difference. We cannot conclude that the blackness we see in crows must be an invariable property of crows merely because there is nothing else present of which it can be an invariable property. We therefore inquire into the truth of a proposition like "all crows are black," under the same disadvantage as if, in our inquiries into causation, we were compelled to let in, as one of the possibilities, that the effect may, in that particular instance, have arisen without any cause at all. To overlook this grand distinction was, as it seems to me, the capital error in Bacon's view of inductive philosophy. The principle of elimination, that great logical instrument which he had the immense merit of first bringing into general use, he deemed applicable in the same sense, and in as unqualified a manner, to the investigation of the coexistences as to that of the successions of phenomena. He seems to have thought that as every event has a cause or invariable antecedent, so every property of an object has an invariable coexistent, which he called its form, and the examples he chiefly selected for the application and illustration of his method were inquiries into such forms, attempts to determine in what else all those objects resembled which agreed in some one general property, as hardness or softness, dryness or moistness, heat or coldness. Such inquiries could lead to no result. The objects seldom have any such circumstances in common. They usually agree in the one point inquired into and in nothing else. A great proportion of the properties which, so far as we can conjecture, are the likeliest to be really ultimate, would seem to be inherently properties of many different kinds of things not allied in any other respect. And as for the properties which, being effects of causes, we are able to give some account of, they have generally nothing to do with the ultimate resemblances or diversities in the objects themselves, but depend on some outward circumstances, under the influence of which any objects whatever are capable of manifesting those properties, as is emphatically the case with those favourite subjects of Bacon's scientific inquiries, hotness and coldness, as well as with hardness and softness, solidity and fluidity, and many other conspicuous qualities. In the absence, then, of any universal law of coexistence similar to the universal law of causation which regulates sequence, we are thrown back upon the unscientific induction of the ancients, per enumerationem simplicem ubi non repitur instantia contradictoria. The reason we have for believing that all crows are black is simply that we have seen and heard of many black crows, and never one of any other colour. It remains to be considered how far this evidence can reach, and how we are to measure its strength in any given case. Part 5. It sometimes happens that a mere change in the mode of verbally enunciating a question, though nothing is really added to the meaning expressed, is of itself a considerable step towards its solution. This, I think, happens in the present instance. The degree of certainty of any generalization which rests on no other evidence than the agreement, so far as it goes, of all past observation is but another phrase for the degree of improbability that an exception, if any existed, could have hitherto remained unobserved. The reason for believing that all crows are black is measured by the improbability that crows of any other colour should have existed to the present time without our being aware of it. Let us state the question in this last mode, and consider what is implied in the supposition that there may be crows which are not black, and under what conditions we can be justified in regarding this as incredible. If there really exist crows which are not black, one of two things must be the fact. Either the circumstance of blackness in all crows hitherto observed must be, as it were, an accident, not connected with any distinction of kind, or, if it be a property of kind, the crows which are not black must be a new kind, a kind hitherto overlooked, though coming under the same general description by which crows have hitherto been characterized. The first supposition would be proved true if we were to discover, casually, a white crow among black ones, or if it were found that black crows sometimes turn white. The second would be shown to be the fact if, in Australia or Central Africa, a species or a race of white or grey crows were found to exist. Part 6. The former of these suppositions necessarily implies that the colour is an effect of causation. If blackness in the crows in which it has been observed be not a property of kind, but can be present or absent without any difference generally in the properties of the object, then it is not an ultimate fact in the individuals themselves, but is certainly dependent on a cause. There are, no doubt, many properties which vary from individual to individual of the same kind, even the same infima species, or lowest kind. Some flowers may be either white or red, without differing in any other respect. But these properties are not ultimate. They depend on causes. So far as the properties of a thing belong to its own nature, and do not arise from some cause extrinsic to it, they are always the same in the same kind. Take, for instance, all simple substances and elementary powers, the only things of which we are certain that some at least of their properties are really ultimate. Colour is generally esteemed the most variable of all properties, yet we do not find that sulfur is sometimes yellow and sometimes white, or that it varies in colour at all, except so far as colour is the effect of some extrinsic cause, as of the sort of light thrown upon it, the mechanical arrangement of the particles, as after fusion, and so on. We do not find that iron is sometimes fluid and sometimes solid at the same temperature, gold sometimes malleable and sometimes brittle, that hydrogen will sometimes combine with oxygen and sometimes not, or the like. If from simple substances we pass to any of their definitive compounds, as water, lime, or sulfuric acid, there is the same constancy in their properties. When properties vary from individual to individual, it is either in the case of miscellaneous aggregations, such as atmospheric air or rock composed of heterogeneous substances and not constituting or belonging to any real kind, or it is in the case of organic beings. Footnote. This doctrine, of course, assumes that the allotropic forms of what is chemically the same substance are so many different kinds, and such, in the sense in which the word kind is used in this treatise, they really are. End footnote. In them indeed there is a variability in a high degree. Animals of the same species and race, human beings of the same age, sex, and country, will be most different, for example, in face and figure. But organized beings, from the extreme complication of the laws by which they are regulated, being more eminently modifiable, that is, liable to be influenced by a greater number and variety of causes than any other phenomena whatever, having also themselves had a beginning, and therefore a cause, there is reason to believe that none of their properties are ultimate, but all of them derivative and produced by causation. And the presumption is confirmed by the fact that the properties which vary from one individual to another also generally vary more or less at different times in the same individual, which variation, like any other event, supposes a cause and implies, consequently, that the properties are not independent of causation. If, therefore, blackness be merely accidental in crows and capable of varying while the kind remains the same, its presence or absence is doubtless no ultimate fact, but the effect of some unknown cause. And in that case, the universality of the experience that all crows are black is sufficient proof of a common cause, and establishes the generalization as an empirical law. Since there are innumerable instances in the affirmative, and hitherto none at all in the negative, the causes on which the property depends must exist everywhere, in the limits of the observations which have been made, and the proposition may be received as universal within those limits, and with the allowable degree of extension to adjacent cases. Part 7. If, in the second place, the property, in the instances in which it has been observed, is not an effect of causation, it is a property of kind, and in that case the generalization can only be set aside by the discovery of a new kind of crow. That, however, a peculiar kind not hitherto discovered should exist in nature is a supposition so often realized that it cannot be considered at all improbable. We have nothing to authorize us in attempting to limit the kinds of things which exist in nature. The only unlikelihood would be that a new kind should be discovered in localities which there was previously reason to believe had been thoroughly explored. And even this improbability depends on the degree of conspicuousness of the difference between the newly discovered kind and all others, since new kinds of minerals, plants, and even animals, previously overlooked or confounded with known species, are still continually detected in the most frequented situations. On this second ground, therefore, as well as on the first, the observed uniformity of coexistence can only hold good as an empirical law within the limits not only of actual observation, but of an observation as accurate as the nature of the case required, and hence it is that, as remarked in an early chapter of the present book, we so often give up generalizations of this class at the first summons. If any credible witness stated that he had seen a white crow under circumstances which made it not incredible that it should have escaped notice previously, we should give full credence to the statement. It appears, then, that the uniformities which obtain in the coexistence of phenomena, those which we have reason to consider as ultimate, no less than those which arise from the laws of causes yet undetected, are entitled to reception only as empirical laws, are not to be presumed true except within the limits of time, place, and circumstance in which the observations were made, or except in cases strictly adjacent. Part 8. We have seen in the last chapter that there is a point of generality at which empirical laws become as certain as laws of nature, or rather, at which there is no longer any distinction between empirical laws and laws of nature. As empirical laws approach this point, in other words, as they rise in their degree of generality, they become more certain, their universality may be more strongly relied on. For in the first place, if they are results of causation, which even in the class of uniformities treated of in the present chapter we never can be certain that they are not, the more general they are, the greater is proved to be the space over which the necessary collocations prevail, and within which no causes exist capable of counteracting the unknown causes on which the empirical law depends. To say that any thing is an invariable property of some very limited class of objects is to say that it invariably accompanies some very numerous and complex group of distinguishing properties, which, if causation be at all concerned in the matter, argues a combination of many causes, and therefore a great liability to counteraction, while the comparatively narrow range of the observations renders it impossible to predict to what extent unknown counteracting causes may be distributed throughout nature. But when a generalization has been found to hold good of a very large proportion of all things whatever, it is already proved that nearly all the causes which exist in nature have no power over it, that very few changes in the combination of causes can affect it, since the greater number of possible combinations must have already existed in some one or other of the instances in which it has been found true. If, therefore, any empirical law is a result of causation, the more general it is, the more it may be depended on. And even if it be no result of causation, but an ultimate coexistence, the more general it is, the greater amount of experience it is derived from, and the greater, therefore, is the probability that if exceptions had existed, some would already have presented themselves. For these reasons, it requires much more evidence to establish an exception to one of the more general empirical laws than to the more special ones. We should not have any difficulty in believing that there might be a new kind of crow or a new kind of bird resembling a crow in the properties hitherto considered distinctive of that kind, but it would require stronger proof to convince us of the existence of a kind of crow having properties at variance with any generally recognized universal property of birds, and a still higher degree if the properties conflict with any recognized universal property of animals, and this is conformable to the mode of judgment recommended by the common sense and general practice of mankind, who are more incredulous as to any novelties in nature, according to the degree of generality of the experience which these novelties seem to contradict. Part 9. It is conceivable that the alleged properties might conflict with some recognized universal property of all matter. In that case, their improbability would be at the highest, but would not even then amount to incredibility. There are only two known properties common to all matter. In other words, there is but one known uniformity of coexistence of properties coextensive with all physical nature, namely, that whatever opposes resistance to movement gravitates, or, as Professor Bain expresses it, inertia and gravity are coexistent throughout all matter, and proportionate in their amount. These properties, as he truly says, are not mutually implicated. From neither of them could we, on grounds of causation, presume the other. But for this very reason we are never certain that a kind may not be discovered possessing one of the properties without the other. The hypothetical ether, if it exists, may be such a kind. Our senses cannot recognize in it either resistance or gravity. But if the reality of a resisting medium should eventually be proved, by alteration, for example, in the times of revolution of periodic comets, combined with the evidences afforded by the phenomena of light and heat, it would be rash to conclude from this alone, without other proofs, that it must gravitate. For even the greater generalizations, which embrace comprehensive kinds containing under them a great number and variety of infime species, are only empirical laws, resting on induction by simple enumeration merely, and not on any process of elimination, a process wholly inapplicable to this sort of case. Such generalizations, therefore, ought to be grounded on an examination of all the infime species comprehended in them, and not of a portion only. We cannot conclude, where causation is not concerned, because a proposition is true of a number of things resembling one another only in being animals, that it is therefore true of all animals. If indeed any thing be true of species which differ more from one another than either differs from a third, especially if that third species occupies in most of its known properties a position between the two former, there is some probability that the same thing will also be true of that intermediate species. For it is often, though by no means universally, found that there is a sort of parallelism in the properties of different kinds, and that their degree of unlikeness in one respect bears some proportion to their unlikeness in others. We see this parallelism in the properties of the different metals, in those of sulfur, phosphorus, and carbon, of chlorine, iodine, and bromine, in the natural orders of plants and animals, and so on. But there are innumerable anomalies and exceptions to this sort of conformity, if indeed the conformity itself be anything but an anomaly and an exception in nature. Universal propositions, therefore, respecting the properties of superior kinds, unless grounded on proved or presumed connection by causation, ought not to be hazarded, except after separately examining every known subkind included in the larger kind. And even then such generalizations must be held in readiness to be given up on the occurrence of some new anomaly, which, when the uniformity is not derived from causation, can never, even in the case of the most general of these empirical laws, be considered very improbable. Thus, all the universal propositions which it has been attempted to lay down respecting simple substances, or concerning any of the classes which have been formed among simple substances, and the attempt has been often made, have, with the progress of experience, either faded into inanity or been proved to be erroneous, and each kind of simple substance remains with its own collection of properties apart from the rest, saving a certain parallelism with a few other kinds, the most similar to itself. In organized beings, indeed, there are abundance of propositions ascertained to be universally true of superior genera, to many of which the discovery hereafter of any exceptions must be regarded as extremely improbable. But these, as already observed, are, we have every reason to believe, properties dependent on causation. Footnote: Professor Bain, Logic, 2:13, mentions two empirical laws which he considers to be, with the exception of the law connecting gravity with resistance to motion, quote, the two most widely operating laws as yet discovered whereby two distinct properties are conjoined throughout substances generally. End quote. The first is, quote, a law connecting atomic weight and specific heat by an inverse proportion. For equal weights of the simple bodies, the atomic weight multiplied by a number expressing the specific heat gives a nearly uniform product. The products for all the elements are near the constant number 6. End quote. The other is a law which obtains, quote, between the specific gravity of substances in the gaseous state and the atomic weights. The relationship of the two numbers is in some instances equality, in other instances the one is a multiple of the other. End quote. Neither of these generalizations has the smallest appearance of being an ultimate law. They point unmistakably to higher laws, since the heat necessary to raise to a given temperature the same weight of different substances, called their specific heat, is inversely as their atomic weight, that is, directly as the number of atoms in a given weight of the substance. It follows that a single atom of every substance requires the same amount of heat to raise it to a given temperature. A most interesting and important law, but a law of causation. The other law mentioned by Mr. Bain points to the conclusion that in the gaseous state all substances contain, in the same space, the same number of atoms, which, as the gaseous state suspends all cohesive force, might naturally be expected, though it could not have been positively assumed. This law may also be a result of the mode of action of causes, namely, of molecular motions. The cases in which one of the numbers is not identical with the other, but a multiple of it, may be explained on the nowise unlikely supposition that in our present estimate of the atomic weights of some substances, we mistake 2 or 3 atoms for one, or one for several. End footnote. Uniformities of coexistence, then, not only when they are consequences of laws of succession, but also when they are ultimate truths, must be ranked for the purpose of logic among empirical laws, and are amenable in every respect to the same rules with those unresolved uniformities which are known to be dependent on causation. Footnote. Dr. McCosh, page 324 of his book, considers the laws of the chemical composition of bodies as not coming under the principle of causation, and thinks it an omission in this work not to have provided special canons for their investigation and proof. But every case of chemical composition is, as I have explained, a case of causation. When it is said that water is composed of hydrogen and oxygen, the affirmation is that hydrogen and oxygen, by the action on one another which they exert under certain conditions, generate the properties of water. The canons of induction, therefore, as laid down in this treatise, are applicable to the case. Such special adaptations as the inductive methods may require in their application to chemistry or any other science are a proper subject for anyone who treats of the logic of the special sciences, as Professor Bain has done in the latter part of his work, but they do not appertain to general logic. Dr. McCosh also complains, page 325, that I have given no canons for those sciences in which, quote, the end sought is not the discovery of causes or of composition, but of classes, that is, natural classes. End quote. Such canons could be no other than the principles and rules of natural classification, which I certainly thought that I had expounded at considerable length. But this is far from the only instance in which Dr. McCosh does not appear to be aware of the contents of the books he is criticizing. End footnote. End of section 57. Section 58 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 23 of Approximate Generalizations and Probable Evidence. Part 1. In our inquiries into the nature of the inductive process, we must not confine our notice to such generalizations from experience as profess to be universally true. There is a class of inductive truths avowedly not universal, in which it is not pretended that the predicate is always true of the subject, but the value of which as generalizations is nevertheless extremely great. An important portion of the field of inductive knowledge does not consist of universal truths, but of approximations to such truths, and when a conclusion is said to rest on probable evidence, the premises it is drawn from are usually generalizations of this sort. As every certain inference respecting a particular case implies that there is ground for a general proposition of the form every A is B, so does every probable inference suppose that there is ground for a proposition of the form most A are B, and the degree of probability of the inference in an average case will depend on the proportion between the number of instances existing in nature which accord with the generalization and the number of those which conflict with it. Part 2. Propositions in the form most A are B are of a very different degree of importance in science and in the practice of life. To the scientific inquirer, they are valuable chiefly as materials for and steps toward universal truths. The discovery of these is the proper end of science. Its work is not done if it stops at the proposition that a majority of A are B without circumscribing that majority by some common character fitted to distinguish them from the minority. Independently of the inferior precision of such imperfect generalizations and the inferior assurance with which they can be applied to individual cases, it is plain that, compared with exact generalization, they are almost useless as means of discovering ulterior truths by way of deduction. We may, it is true, by combining the proposition most A are B with a universal proposition every B is C, arrive at the conclusion that most A are C. But when a second proposition of the approximate kind is introduced, or even when there is but one, if that one be the major premise, nothing can, in general, be positively concluded. When the major is most B are D, then even if the minor be every A is B, we cannot infer that most A are D, or with any certainty that even some A are D. Though the majority of the class B have the attribute signified by D, the whole of the subclass A may belong to the minority. Footnote. Mr. De Morgan, in his Formal Logic, makes the just remark that from two such premises as most A are B and most A are C, we may infer with certainty that some B are C. But this is the utmost limit of the conclusions which can be drawn from two approximate generalizations when the precise degree of their approximation to universality is unknown or undefined. End footnote. Though so little use can be made in science of approximate generalizations, except as a stage on the road to something better, for practical guidance they are often all we have to rely on. Even when science has really determined the universal laws of any phenomenon, not only are those laws generally too much encumbered with conditions to be adapted for everyday use, but the cases which present themselves in life are too complicated, and our decisions require to be taken too rapidly to admit of waiting till the existence of a phenomenon can be proved by what have been scientifically ascertained to be universal marks of it. To be indecisive and reluctant to act because we have not evidence of a perfectly conclusive character to act on, is a defect sometimes incident to scientific minds, but which, wherever it exists, renders them unfit for practical emergencies. If we would succeed in action, we must judge by indications which, though they do not generally mislead us, sometimes do, and must make up, as far as possible, for the incomplete conclusiveness of any one indication by obtaining others to corroborate it. The principles of induction applicable to approximate generalizations are therefore a not less important subject of inquiry than the rules for the investigation of universal truths, and might reasonably be expected to detain us almost as long, were it not that these principles are mere corollaries from those which have been already treated of. Part 3. There are two sorts of cases in which we are forced to guide ourselves by generalizations of the imperfect form. Most A are B. The first is, when we have no others, when we have not been able to carry our investigations of the laws of the phenomena any further, as in the following propositions. Most dark-eyed persons have dark hair. Most springs contain mineral substances. Most stratified formations contain fossils. The importance of this class of generalizations is not very great, for, though it frequently happens that we see no reason why that which is true of most individuals of a class is not true of the remainder, nor are able to bring the former under any general description which can distinguish them from the latter, yet if we are willing to be satisfied with propositions of a less degree of generality, and to break down the class A into subclasses, we may generally obtain a collection of propositions exactly true. We do not know why most wood is lighter than water, nor can we point out any general property which discriminates wood that is lighter than water from that which is heavier. But we know exactly what species are the one and what the other, and if we meet with a specimen not conformable to any known species, the only case in which our previous knowledge affords no other guidance than the approximate generalization, we can generally make a specific experiment which is a surer resource. It often happens, however, that the proposition most A are B is not the ultimatum of our scientific attainments, though the knowledge we possess beyond it cannot conveniently be brought to bear upon the particular instance. We may know well enough what circumstances distinguish the portion of A which has the attribute B from the portion which has it not, but may have no means or may not have time to examine whether those characteristic circumstances exist or not in the individual case. This is the situation we are generally in when the inquiry is of the kind called moral, that is, of the kind which has in view to predict human actions. To enable us to affirm anything universally concerning the actions of classes of human beings, the classification must be grounded on the circumstances of their mental culture and habits, which, in an individual case, are seldom exactly known, and classes grounded on these distinctions would never precisely accord with those into which mankind are divided for social purposes. All propositions which can be framed respecting the actions of human beings as ordinarily classified, or as classified according to any kind of outward indications, are merely approximate. We can only say, most persons of a particular age, profession, country, or rank in society have such and such qualities, or most persons, when placed in certain circumstances, act in such and such a way. Not that we do not often know well enough on what causes the qualities depend, or what sort of persons they are who act in that particular way, but we have seldom the means of knowing whether any individual person has been under the influence of those causes, or is a person of that particular sort. we could replace the approximate generalizations by propositions universally true, but these would hardly ever be capable of being applied to our practice. We should be sure of our majors, but we should not be able to get minors to fit. We are forced, therefore, to draw our conclusions from coarser and more fallible indications. Part 4. Proceeding now to consider what is to be regarded as sufficient evidence of an approximate generalization, we can have no difficulty in at once recognizing that, when admissible at all, it is admissible only as an empirical law. Propositions of the form "every A is B" are not necessarily laws of causation, or ultimate uniformities of coexistence. Propositions like "most A are B" cannot be so. Propositions hitherto found true in every observed instance may yet be no necessary consequence of laws of causation, or of ultimate uniformities, and unless they are so, may, for aught we know, be false beyond the limits of actual observation. Still more evidently must this be the case with propositions which are only true in a mere majority of the observed instances. There is some difference, however, in the degree of certainty of the proposition "most A are B," according as that approximate generalization composes the whole of our knowledge of the subject or not. Suppose, first, that the former is the case. We know only that most A are B, not why they are so, nor in what respect those which are differ from those which are not. How, then, did we learn that most A are B? Precisely in the manner in which we should have learned had such happened to be the fact that all A are B. We collected a number of instances sufficient to eliminate chance, and having done so, compared the number of instances in the affirmative with the number in the negative. The result, like other unresolved derivative laws, can be relied on solely within the limits not only of place and time, but also of circumstance, under which its truth has been actually observed. For as we are supposed to be ignorant of the causes which make the proposition true, we cannot tell in what manner any new circumstance might, perhaps, affect it. The proposition "most judges are inaccessible to bribes" would probably be found true of Englishmen, Frenchmen, Germans, North Americans, and so forth. But if on this evidence alone we extend the assertion to Orientals, we should step beyond the limits not only of place but of circumstance within which the fact had been observed, and should let in possibilities of the absence of the determining causes, or the presence of counteracting ones, which might be fatal to the approximate generalization. In the case where the approximate proposition is not the ultimatum of our scientific knowledge, but only the most available form of it for practical guidance, where we know not only that most A have the attribute B, but also the causes of B, or some properties by which the portion of A which has that attribute is distinguished from the portion which has it not, we are rather more favourably situated than in the preceding case. For we have now a double mode of ascertaining whether it be true that most A are B, the direct mode, as before, and an indirect one, that of examining whether the proposition admits of being deduced from the known cause or from any known criterion of B. Let the question, for example, be whether most Scotchmen can read. We may not have observed or received the testimony of others respecting a sufficient number and variety of Scotchmen to ascertain this fact. But when we consider that the cause of being able to read is having been taught it, another mode of determining the question presents itself, namely, by inquiring whether most Scotchmen have been sent to schools where reading is effectually taught. Of these two modes, sometimes one, and sometimes the other, is the more available. In some cases, the frequency of the effect is the more accessible to that extensive and varied observation which is indispensable to the establishment of an empirical law. At other times, the frequency of the causes, or of some collateral indications. It commonly happens that neither is susceptible of so satisfactory an induction as could be desired, and that the grounds on which the conclusion is received are compounded of both. Thus, a person may believe that most Scotchmen can read because, so far as his information extends, most Scotchmen have been sent to school, and most Scotch schools teach reading effectually, and also because most of the Scotchmen whom he has known or heard of could read, though neither of these two sets of observations may by itself fulfill the necessary conditions of extent and variety. Although the approximate generalization may in most cases be indispensable for our guidance, even when we know the cause or some certain mark of the attribute predicated, it needs hardly be observed that we may always replace the uncertain indication by a certain one, in any case in which we can actually recognize the existence of the cause or mark. For example, an assertion is made by a witness, and the question is whether to believe it. If we do not look to any of the individual circumstances of the case, we have nothing to direct us but the approximate generalization that truth is more common than falsehood, or, in other words, that most persons on most occasions speak truth. But if we consider in what circumstances the cases where truth is spoken differ from those in which it is not, we find, for instance, the following: the witness's being an honest person or not, his being an accurate observer or not, his having an interest to serve in the matter or not. Now, not only may we be able to obtain other approximate generalizations respecting the degree of frequency of these various possibilities, but we may know which of them is positively realized in the individual case. That the witness has or has not an interest to serve, we perhaps know directly, and the other 2 points indirectly by means of marks, as, for example, from his conduct on some former occasion, or from his reputation, which, though a very uncertain mark, affords an approximate generalization, as, for instance, most persons who are believed to be honest by those with whom they have had frequent dealings are really so, which approaches nearer to a universal truth than the approximate general proposition with which we set out, that is, most persons on most occasions speak truth. As it seems unnecessary to dwell further on the question of the evidence of approximate generalizations, we shall proceed to a not less important topic, that of the cautions to be observed in arguing from these incompletely universal propositions to particular cases. Part 5. So far as regards the direct application of an approximate generalization to an individual instance, this question presents no difficulty. If the proposition most A are B has been established by a sufficient induction as an empirical law, we may conclude that any particular A is B with a probability proportioned to the preponderance of the number of affirmative instances over the number of exceptions. If it has been found practicable to attain numerical precision in the data, a corresponding degree of precision may be given to the evaluation of the chances of error in the conclusion. If it can be established as an empirical law that 9 out of every 10 A are B, there will be 1 chance in 10 of error in assuming that any A, not individually known to us, is a B. But this of course holds only within the limits of time, place and circumstance embraced in the observations, and therefore cannot be counted on for any subclass or variety of A, or for A in any set of external circumstances, which were not included in the average. It must be added that we can guide ourselves by the proposition 9 out of every 10A are B only in cases of which we know nothing except that they fall within the class A. For if we know of any particular instances, I, not only that it falls under A, but to what species or variety of A it belongs, we shall generally err in applying to I the average struck for the whole genus, from which the average corresponding to that species alone would, in all probability, materially differ. And so, if I, instead of being a particular sort of instance, is an instance known to be under the influence of a particular set of circumstances, the presumption drawn from the numerical proportions in the whole genus would probably, in such a case, only mislead. A general average should only be applied to cases which are neither known nor can be presumed to be other than average cases. Such averages, therefore, are commonly of little use for the practical guidance of any affairs but those which concern large numbers. Tables of the chances of life are useful to insurance officers, but they go a very little way toward informing any one of the chances of his own life or any other life in which he is interested, since almost every life is either better or worse than the average. Such averages can only be considered as supplying the first term in a series of approximations, the subsequent terms proceeding on an appreciation of the circumstances belonging to the particular case. Part 6. From the application of a single approximate generalization to individual cases, we proceed to the application of two or more of them together to the same case. When a judgment applied to an individual instance is grounded on two approximate generalizations taken in conjunction, the propositions may cooperate toward the result in two different ways. In the one, each proposition is separately applicable to the case in hand, and our object in combining them is to give to the conclusion in that particular case the double probability arising from the two propositions separately. This may be called joining two probabilities by the way of addition, and the result is a probability greater than either. The other mode is when only one of the propositions is directly applicable to the case, the second being only applicable to it by virtue of the application of the first. This is joining two probabilities by way of ratiocination, or deduction, the result of which is a less probability than either. The type of the first argument is, most A are B, most C are B. This thing is both an A and a C, therefore it is probably a B. The type of the second is, most A are B, most C are A. This is a C. Therefore it is probably an A, therefore it is probably a B. The first is exemplified when we prove a fact by the testimony of two unconnected witnesses. The second when we adduce only the testimony of one witness that he has heard the thing asserted by another. Or again, in the first mode, it may be argued that the accused committed the crime because he concealed himself and because his clothes were stained with blood. In the second, that he committed it because he washed or destroyed his clothes, which is supposed to render it probable that they were stained with blood. Instead of only two links, as in these instances, we may suppose chains of any length. A chain of the former kind was termed by Bentham a self-corroborative chain of evidence, the second a self-infirmative chain. Footnote: Rationale of Judicial Evidence, Volume 3, page 224. End footnote. When approximate generalizations are joined by way of addition, we may deduce from the theory of probabilities laid down in a former chapter in what manner each of them adds to the probability of a conclusion which has the warrant of them all. If, on an average, 2 of every 3 A's are B's, and 3 of every 4 C's are B's, the probability that something which is both an A and a C is a B will be more than 2 in 3, or than 3 in 4. Of every 12 things which are A's, all except 4 are B's by the supposition. And if the whole 12, and consequently those 4, have the characters of C likewise, 3 of these will be B's on that ground. Therefore, out of 12 which are both A's and C's, 11 are B's. To state the argument in another way, a thing which is both an A and a C, but which is not a B, is found in only one of 3 sections of the class A, and in only one of 4 sections of the class C. But this fourth of C being spread over the whole of A indiscriminately, only 1/3 part of it, or 1/12 of the whole number, belongs to the 3rd section of A. Therefore, a thing which is not a B occurs only once among 12 things which are both A's and C's. The argument would, in the language of the doctrine of chances, be thus expressed. The chance that an A is not a B is 1/3. The chance that a C is not a B is 1/4. Hence, if the thing be both an A and a C, the chance is 1/3 of 1/4, which is equal to 1/12. Footnote. The evaluation of the chances in this statement has been objected to by a mathematical friend. The correct mode, in his opinion, of setting out the possibilities is as follows. If the thing, let us call it T, which is both an A and a C, is a B, something is true which is only true twice in every thrice, and something else which is only true thrice in every 4 times. The first fact being true 8 times in 12, and the second being true 6 times in every 8, and consequently 6 times in those 8, both facts will be true only 6 times in 12. On the other hand, if T, although it is both an A and a C, is not a B, something is true which is only true once in every thrice, and something else which is only true once in every 4 times. The former being true 4 times out of 12, and the latter once in every 4, and therefore once in those 4, both are only true in one case out of 12. So that T is a B 6 times in 12, and T is not a B only once, making the comparative probabilities not 11-1, as I had previously made them, but 6-1. In the last edition, I accepted this reasoning as conclusive. More attentive consideration, however, has convinced me that it contains a fallacy. The objector argues that the fact of A's being a B is true 8 times in 12, and the fact of C's being a B 6 times in 8, and consequently 6 times in those 8, both facts therefore are true only 6 times in every 12. That is, he concludes that because among A's taken indiscriminately, only 8 out of 12 are B's, and the remaining 4 are not, it must equally hold that 4 out of 12 are not B's, when the 12 are taken from the select portion of A's which are also C's. And by this assumption he arrives at the strange result that there are fewer B's among things which are both A's and C's than there are among either A's or C's taken indiscriminately, so that a thing which has both chances of being a B is less likely to be so than if it had only the one chance or only the other. The objector, as has been acutely remarked by another correspondent, applies to the problem under consideration a mode of calculation only suited to the reverse problem. Had the question been, if 2 of every 3 B's are A's and 3 out of every 4 B's are C's, how many B's will be both A's and C's? His reasoning would have been correct, for the B's that are both A's and C's must be fewer than either the B's that are A's or the B's that are C's, and to find their number we must abate either of these numbers in the ratio due to the other. But when the problem is to find not how many B's are both A's and C's, but how many things that are both A's and C's are B's, it is evident that among these the proportion of B's must be not less but greater than among things which are only A, or among things which are only B. The true theory of the chances is best found by going back to the scientific grounds on which the proportions rest. The degree of frequency of a coincidence depends on, and is a measure of, the frequency combined with the efficacy of the causes in operation that are favourable to it. If out of every 12 A's taken indiscriminately, 8 are B's and 4 are not, it is implied that there are causes operating on A which tend to make it a B, and that these causes are sufficiently constant and sufficiently powerful to succeed in 8 out of 12 cases, but fail in the remaining 4. So if of 12 C's, 9 are B's and 3 are not, there must be causes of the same tendency operating on C, which succeed in 9 cases and fail in 3. Now suppose 12 cases which are both A's and C's. The whole 12 are now under the operation of both sets of causes. One set is sufficient to prevail in 8 of the 12 cases, the other in 9. The analysis of the cases shows that 6 of the 12 will be B's through the operation of both sets of causes, 2 more in virtue of the causes operating on A, and 3 more through those operating on C, and that there will be only one case in which all the causes will be inoperative. The total number, therefore, which are B's will be 11 in 12, and the evaluation in the text is correct. End footnote. In this computation, it is of course supposed that the probabilities arising from A and C are independent of each other. There must not be any such connection between A and C, that when a thing belongs to the one class, it will therefore belong to the other, or even have a greater chance of doing so. Otherwise, the not B's, which are C's, may be, most, or even all of them, identical with the not B's, which are A's, in which last case the probability arising from A and C together will be no greater than that arising from A alone. When approximate generalizations are joined together in the other mode, that of deduction, the degree of probability of the inference, instead of increasing, diminishes at each step. From 2 such premises as most A are B, most B are C, we cannot with certainty conclude that even a single A is C. For the whole of the portion of A which in any way falls under B may perhaps be comprised in the exceptional part of it. Still, the 2 propositions in question afford an appreciable probability that any given A is C, provided the average on which the second proposition is grounded was taken fairly with reference to the first, provided the proposition most B are C was arrived at in a manner leaving no suspicion that the probability arising from it is otherwise than fairly distributed over the section of B which belongs to A. For though the instances which are A may be all in the minority, they may also be all in the majority, and the one possibility is to be set against the other. On the whole, the probability arising from the 2 propositions taken together will be correctly measured by the probability arising from the one abated in the ratio of that arising from the other. If 9 out of 10 Swedes have light hair, and 8 out of 9 inhabitants of Stockholm are Swedes, the probability arising from these two propositions that any given inhabitant of Stockholm is light-haired will amount to 8 in 10, though it is rigorously possible that the whole Swedish population of Stockholm might belong to that 10th section of the people of Sweden who are an exception to the rest. If the premises are known to be true not of a bare majority, but of nearly the whole of their respective subjects, we may go on joining one such proposition to another for several steps before we reach a conclusion not presumably true even of a majority. The error of the conclusion will amount to the aggregate of the errors of all the premises. Let the proposition most A are B be true of 9 in 10. Most B are C of 8 in 9. Then not only will 1A in 10 not be C, because not B, but even of the 9/10ths which are B, only 8/9ths will be C. That is, the cases of A which are C will be only 8/9ths of 9/10ths, or 4/5ths. Let us now add most C are D, and suppose this to be true of 7 cases out of 8, the proportion of A which is D will be only 7/8ths of 8/9ths of 9/10ths, or 7/10ths. Thus the probability progressively dwindles. The experience, however, on which our approximate generalizations are grounded has so rarely been subjected to or admits of accurate numerical estimation that we cannot in general apply any measurement to the diminution of probability which takes place at each elation, but must be content with remembering that it does diminish at every step, and that unless the premises approach very nearly indeed to being universally true, the conclusion, after a very few steps, is worth nothing. A hearsay of a hearsay, or an argument from presumptive evidence depending not on immediate marks but on marks of marks, is worthless at a very few removes from the first stage. Part 7. There are, however, 2 cases in which reasonings depend on approximate generalizations, may be carried to any length we please with as much assurance, and are as strictly scientific as if they were composed of universal laws of nature. But these cases are exceptions of the sort which are currently said to prove the rule. The approximate generalizations are as suitable in the cases in question for purposes of ratiocination as if they were complete generalizations, because they are capable of being transformed into complete generalizations exactly equivalent. First, if the approximate generalization is of the class in which our reason for stopping at the approximation is not the impossibility, but only the inconvenience of going further, if we are cognizant of the character which distinguishes the cases that accord with the generalization from those which are exceptions to it, we may then substitute for the approximate proposition a universal proposition with a proviso. The proposition, most persons who have uncontrolled power employ it ill, is a generalization of this class, and may be transformed into the following. All persons who have uncontrolled power employ it ill, provided they are not persons of unusual strength of judgment and rectitude of purpose. The proposition, carrying the hypothesis or proviso with it, may then be dealt with no longer as an approximate, but as a universal proposition, and to whatever number of steps the reasoning may reach, the hypothesis being carried forward to the conclusion will exactly indicate how far that conclusion is from being applicable universally. If, in the course of the argument, other approximate generalizations are introduced, each of them being in like manner expressed as a universal proposition with a condition annexed, the sum of all the conditions will appear at the end as the sum of all the errors which affect the conclusion. Thus, to the proposition last cited, let us add the following. All absolute monarchs have uncontrolled power, unless their position is such that they need the active support of their subjects, as was the case with Queen Elizabeth, Frederick of Prussia, and others. Combining these two propositions, we can deduce from them a universal conclusion which will be subject to both the hypothesis in the premises. All absolute monarchs employ their power ill unless their position makes them need the active support of their subjects, or unless they are persons of unusual strength of judgment and rectitude of purpose. It is of no consequence how rapidly the errors in our premises accumulate, if we are able in this manner to record each error, and keep an account of the aggregate as it swells up. Secondly, there is a case in which approximate propositions, even without our taking note of the conditions under which they are not true of individual cases, are yet, for the purposes of science, universal ones, namely, in the inquiries which relate to the properties not of individuals but of multitudes. The principal of these is the science of politics, or of human society. This science is principally concerned with the actions not of solitary individuals but of masses, with the fortunes not of single persons but of communities. For the statesman, therefore, it is generally enough to know that most persons act or are acted upon in a particular way, since his speculations and his practical arrangements refer almost exclusively to cases in which the whole community, or some large portion of it, is acted upon at once, and in which, therefore, what is done or felt by most persons determines the result produced by or upon the body at large. He can get on well enough with approximate generalizations on human nature, since what is true approximately of all individuals is true absolutely of all masses. And even when the operations of individual men have a part to play in his deductions, as when he is reasoning of kings or other single rulers, still, as he is providing for indefinite duration, involving an indefinite succession of such individuals, he must in general both reason and act as if what is true of most persons were true of all. The two kinds of considerations above adduced are a sufficient refutation of the popular error that speculations on society and government, as resting on merely probable evidence, must be inferior in certainty and scientific accuracy to the conclusions of what are called the exact sciences, and less to be relied on in practice. There are reasons enough why the moral sciences must remain inferior to at least the more perfect of the physical, why the laws of their more complicated phenomena cannot be so completely deciphered, nor the phenomena predicted with the same degree of assurance. But though we cannot attain to so many truths, there is no reason that those we can attain should deserve less reliance, or have less of a scientific character. Of this topic, however, I shall treat more systematically in the concluding book, to which place any further consideration of it must be deferred. End of section 58. Section 59 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 24 of the Remaining Laws of Nature, Parts 1 through 5. Part 1. In the first book we found that all the assertions which can be conveyed by language express some one or more of 5 different things: existence, order in place, order in time, causation, and resemblance. Footnote. See sections 11 and 12 of this work, Book 1, Chapter 5. End footnote. Of these, Causation, in our view of the subject, not being fundamentally different from order in time, the 5 species of possible assertions are reduced to 4. The propositions which affirm order in time in either of its 2 modes, coexistence and succession, have formed thus far the subject of the present book, and we have now concluded the exposition so far as it falls within the limits assigned to this work, of the nature of the evidence on which these propositions rest, and the processes of investigation by which they are ascertained and proved. There remain 3 classes of facts: existence, order in place, and resemblance, in regard to which the same questions are now to be resolved. Regarding the first of these, very little needs be said. Existence in general is a subject not for our science, but for metaphysics. To determine what things can be recognized as really existing, independently of our own sensible or other impressions, and in what meaning the term is, in that case, predicated of them, belongs to the consideration of things in themselves, from which, throughout this work, we have as much as possible kept aloof. Existence, so far as logic is concerned about it, has reference only to phenomena, to actual or possible states of external or internal consciousness, in ourselves or others. Feelings of sensitive beings, or possibilities of having such feelings, are the only things the existence of which can be a subject of logical induction, because the only things of which the existence in individual cases can be a subject of experience. It is true that a thing is said by us to exist, even when it is absent, and therefore is not and cannot be perceived. But even then its existence is to us only another word for our conviction that we should perceive it on a certain supposition, namely, if we were in the needful circumstance of time and place, and endowed with the needful perfection of organs. My belief that the Emperor of China exists is simply my belief that if I were transported to the Imperial Palace or some other locality in Peking, I should see him. My belief that Julius Caesar existed is my belief that I should have seen him if I had been present in the field of Pharsalia or in the Senate House at Rome. When I believe that stars exist beyond the utmost range of my vision, though assisted by the most powerful telescopes yet invented, my belief, philosophically expressed, is that with still better telescopes, if such existed, I could see them, or that they may be perceived by beings less remote from them in space, or whose capacities of perception are superior to mine. The existence, therefore, of a phenomenon is but another word for its being perceived, or for the inferred possibility of perceiving it. When the phenomenon is within the range of present observation, by present observation we assure ourselves of its existence. When it is beyond that range, and is therefore said to be absent, we infer its existence from marks or evidences. But what can these evidences be? Other phenomena, ascertained by induction to be connected with the given phenomenon, either in the way of succession or of coexistence. The simple existence, therefore, of an individual phenomenon, when not directly perceived, is inferred from some inductive law of succession or coexistence, and is consequently not amenable to any peculiar inductive principles. We prove the existence of a thing by proving that it is connected by succession or coexistence with some known thing. With respect to general propositions of this class, that is, which affirm the bare fact of existence, they have a peculiarity which renders the logical treatment of them a very easy matter. They are generalizations which are sufficiently proved by a single instance. That ghosts or unicorns or sea serpents exist would be fully established if it could be ascertained positively that such things had been even once seen. Whatever has once happened is capable of happening again. The only question relates to the conditions under which it happens. So far, therefore, as relates to simple existence, the inductive logic has no knots to untie, and we may proceed to the remaining two of the great classes into which facts have been divided: resemblance and order in place. Part 2. Resemblance and its opposite, except in the case in which they assume the names of equality and inequality, are seldom regarded as subjects of science. They are supposed to be perceived by simple apprehension, by merely applying our senses or directing our attention to the two objects at once, or in immediate succession. And this simultaneous or virtually simultaneous application of our faculties to the two things which are to be compared does necessarily constitute the ultimate appeal, wherever such application is practicable. But in most cases it is not practicable. The objects cannot be brought so close together that the feeling of their resemblance, at least a complete feeling of it, directly arises in the mind. We can only compare each of them with some third object capable of being transported from one to the other, and besides, even when the objects can be brought into immediate juxtaposition, their resemblance or difference is but imperfectly known to us, unless we have compared them minutely, part by part. Until this has been done, things in reality very dissimilar often appear undistinguishably alike. Two lines of very unequal length will appear about equal when lying in different directions, but place them parallel with their farther extremities even, and if we look at the nearer extremities, their inequality becomes a matter of direct perception. To ascertain whether and in what two phenomena resemble or differ is not always, therefore, so easy a thing as it might at first appear. When the two cannot be brought into juxtaposition, or not so that the observer is able to compare their several parts in detail, he must employ the indirect means of reasoning and general propositions. When we cannot bring two straight lines together to determine whether they are equal, we do it by the physical aid of a foot rule, applied first to one and then to the other, and the logical aid of the general proposition or formula, "Things which are equal to the same thing are equal to one another." The comparison of two things through the intervention of a third thing, when their direct comparison is impossible, is the appropriate scientific process for ascertaining resemblance and dissimilarities, and is the sum total of what logic has to teach us on the subject. An undue extension of this remark induced Locke to consider reasoning itself as nothing but the comparison of two ideas through the medium of a third, and knowledge as the perception of the agreement or disagreement of two ideas, doctrines which the Condillac school blindly adopted without the qualifications and distinctions with which they were studiously guarded by their illustrious author. Where, indeed, the agreement or disagreement, otherwise called resemblance or dissimilarity, of any two things is the very matter to be determined, as is the case particularly in the sciences of quantity and extension. There, the process by which a solution, if not attainable by direct perception, must be indirectly sought, consists in comparing these two things through the medium of a third. But this is far from being true of all inquiries. The knowledge that bodies fall to the ground is not a perception of agreement or disagreement, but of a series of physical occurrences, a succession of sensations. Locke's definitions of knowledge and of reasoning required to be limited to our knowledge of, and reasoning about, resemblances. Nor, even when thus restricted, are the propositions strictly correct, since the comparison is not made, as he represents, between the ideas of the two phenomena, but between the phenomena themselves. This mistake has been pointed out in an earlier part of our inquiry, and we traced it to an imperfect conception of what takes place in mathematics, where very often the comparison is really made between the ideas without any appeal to the outward senses. Only, however, because in mathematics a comparison of the ideas is strictly equivalent to a comparison of the phenomena themselves. Footnote. See sections 11 and 12 of this work, Book 1, Chapter 5, Part 1 and Part 5. End footnote. Where, as in the case of numbers, lines, and figures, our idea of an object is a complete picture of the object, so far as respects the matter in hand, we can, of course, learn from the picture whatever could be learned from the object itself, by mere contemplation of it as it exists at the particular instant when the picture is taken. No mere contemplation of gunpowder would ever teach us that a spark would make it explode, nor, consequently, would the contemplation of the idea of gunpowder do so. But the mere contemplation of a straight line shows that it cannot enclose a space. Accordingly, the contemplation of the idea of it will show the same. What takes place in mathematics is thus no argument that the comparison is between the ideas only. It is always, either indirectly or directly, a comparison of the phenomena. In cases in which we cannot bring the phenomena to the test of direct inspection at all, or not in a manner sufficiently precise, but must judge of their resemblance by inference from other resemblances or dissimilarities more accessible to observation, we of course require, as in all cases of ratiocination, generalizations or formulae applicable to the subject. We must reason from laws of nature, from the uniformities which are observable in the fact of likeness or unlikeness. Part 3. Of these laws or uniformities, the most comprehensive are those supplied by mathematics, the axioms relating to equality, inequality, and proportionality, and the various theorems thereon founded. And these are the only laws of resemblance which require to be, or which can be, treated apart. It is true there are innumerable other theorems which affirm resemblances amongst phenomena, as that the angle of the reflection of light is equal to its angle of incidence, equality being merely exact resemblance in magnitude. Again, that the heavenly bodies describe equal areas in equal times, and that their periods of revolution are proportional, another species of resemblance, to the sesquiplicate powers of their distance from the centre of force. These and similar propositions affirm resemblances of the same nature with those asserted in the theorems of mathematics. But the distinction is that the propositions of mathematics are true of all phenomena whatever, or at least without distinction of origin, while the truths in question are affirmed only of special phenomena, which originate in a certain way, and the equalities, proportionalities, or other resemblances which exist between such phenomena must necessarily be either derived from or identical with the law of their origin, the law of causation on which they depend. The equality of the areas described in equal times by the planets is derived from the laws of the causes, and until its derivation was shown, it was an empirical law. The equality of the angles of reflection and incidence is identical with the law of the cause, for the cause is the incidence of a ray of light upon a reflecting surface, and the equality in question is the very law according to which that cause produces its effects. This class, therefore, of the uniformities of resemblance between phenomena are inseparable, in fact and in thought, from the laws of the production of those phenomena, and the principles of induction applicable to them are no other than those of which we have treated in the preceding chapters of this book. It is otherwise with the truths of mathematics. The laws of equality and inequality between spaces or between numbers have no connection with laws of causation. That the angle of reflection is equal to the angle of incidence is a statement of the mode of action of a particular cause, but that when two straight lines intersect each other, the opposite angles are equal, is true of all such lines and angles by whatever cause produced. That the squares of the periodic times of the planets are proportional to the cubes of their distances from the Sun is a uniformity derived from the laws of the causes, or forces, which produce the planetary motions. But that the square of any number is 4 times the square of half the number is true independently of any cause. The only laws of resemblance, therefore, which we are called upon to consider independently of causation, belong to the province of mathematics. Part 4. The same thing is evident with respect to the only one remaining of our 5 categories, order in place. The order in place of the effects of a cause is, like everything else belonging to the effects, a consequence of the laws of that cause. The order in place, or, as we have termed it, the collocation of the primeval causes, is, as well as their resemblance, in each instance an ultimate fact, in which no laws or uniformities are traceable. The only remaining general propositions respecting order in place, and the only ones which have nothing to do with causation, are some of the truths of geometry, laws through which we are able from the order in place of certain points, lines, or spaces to infer the order in place of others which are connected with the former in some known mode, quite independently of the particular nature of those points, lines, or spaces in any other respect than position or magnitude, as well as independently of the physical cause from which in any particular case they happen to derive their origin. It thus appears that mathematics is the only department of science into the methods of which it still remains to inquire, and there is the less necessity that this inquiry should occupy us long, as we have already, in the 2nd book, made considerable progress in it. We there remarked that the directly inductive truths of mathematics are few in number, consisting of the axioms, together with certain propositions concerning existence, tacitly involved in most of the so-called definitions, and we gave what appeared conclusive reasons for affirming that these original premises, from which the remaining truths of the science are deduced, are, notwithstanding all appearances to the contrary, results of observation and experience, founded, in short, on the evidence of the senses. That things equal to the same thing are equal to one another, and that two straight lines which have once intersected one another continue to diverge, are inductive truths, resting indeed, like the law of universal causation, only on induction per enumerationem simplicem, on the fact that they have been perpetually perceived to be true and never once found to be false. But as we have seen in a recent chapter that this evidence, in the case of a law so completely universal as the law of causation, amounts to the fullest proof, so is this even more evidently true of the general propositions to which we are now adverting, because, as a perception of their truth in any individual case whatever requires only the simple act of looking at the objects in a proper position, there never could have been in their case what for a long period there were in the case of the law of causation, instances which were apparently, though not really, exceptions to them. Their infallible truth was recognized from the very dawn of speculation, and as their extreme familiarity made it impossible for the mind to conceive the objects under any other law, they were, and still are, generally considered as truths recognized by their own evidence or by instinct. Part 5. There is something which seems to require explanation in the fact that the immense multitude of truths, a multitude still as far from being exhausted as ever, comprised in the mathematical sciences, can be elicited from so small a number of elementary laws. One sees not, at first, how it is that there can be room for such an infinite variety of true propositions on subjects apparently so limited. To begin with the science of number, the elementary or ultimate truths of this science are the common axioms concerning equality, namely, things which are equal to the same thing are equal to one another, and equals added to equals make equal sums. No other axioms are required, together with the definitions of the various numbers. Footnote: the axiom equals subtracted from equals leave equal differences may be demonstrated from the two axioms in the text. If upper A equals lower A and upper B equals lower B, upper A minus B equals lower A minus B. For if not, let upper A minus B equal lower A minus lower B plus lower C. Then, since upper B equals lower B, adding equals to equals, upper A equals lower A plus lower C. But upper A equals lower A. Therefore, lower A equals lower A plus lower C, which is impossible. This proposition having been demonstrated, we may, by means of it, demonstrate the following. Quote, if equals be added to unequals, the sums are unequal. End quote. If upper A equals lower A and upper B not equal lower B, upper A plus upper B is not equal lower A plus lower B. For suppose it to be so. Then, since upper A equals lower A and upper A plus upper B equals lower A plus lower B, subtracting equals from equals, upper B equals lower B, which is contrary to the hypothesis. So again, it may be proved that two things, one of which is equal and the other unequal to a third thing, are unequal to one another. If upper A equals lower A and upper A not equal upper B, neither is lower A equal upper B. For suppose it to be equal, then since upper A equals lower A and lower A equals B, and since things equal to the same thing are equal to one another, upper A equals upper B, which is contrary to the hypothesis. End footnote. Like other so-called definitions, these are composed of two things, the explanation of a name and the assertion of a fact, of which the latter alone can form a first principle or premise of a science. The fact asserted in the definition of a number is a physical fact. Each of the numbers 2, 3, 4, and so on denotes physical phenomena and connotes a physical property of those phenomena. 2, for instance, denotes all pairs of things, and 12 all dozens of things, connoting what makes them pairs or dozens, and that which makes them so is something physical, since it cannot be denied that 2 apples are physically distinguishable from 3 apples, 2 horses from 1 horse, and so forth, that they are a different visible and tangible phenomenon. I am not undertaking to say what the difference is. It is enough that there is a difference of which the senses can take cognizance. And although 102 horses are not so easily distinguished from 103 as 2 horses are from 3, though in most positions the senses do not perceive any difference, yet they may be so placed that a difference will be perceptible, or else we should never have distinguished them and given them different names. Weight is confessedly a physical property of things, yet small differences between great weights are as imperceptible to the senses in most situations as small differences between great numbers, and are only put in evidence by placing the two objects in a peculiar position, namely, in the opposite scales of a delicate balance. What then is that which is connoted by a name of number? Of course, some property belonging to the agglomeration of things which we call by the name, and that property is the characteristic manner in which the agglomeration is made up of, and may be separated into, parts. I will endeavour to make this more intelligible by a few explanations. When we call a collection of objects 2, 3, or 4, they are not 2, 3, or 4 in the abstract. They are 2, 3, or 4 things of some particular kind: pebbles, horses, inches, pounds weight. What the name of the number connotes is the manner in which single objects of the given kind must be put together in order to produce that particular aggregate. If the aggregate be of pebbles, and we call it 2, the name implies that to compose the aggregate, one pebble must be joined to one pebble. If we call it 3, 1 and 1 pebble must be brought together to produce it, or else one pebble must be joined to an aggregate of the kind called 2 already existing. The aggregate which we call 4 has a still greater number of characteristic modes of formation. 1 and 1 and 1 and 1 pebble may be brought together, or two aggregates of the kind called 2 may be united, or one pebble may be added to an aggregate of the kind called 3. Every succeeding number in the ascending series may be formed by the junction of smaller numbers in a progressively greater variety of ways. Even limiting the parts to 2, the number may be formed, and consequently may be divided in as many different ways as there are numbers smaller than itself, and if we admit of 3s, 4s, and so on, in a still greater variety. Other modes of arriving at the same aggregate present themselves, not by the union of smaller, but by the dismemberment of larger aggregates. Thus, 3 pebbles may be formed by taking away 1 pebble from an aggregate of 4, 2 pebbles by an equal division of a similar aggregate, and so on. Every arithmetical proposition, every statement of the result of an arithmetic operation, is a statement of one of the modes of formation of a given number. It affirms that a certain aggregate might have been formed by putting together certain other aggregates, or by withdrawing certain portions of some aggregate, and that, by consequence, we might reproduce those aggregates from it by reversing the process. Thus, when we say that the cube of 12 is 1728, what we affirm is this: that if, having a sufficient number of pebbles or of any other objects, we put them together into the particular sort of parcels or aggregates called 12s, and put together these 12s again into a similar collection, and finally make up 12 of these largest parcels, the aggregate thus formed will be such a one as we call 1728, namely, that which, to take the most familiar of its modes of formation, may be made by joining the parcel called 1,000 pebbles, the parcel called 700 pebbles, the parcel called 20 pebbles, and the parcel called 8 pebbles. The converse proposition that the cube root of 1728 is 12 asserts that this large aggregate may again be decomposed into the 12 12s of pebbles, which it consists of. The modes of formation of any number are innumerable, but when we know one mode of formation of each, all the rest may be determined deductively. If we know that lower a is formed from lower b and lower c, lower b from lower a and lower e, lower c from lower d and lower f, and so forth, until we have included all the numbers of any scale we choose to select, taking care that for each number the mode of formation be really a distinct one, not bringing us round again to the former numbers, but introducing a new number, we have a set of propositions from which we may reason to all the other modes of formation of those numbers from one another. Having established a chain of inductive truths connecting together all the numbers of the scale, we can ascertain the formation of any one of those numbers from any other by merely travelling from one to the other along the chain. Suppose that we know only the following modes of formation. 6 equals 4 plus 2, 4 equals 7 minus 3, 7 equals 5 plus 2, 5 equals 9 minus 4. We could determine how 6 may be formed from 9, for 6 equals 4 plus 2 equals 7 minus 3 plus 2 equals 5 plus 2 minus 3 plus 2 equals 9 minus 4 plus 2 minus 3 plus 2. It may therefore be formed by taking away 4 and 3 and adding 2 and 2. If we know besides that 2 plus 2 equals 4, we obtain 6 from 9 in a simpler mode by merely taking away 3. It is sufficient, therefore, to select one of the various modes of formation of each number as a means of ascertaining all the rest. And since things which are uniform and therefore simple are most easily received and retained by the understanding, there is an obvious advantage in selecting a mode of formation which shall be alike for all, in fixing the connotation of names of number on one uniform principle. The mode in which our existing numerical nomenclature is contrived possesses this advantage, with the additional one that it happily conveys to the mind two of the modes of formation of every number. Each number is considered as formed by the addition of a unit to the number next below it in magnitude, and this mode of formation is conveyed by the place which it occupies in the series. And each is also considered as formed by the addition of a number of units less than 10, and a number of aggregates each equal to one of the successive powers of 10. And this mode of its formation is expressed by its spoken name and by its numerical character. What renders arithmetic the type of a deductive science is the fortunate applicability to it of a law so comprehensive as the sums of equals are equals, or, to express the same principle in less familiar but more characteristic language, whatever is made up of parts is made up of the parts of those parts. This truth, obvious to the senses in all cases which can be fairly referred to their decision, and so general as to be coextensive with nature itself, being true of all sorts of phenomena, for all admit of being numbered, must be considered an inductive truth, or law of nature, of the highest order, and every arithmetical operation is an application of this law, or of other laws capable of being deduced from it. This is our warrant for all calculations. We believe that 5 and 2 are equal to 7, on the evidence of this inductive law, combined with the definition of those numbers. We arrive at that conclusion, as all know who remember how they first learned it, by adding a single unit at a time. 5 plus 1 equals 6. Therefore, 5 plus 1 plus 1 equals 6 plus 1 equals 7. And again, 2 equals 1 plus 1. Therefore, 5 plus 2 equals 5 plus 1 plus 1 equals 7. End of section 59. Section 60 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 24 of the Remaining Laws of Nature, Parts 6 through 9. Part 6. Innumerable as are the true propositions which can be formed concerning particular numbers, no adequate conception could be gained from these alone of the extent of the truths composing the science of number. Such propositions as we have spoken of are the least general of all numerical truths. It is true that even these are coextensive with all nature. The properties of the number 4 are true of all objects that are divisible into 4 equal parts, and all objects are either actually or ideally so divisible. But the propositions which compose the science of algebra are true not of a particular number, but of all numbers, not of all things under the condition of being divided in a particular way, but of all things under the condition of being divided in any way, of being designated by a number at all. Since it is impossible for different numbers to have any of their modes of formation completely in common, it is a kind of paradox to say that all propositions which can be made concerning numbers relate to their modes of formation from other numbers, and yet that there are propositions which are true of all numbers. But this very paradox leads to the real principle of generalization concerning the properties of numbers. Two different numbers cannot be formed in the same manner from the same numbers, but they may be formed in the same manner from different numbers, as 9 is formed from 3 by multiplying it into itself, and 16 is formed from 4 by the same process. Thus there arises a classification of modes of formation, or, in the language commonly used by mathematicians, a classification of functions. Any number considered as formed from any other number is called a function of it, and there are as many kinds of functions as there are modes of formation. The simple functions are by no means numerous, most functions being formed by the combination of several of the operations which form simple functions, or by successive repetitions of some one of those operations. The simple functions of any number x are all reducible to the following forms: x plus a, x minus a multiplied by x divided by a, logarithm of x to the base a, and the same expressions varied by putting x for a and a for x, wherever that substitution would alter the value, to which perhaps ought to be added the sine of x and the arcsine of x. All other functions of x are formed by putting some one or more of the simple functions in the place of x or a, and subjecting them to the same elementary operations. In order to carry on general reasonings on the subject of functions, we require a nomenclature enabling us to express any two numbers by names which, without specifying what particular numbers they are, shall show what function each is of the other, or in other words, shall put in evidence their mode of formation from one another. The system of general language called algebraical notation does this. The expressions a and a raised to the power 2 plus 3 times a denote the one any number, the other the number formed from it in a particular manner. The expressions a, b, n, and a plus b raised to the power n denote any three numbers, and a fourth which is formed from them in a certain mode. The following may be stated as the general problem of the algebraical calculus. Upper f being a certain function of a given number, to find what function upper f will be of any function of that number. For example, a binomial, a plus b, is a function of its two parts a and b, and the parts are, in their turn, functions of a plus b. Now, a plus b raised to the power n is a certain function of the binomial. What function will this be of A and B, the two parts? The answer to this question is the binomial theorem. The formula A plus B raised to the power 4 is equivalent to A raised to the power 4 plus 4 times A raised to the power 3 times B plus 6 times A raised to the power 2 times B raised to the power 2 plus 4 times A times B raised to the power 3 plus B raised to the power 4, which shows in what manner the number which is formed by multiplying A plus B into itself 4 times might be formed without that process directly from A, B, and N. And of this nature are all the theorems of the science of number. They assert the identity of the result of different modes of formation. They affirm that some mode of formation from X and some mode of formation from a certain function of X produce the same number. Such, as above described, is the aim and end of the calculus. As for its processes, everyone knows that they are simply deductive. In demonstrating an algebraical theorem or in resolving an equation, we travel from the datum to the quaestitum by pure ratiocination, in which the only premises introduced, besides the original hypotheses, are the fundamental axioms already mentioned, that things equal to the same thing are equal to one another, and that the sums of equal things are equal. At each step in the demonstration or in the calculation, we apply one or other of these truths, or truths deducible from them, as that the differences, products, and so on, of equal numbers are equal. It would be inconsistent with the scale of this work, and not necessary to its design, to carry the analysis of the truths and processes of algebra any further, which is also the less needful, as the task has been, to a very great extent, performed by other writers. Peacock's algebra and Dr. Whewell's Doctrine of Limits are full of instruction on the subject. The profound treatises of a truly philosophical mathematician, Professor de Morgan, should be studied by everyone who desires to comprehend the evidence of mathematical truths and the meaning of the obscurer processes of the calculus, and the speculations of Monsieur Comte in his Cours de philosophie positive on the philosophy of the higher branches of mathematics are among the many valuable gifts for which philosophy is indebted to that eminent thinker. Part 7. If the extreme generality and remoteness, not so much from sense as from the visual and tactual imagination of the laws of number, renders it a somewhat difficult effort of abstraction to conceive those laws as being in reality physical truths obtained by observation, the same difficulty does not exist with regard to the laws of extension. The facts of which those laws are expressions are of a kind peculiarly accessible to the senses and suggesting eminently distinct images to the fancy. That geometry is a strictly physical science would doubtless have been recognized in all ages, had it not been for the illusions produced by two circumstances. One of these is the characteristic property, already noticed, of the facts of geometry, that they may be collected from our ideas or mental pictures of objects as effectually as from the objects themselves. The other is the demonstrative character of geometrical truths, which was at one time supposed to constitute a radical distinction between them and physical truths, the latter as resting on merely probable evidence, being deemed essentially uncertain and unprecise. The advance of knowledge has, however, made it manifest that physical science, in its better understood branches, is quite as demonstrative as geometry. the task of deducing its details from a few comparatively simple principles is found to be anything but the impossibility it was once supposed to be. And the notion of the superior certainty of geometry is an illusion arising from the ancient prejudice which, in that science, mistakes the ideal data from which we reason for a peculiar class of realities, while the corresponding ideal data of any deductive physical science are recognized as what they really are, hypotheses. Every theorem in geometry is a law of external nature, and might have been ascertained by generalizing from observation and experiment, which in this case resolve themselves into comparison and measurement. But it was found practicable, and being practicable was desirable, to deduce these truths by ratiocination from a small number of general laws of nature, the certainty and universality of which are obvious to the most careless observer, and which compose the first principles and ultimate premises of the science. Among these general laws must be included the same two which we have noticed as ultimate principles of the science of number also, and which are applicable to every description of quantity, that is, the sums of equals are equal, and things which are equal to the same thing are equal to one another, the latter of which may be expressed in a manner more suggestive of the inexhaustible multitude of its consequences by the following terms. Whatever is equal to any one of a number of equal magnitudes is equal to any other of them. To these two must be added in geometry a third law of equality, namely, that lines, surfaces, or solid spaces which can be so applied to one another as to coincide are equal. Some writers have asserted that this law of nature is a mere verbal definition, that the expression equal magnitudes means nothing but magnitudes which can be so applied to one another as to coincide. But in this opinion I cannot agree. The equality of two geometrical magnitudes cannot differ fundamentally in its nature from the equality of two weights, 2 degrees of heat, or 2 portions of duration, to none of which would this definition of equality be suitable. None of these things can be so applied to one another as to coincide, yet we perfectly understand what we mean when we call them equal. Things are equal in magnitude, as things are equal in weight, when they are felt to be exactly similar in respect of the attribute in which we compare them. And the application of the objects to each other in the one case, like the balancing them with a pair of scales in the other, is but a mode of bringing them into a position in which our senses can recognize deficiencies of exact resemblance that would otherwise escape our notice. Along with these three general principles or axioms, the remainder of the premises of geometry consists of the so-called definitions, that is to say, propositions asserting the real existence of the various objects therein designated, together with some one property of each. In some cases, more than one property is commonly assumed, but in no case is more than one necessary. It is assumed that there are such things in nature as straight lines, and that any two of them, setting out from the same point, diverge more and more without limit. This assumption, which includes and goes beyond Euclid's axiom that two straight lines cannot enclose a space, is as indispensable in geometry and as evident, resting on as simple, familiar, and universal observation as any of the other axioms. It also assumed that straight lines diverge from one another in different degrees. In other words, that there are such things as angles, and that they are capable of being equal or unequal. It is assumed that there is such a thing as a circle, and that all its radii are equal, such things as ellipses, and that the sums of the focal distances are equal for every point in an ellipse, such things as parallel lines, and that those lines are everywhere equally distant. Footnote. Geometers have usually preferred to define parallel lines by the property of being in the same plane and never meeting. This, however, has rendered it necessary for them to assume, as an additional axiom, some other property of parallel lines, and the unsatisfactory manner in which properties for that purpose have been selected by Euclid and others has always been deemed the opprobrium of elementary geometry. Even as a verbal definition, equidistance is a fitter property to characterize parallels by, since it is the attribute really involved in the signification of the name. If to be in the same plane and never to meet were all that is meant by being parallel, we should feel no incongruity in speaking of a curve as parallel to its asymptote. The meaning of parallel lines is lines which pursue exactly the same direction and which, therefore, neither draw nearer nor go farther from one another, a conception suggested at once by the contemplation of nature. That the lines will never meet is, of course, included in the more comprehensive proposition that they are everywhere equally distant, and that any straight lines which are in the same plane and not equidistant will certainly meet, may be demonstrated in the most rigorous manner from the fundamental property of straight lines assumed in the text, that is, that if they set out from the same point, they diverge more and more without limit. End footnote. Part 8. It is a matter of more than curiosity to consider to what peculiarity of the physical truths which are the subject of geometry it is owing that they can all be deduced from so small a number of original premises. Why it is that we can set out from only one characteristic property of each kind of phenomenon, and with that and 2 or 3 general truths relating to equality, can travel from mark to mark until we obtain a vast body of derivative truths to all appearance extremely unlike those elementary ones. The explanation of this remarkable fact seems to lie in the following circumstances. In the first place, all questions of position and figure may be resolved into questions of magnitude. The position and figure of any object are determined by determining the position of a sufficient number of points in it, and the position of any point may be determined by the magnitude of 3 rectangular coordinates, that is, of the perpendiculars drawn from the point to 3 planes at right angles to one another, arbitrarily selected. By this transformation of all questions of quality into questions only of quantity, geometry is reduced to the single problem of the measurement of magnitudes, that is, the ascertainment of the equalities which exist between them. Now, when we consider that by one of the general axioms, any equality, when ascertained, is proof of as many other equalities as there are other things equal to either of the 2 equals, and that by another of those axioms, any ascertained equality is proof of the equality of as many pairs of magnitudes as can be formed by the numerous operations which resolve themselves into the addition of the equals to themselves or to other equals, we cease to wonder that in proportion as a science is conversant about equality, it should afford a more copious supply of marks, and that the sciences of number and extension, which are conversant with little else than equality, should be the most deductive of all the sciences. There are also 2 or 3 of the principal laws of space or extension which are unusually fitted for rendering one position or magnitude a mark of another, and thereby contributing to render the science largely deductive. First, the magnitudes of enclosed spaces, whether superficial or solid, are completely determined by the magnitudes of the lines and angles which bound them. Secondly, the length of any line, whether straight or curve, is measured, certain other things being given, by the angle which it subtends, and vice versa. Lastly, the angle which any two straight lines make with each other at an inaccessible point is measured by the angles they severally make with any third line we choose to select. By means of these general laws, the measurement of all lines, angles, and spaces whatsoever might be accomplished by measuring a single straight line and a sufficient number of angles, which is the plan actually pursued in the trigonometrical survey of a country, and fortunate it is that this is practicable, the exact measurement of long straight lines being always difficult and often impossible, but that of angles very easy. Three such generalizations as the foregoing afford such facilities for the indirect measurement of magnitudes, by supplying us with known lines or angles which are marks of the magnitude of unknown ones, and thereby of the spaces which they enclose, that it is easily intelligible how, from a few data, we can go on to ascertain the magnitude of an indefinite multitude of lines, angles, and spaces, which we could not easily, or could not at all, measure by any more direct process. Part 9. Such are the remarks which it seems necessary to make in this place respecting the laws of nature, which are the peculiar subject of the sciences of number and extension. The immense part which those laws take in giving a deductive character to the other departments of physical science is well known, and is not surprising when we consider that all causes operate according to mathematical laws. The effect is always dependent on, or is a function of, the quantity of the agent, and generally of its position also. We cannot, therefore, reason respecting causation without introducing considerations of quantity and extension at every step. And if the nature of the phenomena admits of our obtaining numerical data of sufficient accuracy, the laws of quantity become the grand instrument for calculating forward to an effect, or backward to a cause. That in all other sciences, as well as in geometry, questions of quality are scarcely ever independent of questions of quantity may be seen from the most familiar phenomena. Even when several colours are mixed on a painter's palette, the comparative quantity of each entirely determines the colour of the mixture. With this mere suggestion of the general causes which render mathematical principles and processes so predominant in those deductive sciences which afford precise numerical data, I must on the present occasion content myself, referring the reader who desires a more thorough acquaintance with the subject to the first 2 volumes of M. Comte's systematic work. In the same work, and more particularly in the 3rd volume, are also fully discussed the limits of the applicability of mathematical principles to the improvement of other sciences. Such principles are manifestly inapplicable where the causes on which any class of phenomena depend are so imperfectly accessible to our observation that we cannot ascertain by a proper induction their numerical laws, or where the causes are so numerous and intermixed in so complex a manner with one another that even supposing their laws known, the computation of the aggregate effect transcends the powers of the calculus as it is, or is likely to be. Or lastly, where the causes themselves are in a state of perpetual fluctuation, as in physiology, and still more, if possible, in the social science. The mathematical solutions of physical questions become progressively more difficult and imperfect in proportion as the questions divest themselves of their abstract and hypothetical character, and approach nearer to the degree of complication actually existing in nature, insomuch that beyond the limits of astronomical phenomena and of those most nearly analogous to them, mathematical accuracy is generally obtained at the expense of the reality of the inquiry, while even in astronomical questions notwithstanding the admirable simplicity of their mathematical elements, our feeble intelligence becomes incapable of following out effectually the logical combinations of the laws on which the phenomena are dependent, as soon as we attempt to take into simultaneous consideration more than 2 or 3 essential influences." End quote. Footnote: Cours de philosophie positive by Comte, Book 3, pages 414 through 416. End footnote. Of this, the problem of the three bodies has already been cited more than once as a remarkable instance, the complete solution of so comparatively simple a question having vainly tried the skill of the most profound mathematicians. We may conceive, then, how chimerical would be the hope that mathematical principles could be advantageously applied to phenomena dependent on the mutual action of the innumerable minute particles of bodies, as those of chemistry, and still more of physiology. And for similar reasons those principles remain inapplicable to the still more complex inquiries, the subjects of which are phenomena of society and government. The value of mathematical instruction as a preparation for those more difficult investigations consists in the applicability not of its doctrines but of its method. Mathematics will ever remain the most perfect type of the deductive method in general, and the applications of mathematics to the deductive branches of physics furnish the only school in which philosophers can effectually learn the most difficult and important portion of their art, the employment of the laws of simpler phenomena for explaining and predicting those of the more complex. These grounds are quite sufficient for deeming mathematical training an indispensable basis of real scientific education, and regarding, according to the dictum which an old but unauthentic tradition ascribes to Plato, one who is agiometritos as wanting in one of the most essential qualifications for the successful cultivation of the higher branches of philosophy. End of section 60. Section 61 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 25 of the Grounds of Disbelief, Parts 1 through 3. Part 1. The method of arriving at general truths or general propositions fit to be believed, and the nature of the evidence on which they are grounded, have been discussed as far as space and the writer's faculties permitted in the 24 preceding chapters. But the result of the examination of evidence is not always belief, nor even suspension of judgment. It is sometimes disbelief. The philosophy, therefore, of induction and experimental inquiry is incomplete unless the grounds not only of belief but of disbelief are treated of. And to this topic we shall devote one and the final chapter. By disbelief is not here to be understood the mere absence of belief. The ground for abstaining from belief is simply the absence or insufficiency of proof, and in considering what is sufficient evidence to support any given conclusion, we have already, by implication, considered what evidence is not sufficient for the same purpose. By disbelief is here meant not the state of mind in which we form no opinion concerning a subject, but that in which we are fully persuaded that some opinion is not true, insomuch that if evidence, even of great apparent strength, whether grounded on the testimony of others or on our own supposed perceptions, were produced in favour of the opinion, we should believe that the witnesses spoke falsely, or that they, or we ourselves, if we were the direct percipients, were mistaken. That there are such cases no one is likely to dispute. Assertions for which there is abundant positive evidence are often disbelieved on account of what is called their improbability or impossibility. And the question for consideration is what, in the present case, these words mean, and how far and in what circumstances the properties which they express are sufficient grounds for disbelief. Part 2. It is to be remarked in the first place that the positive evidence produced in support of an assertion which is nevertheless rejected on the score of impossibility or improbability is never such as amounts to full proof. It is always grounded on some approximate generalization. The fact may have been asserted by 100 witnesses, but there are many exceptions to the universality of the generalization that what 100 witnesses affirm is true. We may seem to ourselves to have actually seen the fact, but that we really see what we think we see is by no means a universal truth. Our organs may have been in a morbid state, or we may have inferred something and imagined that we perceived it. The evidence, then, in the affirmative being never more than an approximate generalization, all will depend on what the evidence in the negative is. If that also rests on an approximate generalization, it is a case for comparison of probabilities. If the approximate generalizations leading to the affirmative are, when added together, less strong, or, in other words, farther from being universal, than the approximate generalizations which support the negative side of the question, the proposition is said to be improbable and is to be disbelieved provisionally. If, however, an alleged fact be in contradiction not to any number of approximate generalizations, but to a completed generalization grounded on a rigorous induction, it is said to be impossible and is to be disbelieved totally. This last principle, simple and evident as it appears, is the doctrine which, on the occasion of an attempt to apply it to the question of the credibility of miracles, excited so violent a controversy. Hume's celebrated doctrine that nothing is credible which is contradictory to experience or at variance with the laws of nature is merely this very plain and harmless proposition that whatever is contradictory to a complete induction is incredible. That such a maxim as this should either be accounted a dangerous heresy or mistaken for a great and recondite truth speaks ill for the state of philosophical speculation on such subjects. But does not, it may be asked, the very statement of the proposition imply a contradiction? An alleged fact, according to this theory, is not to be believed if it contradict a complete induction, but it is essential to the completeness of an induction that it shall not contradict any known fact. Is it not, then, a petito principii to say that the fact ought to be disbelieved because the induction opposed to it is complete? How can we have a right to declare the induction complete, while facts, supported by credible evidence, present themselves in opposition to it? I answer, we have that right whenever the scientific canons of induction give it to us, that is, whenever the induction can be complete. We have it, for example, in a case of causation in which there has been an experimentum crucis. If an antecedent, A, superadded to a set of antecedents in all other respects unaltered, is followed by an effect, B, which did not exist before, A is, in that instance at least, the cause of B, or an indispensable part of its cause. And if A be tried again with many totally different sets of antecedents, and B still follows, then it is the whole cause. If these observations or experiments have been repeated so often and by so many persons as to exclude all supposition of error in the observer, a law of nature is established, and so long as this law is received as such, the assertion that on any particular occasion A took place, and yet B did not follow, without any counteracting cause, must be disbelieved. Such an assertion is not to be credited on any less evidence than what would suffice to overturn the law. The general truths that whatever has a beginning has a cause, and that when none but the same causes exist, the same effects follow, rest on the strongest inductive evidence possible. The proposition that things affirmed by even a crowd of respectable witnesses are true is but an approximate generalization. And even if we fancy we actually saw or felt the fact which is in contradiction to the law, what a human being can see is no more than a set of appearances, from which the real nature of the phenomenon is merely an inference, and in this inference approximate generalizations usually have a large share. If, therefore, we make our election to hold by the law, no quantity of evidence whatever ought to persuade us that there has occurred anything in contradiction to it. If indeed the evidence produced is such that it is more likely that the set of observations and experiments on which the law rests should have been inaccurately performed or incorrectly interpreted than that the evidence in question should be false, we may believe the evidence, but then we must abandon the law. And since the law was received on what seemed a complete induction, it can only be rejected on evidence equivalent, namely, as being inconsistent not with any number of approximate generalizations, but with some other and better established law of nature. This extreme case of a conflict between two supposed laws of nature has probably never actually occurred where, in the process of investigating both the laws, the true canons of scientific induction had been kept in view. But if it did occur, it must terminate in the total rejection of one of the supposed laws. It would prove that there must be a flaw in the logical process by which either one or the other was established, and if there be so, that supposed general truth is no truth at all. We cannot admit a proposition as a law of nature and yet believe a fact in real contradiction to it. We must disbelieve the alleged fact, or believe that we were mistaken in admitting the supposed law. But in order that any alleged fact should be contradictory to a law of causation, the allegation must be not simply that the cause existed without being followed by the effect, for that would be no uncommon occurrence, but that this happened in the absence of any adequate counteracting cause. Now, in the case of an alleged miracle, the assertion is the exact opposite of this. It is that the effect was defeated, not in the absence, but in consequence of a counteracting cause, namely, a direct interposition of an act of the will of some being who has power over nature, and in particular of a being whose will being assumed to have endowed all the causes with the powers by which they produce their effects, may well be supposed able to counteract them. A miracle, as was justly remarked by Brown, is no contradiction to the law of cause and effect. It is a new effect, supposed to be produced by the introduction of a new cause. Footnote. See the two remarkable notes A and F appended to his Inquiry into the Relation of Cause and Effect. End footnote. Of the adequacy of that cause, if present, there can be no doubt, and the only antecedent improbability which can be ascribed to the miracle is the improbability that any such cause existed. All, therefore, which Hume has made out, and this he must be considered to have made out, is that, at least in the imperfect state of our knowledge of natural agencies, which leaves it always possible that some of the physical antecedents may have been hidden from us, no evidence can prove a miracle to anyone who did not previously believe the existence of a being or beings with supernatural power, or who believes himself to have full proof, that the character of the being whom he recognizes is inconsistent with his having seen fit to interfere on the occasion in question. If we do not already believe in supernatural agencies, no miracle can prove to us their existence. The miracle itself, considered merely as an extraordinary fact, may be satisfactorily certified by our senses or by testimony, but nothing can ever prove that it is a miracle. There is still another possible hypothesis, that of its being the result of some unknown natural cause, and this possibility cannot be so completely shut out as to leave no alternative but that of admitting the existence and intervention of a being superior to nature. Those, however, who already believe in such a being have two hypotheses to choose from: a supernatural and an unknown natural agency, and they have to judge which of the two is the most probable in the particular case. In forming this judgment, an important element of the question will be the conformity of the result to the laws of the supposed agent, that is, to the character of the deity as they conceive it. But with the knowledge which we now possess of the general uniformity of the course of nature, religion, following in the wake of science, has been compelled to acknowledge the government of the universe as being, on the whole, carried on by general laws, and not by special interpositions. To whoever holds this belief, there is a general presumption against any supposition of divine agency not operating through general laws. Or, in other words, there is an antecedent improbability in every miracle, which, in order to outweigh it, requires an extraordinary strength of antecedent probability derived from the special circumstances of the case. Part 3. It appears from what has been said that the assertion that a cause has been defeated of an effect which is connected with it by a completely ascertained law of causation is to be disbelieved or not, according to the probability or improbability that there existed in the particular instance an adequate counteracting cause. To form an estimate of this is not more difficult than of other probabilities. With regard to all known causes capable of counteracting the given causes, we have generally some previous knowledge of the frequency or rarity of their occurrence, from which we may draw an inference as to the antecedent improbability of their having been present in any particular case. And neither in respect to known nor unknown causes are we required to pronounce on the probability of their existing in nature, but only of their having existed at the time and place at which the transaction is alleged to have happened. We are seldom, therefore, without the means, when the circumstances of the case are at all known to us, of judging how far it is likely that such a cause should have existed at that time and place without manifesting its presence by some other marks, and, in the case of an unknown cause, without having hitherto manifested its existence in any other instance. According as this circumstance or the falsity of the testimony appears more improbable, that is, conflicts with an approximate generalization of a higher order, we believe the testimony or disbelieve it, with a stronger or a weaker degree of conviction according to the preponderance, at least until we have sifted the matter further. So much, then, for the case in which the alleged fact conflicts or appears to conflict with a real law of causation. But a more common case, perhaps, is that of its conflicting with uniformities of mere coexistence, not proved to be dependent on causation. In other words, with the properties of kinds. It is with these uniformities principally that the marvellous stories related by travellers are apt to be at variance, as of men with tails or with wings, and, until confirmed by experience, of flying fish, or of ice in the celebrated anecdote of the Dutch travellers and the King of Siam. Facts of this description, facts previously unheard of, but which could not from any known law of causation be pronounced impossible, are what Hume characterizes as not contrary to experience, but merely unconformable to it. And Bentham, in his treatise on evidence, denominates them facts disconformable in specie, as distinguished from such as are disconformable in toto or in degree. In a case of this description, the fact asserted is the existence of a new kind, which in itself is not in the slightest degree incredible, and only to be rejected if the improbability that any variety of object existing at the particular place and time should not have been discovered sooner be greater than that of error or mendacity in the witnesses. Accordingly, such assertions, when made by credible persons and of unexplored places, are not disbelieved, but at most regarded as requiring confirmation from subsequent observers, unless the alleged properties of the supposed new kind are at variance with known properties of some larger kind which includes it. Or, in other words, unless in the new kind which is asserted to exist, some properties are said to have been found disjoined from others, which have always been known to accompany them, as in the case of Pliny's men, or any other kind of animal of a structure different from that which has always been found to coexist with animal life. On the mode of dealing with any such case, little needs be added to what has been said on the same topic in the 22nd chapter. Footnote: see section 57 of this work, Book 3, Chapter 22. End footnote. When the uniformities of coexistence which the alleged fact would violate are such as to raise a strong presumption of their being the result of causation, the fact which conflicts with them is to be disbelieved, at least provisionally and subject to further investigation. When the presumption amounts to a virtual certainty, as in the case of the general structure of organized beings, the only question requiring consideration is whether, in phenomena so little understood, there may not be liabilities to counteraction from causes hitherto unknown, or whether the phenomena may not be capable of originating in some other way, which would produce a different set of derivative uniformities, where, as in the case of the flying fish or the ornithorhynchus, the generalization to which the alleged fact would be an exception is very special and of limited range. Neither of the above suppositions can be deemed very improbable, and it is generally, in the case of such alleged anomalies, wise to suspend our judgment pending the subsequent inquiries which will not fail to confirm the assertion if it be true. But when the generalization is very comprehensive, embracing a vast number and variety of observations, and covering a considerable province of the domain of nature, then, for reasons which have been fully explained, such an empirical law comes near to the certainty of an ascertained law of causation, and any alleged exception to it cannot be admitted unless on the evidence of some law of causation proved by a still more complete induction. Such uniformities in the course of nature as do not bear marks of being the results of causation are, as we have already seen, admissible as universal truths with a degree of credence proportioned to their generality. Those which are true of all things whatever, or at least which are totally independent of the varieties of kinds, namely the laws of number and extension, to which we may add the law of causation itself, are probably the only ones, an exception to which is absolutely and permanently incredible. Accordingly, it is to assertions supposed to be contradictory to these laws, or to some others coming near to them in generality, that the word impossibility, at least total impossibility, seems to be generally confined. Violations of other laws of special laws of causation, for instance, are said by persons studious of accuracy in expression to be impossible in the circumstances of the case, or impossible unless some cause had existed which did not exist in the particular case. Footnote. A writer to whom I have several times referred gives as the definition of an impossibility that which there exists in the world no cause adequate to produce. This definition does not take in such impossibilities as these, that 2 and 2 should make 5, that 2 straight lines should enclose a space, or that anything should begin to exist without a cause. I can think of no definition of impossibility comprehensive enough to include all its varieties except the one which I have given, that is, an impossibility is that the truth of which would conflict with a complete induction, that is, with the most conclusive evidence which we possess of universal truth. As to the reputed impossibilities which rest on no other grounds than our ignorance of any cause capable of producing the supposed effects, very few of them are certainly impossible or permanently incredible. The facts of travelling 70 miles an hour, painless surgical operations, and conversing by instantaneous signals between London and New York held a high place, not many years ago, among such impossibilities. End footnote. Of no assertion not in contradiction to some of these very general laws will more than improbability be asserted by any cautious person, and improbability not of the highest degree, unless the time and place in which the fact is said to have occurred render it almost certain that the anomaly, if real, could not have been overlooked by other observers. Suspension of judgment is in all other cases the resource of the judicious inquirer, provided the testimony in favour of the anomaly presents, when well sifted, no suspicious circumstances. But the testimony is scarcely ever found to stand that test in cases in which the anomaly is not real. In the instances on record in which a great number of witnesses of good reputation and scientific acquirements have testified to the truth of something which has turned out untrue, there have almost always been circumstances which, to a keen observer who had taken due pains to sift the matter, would have rendered the testimony untrustworthy. There have generally been means of accounting for the impression on the senses or minds of the alleged percipients by fallacious appearances, or some epidemic delusion propagated by the contagious influence of popular feeling has been concerned in the case, or some strong interest has been implicated, religious zeal, party feeling, vanity, or at least the passion for the marvellous, in persons strongly susceptible of it. When none of these or similar circumstances exist to account for the apparent strength of the testimony, and where the assertion is not in contradiction either to those universal laws which know no counteraction or anomaly, or to the generalizations next in comprehensiveness to them, but would only amount, if admitted, to the existence of an unknown cause or an anomalous kind in circumstances not so thoroughly explored but that it is credible that things hitherto unknown may still come to light, a cautious person will neither admit nor reject the testimony, but will wait for confirmation at other times and from other unconnected sources. Such ought to have been the conduct of the King of Siam, when the Dutch travellers affirmed to him the existence of ice. But an ignorant person is as obstinate in his contemptuous incredulity as he is unreasonably credulous. Anything unlike his own narrow experience he disbelieves, if it flatters no propensity. Any nursery tale is swallowed implicitly by him, if it does. End of section 61. Section 62 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 3, Chapter 25 of The Grounds of Disbelief, Parts 4 through 6. Part 4. I shall now advert to a very serious misapprehension of the principles of the subject, which has been committed by some of the writers against Hume's essay on miracles, and by Bishop Butler before them, in their anxiety to destroy what appeared to them a formidable weapon of assault against the Christian religion, and the effect of which is entirely to confound the doctrine of the grounds of disbelief. The mistake consists in overlooking the distinction between what may be called improbability before the fact and improbability after it, or, since, as Mr. Venn remarks, the distinction of past and future is not the material circumstance, between the improbability of a mere guess being right and the improbability of an alleged fact being true. Many events are altogether improbable to us before they have happened, or before we are informed of their happening, which are not in the least incredible when we are informed of them, because not contrary to any, even approximate, induction. In the cast of a perfectly fair die, the chances are 5 to 1 against throwing ace. That is, ace will be thrown on an average only once in 6 throws. But this is no reason against believing that ace was thrown on a given occasion, if any credible witness asserts it, since though ace is only thrown once in 6 times, some number which is only thrown once in 6 times must have been thrown if the die was thrown at all. The improbability, then, or, in other words, the unusualness of any fact, is no reason for disbelieving it, if the nature of the case renders it certain that either that or something equally improbable, that is, equally unusual, did happen. Nor is this all, for even if the other 5 sides of the die were all 2s or all 3s, yet as ace would still, on the average, come up once in every 6 throws, its coming up in a given throw would be not in any way contradictory to experience. If we disbelieved all facts which had the chances against them beforehand, we should believe hardly anything at all. We are told that A.B. died yesterday. The moment before we were so told, the chances against his having died on that day may have been 10,000 to 1. But since he was certain to die at some time or other, and when he died must necessarily die on some particular day, while the preponderance of chances is very great against every day in particular, experience affords no ground for discrediting any testimony which may be produced to the events having taken place on a given day. Yet it has been considered by Dr. Campbell and others as a complete answer to Hume's doctrine that things are incredible which are contrary to the uniform course of experience, that we do not disbelieve merely because the chances were against them, things in strict conformity to the uniform course of experience, that we do not disbelieve an alleged fact merely because the combination of causes on which it depends occurs only once in a certain number of times. It is evident that whatever is shown by observation, or can be proved from laws of nature to occur in a certain proportion, however small, of the whole number of possible cases, is not contrary to experience, though we are right in disbelieving it if some other supposition respecting the matter in question involves, on the whole, a less departure from the ordinary course of events. Yet on such grounds as this have able writers been led to the extraordinary conclusion that nothing supported by credible testimony ought ever to be disbelieved. Part 5. We have considered 2 species of events commonly said to be improbable. One kind which are in no way extraordinary, but which, having an immense preponderance of chances against them, are improbable until they are affirmed, but no longer another kind which, being contrary to some recognized law of nature, are incredible on any amount of testimony except such as would be sufficient to shake our belief in the law itself. But between these two classes of events there is an intermediate class consisting of what are commonly termed coincidences. In other words, those combinations of chances which present some peculiar and unexpected regularity, assimilating them in so far to the results of law. As if, for example, in a lottery of 1,000 tickets, the numbers should be drawn in the exact order of what are called the natural numbers, 1, 2, 3, and so on. We have still to consider the principles of evidence applicable to this case, whether there is any difference between coincidences and ordinary events in the amount of testimony or other evidence necessary to render them credible. It is certain that on every rational principle of expectation, a combination of this peculiar sort may be expected quite as often as any other given series of 1,000 numbers, that with perfectly fair dice, sixes will be thrown twice, thrice, or any number of times in succession, quite as often in 1,000 or 1,000,000 throws as any other succession of numbers fixed upon beforehand, and that no judicious player would give greater odds against the one series than against the other. Notwithstanding this, there is a general disposition to regard the one as much more improbable than the other, and as requiring much stronger evidence to make it credible. Such is the force of this impression that it has led some thinkers to the conclusion that nature has greater difficulty in producing regular combinations than irregular ones. Or in other words, that there is some general tendency of things, some law, which prevents regular combinations from occurring, or at least from occurring so often as others. Among these thinkers may be numbered D'Alembert, who, in an essay on probabilities to be found in the 5th volume of his Mélanges, contends that regular combinations, though equally probable according to the mathematical theory with any others, are physically less probable. He appeals to common sense, or, in other words, to common impressions, saying, if dice thrown repeatedly in our presence gave sixes every time, should we not, before the number of throws had reached 10, not to speak of thousands of millions, be ready to affirm with the most positive conviction that the dice were false? The common and natural impression is in favour of D'Alembert. The regular series would be thought much more unlikely than an irregular. But this common impression is, I apprehend, merely grounded on the fact that scarcely anybody remembers to have ever seen one of these peculiar coincidences, the reason of which is simply that no one's experience extends to anything like the number of trials within which that or any other given combination of events can be expected to happen. The chance of sixes on a single throw of 2 dice being 1 in 36, the chance of sixes 10 times in succession is 1 divided by the 10th power of 36. In other words, such a concurrence is only likely to happen once in 3,656 million trials, a number which no dice player's experience comes up to a millionth part of it. But if, instead of sixes 10 times, any other given succession of 10 throws had been fixed upon, it would have been exactly as unlikely that in any individual's experience that particular succession had ever occurred, although this does not seem equally improbable, because no one would be likely to have remembered whether it had occurred or not, and because the comparison is tacitly made, not between sixes 10 times and any one particular series of throws, but between all regular and all irregular successions taken together. That, as D'Alembert says, if the succession of sixes was actually thrown before our eyes, we should ascribe it not to chance, but to unfairness in the dice is unquestionably true. But this arises from a totally different principle. We should then be considering not the probability of the fact in itself, but the comparative probability with which, when it is known to have happened, it may be referred to one or to another cause. The regular series is not at all less likely than the irregular one to be brought about by chance, but it is much more likely than the irregular one to be produced by design, or by some general cause operating through the structure of the dice. It is the nature of casual combinations to produce a repetition of the same event as often and no oftener than any other series of events. But it is the nature of general causes to reproduce in the same circumstances always the same event. Common sense and science alike dictate that, all other things being the same, we should rather attribute the effect to a cause which, if real, would be very likely to produce it, than to a cause which would be very unlikely to produce it. According to Laplace's sixth theorem, which we demonstrated in a former chapter, the difference of probability arising from the superior efficacy of the constant cause, unfairness in the dice, would, after a very few throws, far outweigh any antecedent probability which there could be against its existence. D'Alembert should have put the question in another manner. He should have supposed that we had ourselves previously tried the dice, and knew by ample experience that they were fair. Another person then tries them in our absence, and assures us that he threw sixes 10 times in succession. Is the assertion credible or not? Here the effect to be accounted for is not the occurrence itself, but the fact of the witnesses asserting it. This may arise either from its having really happened, or from some other cause. What we have to estimate is the comparative probability of these two suppositions. If the witness affirmed that he had thrown any other series of numbers, supposing him to be a person of veracity and tolerable accuracy, and to profess that he took particular notice, we should believe him. But the 10 sixes are exactly as likely to have been really thrown as the other series. If, therefore, this assertion is less credible than the other, the reason must be, not that it is less likely than the other to be made truly, but that it is more likely than the other to be made falsely. One reason obviously presents itself why what is called a coincidence should be oftener asserted falsely than an ordinary combination. It excites wonder. It gratifies the love of the marvelous. The motives, therefore, to falsehood, one of the most frequent of which is the desire to astonish, operate more strongly in favor of this kind of assertion than of the other kind. Thus far, there is evidently more reason for discrediting an alleged coincidence than a statement in itself not more probable, but which, if made, would not be thought remarkable. There are cases, however, in which the presumption on this ground would be the other way. There are some witnesses who, the more extraordinary an occurrence might appear, would be the more anxious to verify it by the utmost carefulness of observation before they would venture to believe it, and still more before they would assert it to others. Part 6. Independently, however, of any peculiar chances of mendacity arising from the nature of the assertion, Laplace contends that, merely on the general ground of the fallibility of testimony, a coincidence is not credible on the same amount of testimony on which we should be warranted in believing an ordinary combination of events. In order to do justice to his argument, it is necessary to illustrate it by the example chosen by himself. If, says Laplace, there were 1,000 tickets in a box, and only one has been drawn out, then, if an eyewitness affirms that the number drawn was 79, this, though the chances were 999 in 1,000 against it, is not on that account the less credible. Its credibility is equal to the antecedent probability of the witness's veracity. But if there were in the box 999 black balls and only one white, and the witness affirms that the white ball was drawn, the case, according to Laplace, is very different. The credibility of his assertion is but a small fraction of what it was in the former case, the reason of the difference being as follows. The witness of whom we are speaking must, from the nature of the case, be of a kind whose credibility falls materially short of certainty. Let us suppose, then, the credibility of the witness in the case in question to be 9 out of 10. That is, let us suppose that in every 10 statements which the witness makes, 9, on an average, are correct, and 1 incorrect. Let us now suppose that there have taken place a sufficient number of drawings to exhaust all the possible combinations, the witness deposing in every one. In one case out of every 10 in all these drawings, he will actually have made a false announcement. But in the case of the 1,000 tickets, these false announcements will have been distributed impartially over all the numbers, and of the 999 cases in which number 79 was not drawn, there will have been only one case in which it was announced. On the contrary, in the case of the 1,000 balls, the announcement being always black or white, if white was not drawn and there was a false announcement, that false announcement must have been white. And since by the supposition that there was a false announcement once in every 10 times, white will have been announced falsely in 1/10th part of all the cases in which it was not drawn, that is, in 1/10th part of 999 cases out of every 1,000. White, then, is drawn on average exactly as often as number 79, but it is announced without having been really drawn 999 times as often as number 79. The announcement, therefore, requires a much greater amount of testimony to render it credible. Footnote. Not, however, as might at first sight appear, 990 times as much. A complete analysis of the cases shows that, always assuming the veracity of the witness to be 9/10ths, in 10,000 drawings, the drawing of number 79 will occur 9 times and be announced incorrectly once. The credibility, therefore, of the announcement of number 79 is 9/10ths, while the drawing of a white ball will occur 9 times and be announced incorrectly 999 times. The credibility, therefore, of the announcement of white is 9 divided by 1008, and the ratio of the two 10,008 to 10, the one announcement being thus only about 100 times more credible than the other, instead of 999 times. End footnote. To make this argument valid, it must of course be supposed that the announcements made by the witness are average specimens of his general veracity and accuracy, or at least that they are neither more nor less so in the case of the black and white balls than in the case of the 1,000 tickets. This assumption, however, is not warranted. A person is far less likely to mistake who has only one form of error to guard against than if he had 999 different errors to avoid. For instance, in the example chosen, a messenger who might make a mistake once in 10 times in reporting the number drawn in a lottery might not err once in 1,000 times, if sent simply to observe whether a ball was black or white. Laplace's argument, therefore, is faulty, even as applied to his own case. Still less can that case be received as completely representing all cases of coincidence. Laplace has so contrived his example that though black answers to 999 distinct possibilities, and white only to one, the witness has nevertheless no bias which can make him prefer black to white. The witness did not know that there were 999 black balls in the box and only one white. Or if he did, Laplace has taken care to make all the 999 cases so undistinguishably alike that there is hardly a possibility of any cause of falsehood or error operating in favour of any of them, which would not operate in the same manner if there were only one. Alter this supposition and the whole argument falls to the ground. Let the balls, for instance, be numbered, and let the white ball be number 79. Considered in respect of their colour, there are but two things which the witness can be interested in asserting, or can have dreamed or hallucinated, or has to choose from if he answers at random, that is, black and white. But considered in respect of the numbers attached to them, there are 1,000, and if his interest or error happens to be connected with the numbers, though the only assertion he makes is about the colour, the case becomes precisely assimilated to that of the 1,000 tickets. Or instead of the balls, suppose a lottery with 1,000 tickets and but one prize, and that I hold number 79, and being interested only in that, ask the witness not what was the number drawn, but whether it was 79 or some other. There are now only two cases, as in Laplace's example. Yet he surely would not say that if the witness answered 79, the assertion would be in an enormous proportion less credible than if he made the same answer to the same question asked in the other way. If, for instance, to put a case supposed by Laplace himself, he has staked a large sum on one of the chances and thinks that by announcing its occurrence he shall increase his credit, he is equally likely to have betted on any one of the 999 numbers which are attached to black balls, and so far as the chances of mendacity from this cause are concerned, there will be 999 times as many chances of his announcing black falsely as white. Or, suppose a regiment of 1,000 men, 999 Englishmen and 1 Frenchman, and that of these one man has been killed, and it is not known which. I ask the question, and the witness answers, the Frenchman. This was not only as improbable a priori, but is in itself as singular a circumstance, as remarkable a coincidence as the drawing of the white ball. Yet we should believe the statement as readily as if the answer had been John Thompson, because, though the 999 Englishmen were all alike in the point in which they differed from the Frenchmen, they were not, like the 990 black balls, undistinguishable in every other respect, but being all different, they admitted as many chances of interest or error as if each man had been of a different nation, and if a lie was told or a mistake made, the misstatement was as likely to fall on any Jones or Thompson of the set as on the Frenchman. The example of a coincidence selected by D'Alembert, that of sixes thrown on a pair of dice 10 times in succession, belongs to this sort of cases rather than to such as Laplace's. The coincidence is here far more remarkable, because of far rarer occurrence than the drawing of the white ball. But though the improbability of its really occurring is greater, the superior probability of its being announced falsely cannot be established with the same evidence. The announcement, black, represented 999 cases, but the witness may not have known this, and if he did, the 999 cases are so exactly alike that there is really only one set of possible causes of mendacity corresponding to the whole. The announcement, sixes not drawn 10 times, represents and is known by the witness to represent a great multitude of contingencies, every one of which being unlike every other, there may be a different and a fresh set of causes of mendacity corresponding to each. It appears to me, therefore, that Laplace's doctrine is not strictly true of any coincidences, and is wholly inapplicable to most, and that to know whether a coincidence does or does not require more evidence to render it credible than an ordinary event, we must refer in every instance to first principles, and estimate afresh what is the probability that the given testimony would have been delivered in that instance, supposing the fact which it asserts not to be true. With these remarks we close the discussion of the grounds of disbelief, and along with it such exposition as space admits, and as the writer has it in his power to furnish, of the logic of induction. End of section 62. Section 63 of A System of Logic by John Stuart Mill. This LibriVox recording is in the public domain. Book 4 of Operations Subsidiary to Induction. Chapter 1 of Observation and Description. Quote, "Clear and distinct ideas are terms which, though familiar and frequent in men's mouths, I have reason to think every one who uses does not perfectly understand. And possibly it is but here and there one who gives himself the trouble to consider them so far as to know what he himself or others precisely mean by them. I have, therefore, in most places, chose to put determinate or determined instead of clear and distinct, as more likely to direct men's thoughts to my meaning in this matter." End quote. Locke's Essay on the Human Understanding, Epistle to the Reader. Quote, "Il ne peut y avoir qu'une méthode parfaite, qui est la méthode naturelle. On nomme ainsi un arrangement dans lequel les êtres du même genre seraient plus voisins entre eux que ceux de tous les autres genres. Les genres du même ordre, plus que ceux de tous les autres ordres, et ainsi de suite. Cette méthode est l'idéal auquel l'histoire naturelle doit tendre, car il est évident que si l'on y parvenait, on aurait l'expression exacte et complète de la nature entière." End quote. Cuvier, Règne animal, Introduction. Quote, "Deux grandes notions philosophiques dominaient la théorie fondamentale de la méthode naturelle proprement dite, savoir la formation des groupes naturels, et ensuite leur succession hiérarchique." Comte, Cours de philosophie positive, 42e leçon. Part 1. The inquiry which occupied us in the two preceding books has conducted us to what appears a satisfactory solution of the principal problem of logic, according to the conception I have formed of the science. We have found that the mental process with which logic is conversant, the operation of ascertaining truths by means of evidence, is always, even when appearances point to a different theory of it, a process of induction. And we have particularized the various modes of induction and obtained a clear view of the principles to which it must conform in order to lead to results which can be relied on. The consideration of induction, however, does not end with the direct rules for its performance. Something must be said of those other operations of the mind which are either necessarily presupposed in all induction, or are instrumental to the more difficult and complicated inductive processes. The present book will be devoted to the consideration of these subsidiary operations, among which our attention must first be given to those which are indispensable preliminaries to all induction whatsoever. Induction being merely the extension to a class of cases of something which has been observed to be true in certain individual instances of the class, the first place among the operations subsidiary to induction is claimed by observation. This is not, however, the place to lay down rules for making good observers, nor is it within the competence of logic to do so, but of the art of intellectual education. Our business with observation is only in its connection with the appropriate problem of logic, the estimation of evidence. We have to consider not how or what to observe, but under what conditions observation is to be relied on, what is needful in order that the fact supposed to be observed may safely be received as true. Part 2. The answer to this question is very simple, at least in its first aspect. The sole condition is that what is supposed to have been observed shall really have been observed, that it be an observation, not an inference. For in almost every act of our perceiving faculties, observation and inference are intimately blended. What we are said to observe is usually a compound result, of which 1/10 may be observation and the remaining 9/10 inference. I affirm, for example, that I hear a man's voice. This would pass in common language for a direct perception. All, however, which is really perception is that I hear a sound, that the sound is a voice, and that voice, the voice of a man, are not perceptions but inferences. I affirm, again, that I saw my brother at a certain hour this morning. If any proposition concerning a matter of fact would commonly be said to be known by the direct testimony of the senses, this surely would be so. The truth, however, is far otherwise. I only saw a certain coloured surface, or rather, I had the kind of visual sensations which are usually produced by a coloured surface, and from these as marks, known to be such by previous experience, I concluded that I saw my brother. I might have had sensations precisely similar when my brother was not there. I might have seen some other person so nearly resembling him in appearance as, at the distance and with the degree of attention which I bestowed, to be mistaken for him. I might have been asleep and have dreamed that I saw him, or in a state of nervous disorder which brought his image before me in a waking hallucination. In all these modes, many have been led to believe that they saw persons well known to them who were dead, or far distant. If any of these suppositions had been true, the affirmation that I saw my brother would have been erroneous, but whatever was matter of direct perception, namely the visual sensations, would have been real. The inference only would have been ill-grounded. I should have ascribed those sensations to a wrong cause. Innumerable instances might be given and analysed in the same manner of what are vulgarly called errors of sense. There are none of them properly errors of sense. They are erroneous inferences from sense. When I look at a candle through a multiplying glass, I see what seems a dozen candles instead of one, and if the real circumstances of the case were skilfully disguised, I might suppose that there were really that number. There would be what is called an optical deception. In the kaleidoscope there really is that deception. When I look through the instrument, instead of what is actually there, namely a casual arrangement of coloured fragments, the appearance presented is that of the same combination several times repeated in symmetrical arrangement round a point. The delusion is, of course, effected by giving me the same sensations which I should have had if such a symmetrical combination had really been presented to me. If I cross two of my fingers and bring any small object, a marble for instance, into contact with both, at points not usually touched simultaneously by one object, I can hardly, if my eyes are shut, help believing that there are two marbles instead of one. But it is not my touch in this case, nor my sight in the other, which is deceived. The deception, whether durable or only momentary, is in my judgment. From my senses I have only the sensations, and those are genuine. Being accustomed to have those or similar sensations when, and only when, a certain arrangement of outward objects is present to my organs, I have the habit of instantly, when I experience the sensations, inferring the existence of that state of outward things. This habit has become so powerful that the inference performed with the speed and certainty of an instinct is confounded with intuitive perceptions. When it is correct, I am unconscious that it ever needed proof. Even when I know it to be incorrect, I cannot, without considerable effort, abstain from making it. In order to be aware that it is not made by instinct, but by an acquired habit, I am obliged to reflect on the slow process through which I learned to judge by the eye of many things which I now appear to perceive directly by sight, and on the reverse operation performed by persons learning to draw, who with difficulty and labour divest themselves of their acquired perceptions, and learn afresh to see things as they appear to the eye. It would be easy to prolong these illustrations were there any need to expatiate on a topic so copiously exemplified in various popular works. From the examples already given, it is seen sufficiently that the individual facts from which we collect our inductive generalizations are scarcely ever obtained by observation alone. Observation extends only to the sensations by which we recognize objects, but the propositions which we make use of, either in science or in common life, relate mostly to the objects themselves. In every act of what is called observation, there is at least one inference, from the sensations to the presence of the object, from the marks or diagnostics to the entire phenomenon, and hence, among other consequences, follows the seeming paradox, that a general proposition collected from particulars is often more certainly true than any one of the particular propositions from which, by an act of induction, it was inferred. For each of those particular, or rather singular, propositions involved an inference from the impression on the senses to the fact which caused that impression, and this inference may have been erroneous in any one of the instances, but cannot well have been erroneous in all of them, provided their number was sufficient to eliminate chance. The conclusion, therefore, that is, the general proposition, may deserve more complete reliance than it would be safe to repose in any one of the inductive premises. The logic of observation, then, consists solely in a correct discrimination between that in a result of observation which has really been perceived, and that which is an inference from the perception. Whatever portion is inference is amenable to the rules of induction already treated of, and requires no further notice here. The question for us in this place is, when all which is inference is taken away, what remains? There remains in the first place the mind's own feelings or states of consciousness, namely its outward feelings or sensations and its inward feelings, its thoughts, emotions, and volitions. Whether anything else remains, or all else is inference from this, whether the mind is capable of directly perceiving or apprehending anything except states of its own consciousness, is a problem of metaphysics not to be discussed in this place. But after excluding all questions on which metaphysicians differ, it remains true that for most purposes the discrimination we are called upon practically to exercise is that between sensations or other feelings, of our own or of other people, and inferences drawn from them. And on the theory of observation, this is all which seems necessary to be said for the purposes of the present work. Part 3. If, in the simplest observation, or in what passes for such, there is a large part which is not observation but something else, so, in the simplest description of an observation, there is and must always be much more asserted than is contained in the perception itself. We cannot describe a fact without implying more than the fact. The perception is only of one individual thing, but to describe it is to affirm a connection between it and every other thing, which is either denoted or connoted by any of the terms used. To begin with an example, than which none can be conceived more elementary, I have a sensation of sight, and I endeavour to describe it by saying that I see something white. In saying this, I do not solely affirm my sensation, I also class it. I assert a resemblance between the thing I see and all things which I and others are accustomed to call white. I assert that it resembles them in the circumstance in which they all resemble one another, in that which is the ground of their being called by the name. This is not merely one way of describing an observation, but the only way. If I would either register my observation for my own future use, or make it known for the benefit of others, I must assert a resemblance between the fact which I have observed and something else. It is inherent in a description to be the statement of a resemblance or resemblances. We thus see that it is impossible to express in words any result of observation without performing an act possessing what Dr. Whewell considers to be characteristic of induction. There is always something introduced which was not included in the observation itself, some conception common to the phenomenon with other phenomena to which it is compared. An observation cannot be spoken of in language at all without declaring more than that one observation, without assimilating it to other phenomena already observed and classified. But this identification of an object, this recognition of it as possessing certain known characteristics, has never been confounded with induction. It is an operation which precedes all induction and supplies it with its materials. It is a perception of resemblances obtained by comparison. These resemblances are not always apprehended directly by merely comparing the object observed with some other present object, or with our recollection of an object which is absent. They are often ascertained through intermediate marks, that is, deductively. In describing some new kind of animal, suppose me to say that it measures 10 feet in length, from the forehead to the extremity of the tail. I did not ascertain this by the unassisted eye. I had a 2-foot rule which I applied to the object, and, as we commonly say, measured it, an operation which was not wholly manual, but partly also mathematical, involving the two propositions 5 times 2 is 10, and things which are equal to the same thing are equal to one another. Hence, the fact that the animal is 10 feet long is not an immediate perception, but a conclusion from reasoning, the minor premises alone being furnished by observation of the object. Nevertheless, this is called an observation, or a description of the animal, not an induction respecting it. To pass at once from a very simple to a very complex example, I affirm that the earth is globular. The assertion is not grounded on direct perception, for the figure of the earth cannot by us be directly perceived, though the assertion would not be true unless circumstances could be supposed under which its truth could be so perceived. That the form of the earth is globular is inferred from certain marks, as for instance from this, that its shadow thrown upon the moon is circular, or this, that on the sea or any extensive plain our horizon is always a circle, either of which marks is incompatible with any other than a globular form. I assert further that the earth is that particular kind of a globe which is termed an oblate spheroid, because it is found by measurement in the direction of the meridian, that the length on the surface of the earth which subtends a given angle at its centre diminishes as we recede from the equator and approach the poles. But these propositions that the Earth is globular and that it is an oblate spheroid assert each of them an individual fact in its own nature capable of being perceived by the senses when the requisite organs and the necessary position are supposed, and not only actually perceived because those organs and that position are wanting. This identification of the Earth, first as a globe, and next as an oblate spheroid, which, if the fact could have been seen, would have been called a description of the figure of the Earth, may without impropriety be so called when, instead of being seen, it is inferred. But we could not without impropriety call either of these assertions an induction from facts respecting the Earth. They are not general propositions collected from particular facts, but particular facts deduced from general propositions. They are conclusions obtained deductively from premises originating in induction. But of these premises some were not obtained by observation of the Earth, nor had any peculiar reference to it. If, then, the truth respecting the figure of the Earth is not an induction, why should the truth respecting the figure of the Earth's orbit be so? The two cases only differ in this, that the form of the orbit was not, like the form of the Earth itself, deduced by ratiocination from facts which were marks of ellipticity, but was got at by boldly guessing that the path was an ellipse, and finding afterward, on examination, that the observations were in harmony with the hypothesis. According to Dr. Whewell, however, this process of guessing and verifying our guesses is not only induction, but the whole of induction. No other exposition can be given of that logical operation. That he is wrong in the latter assertion, the whole of the preceding book has, I hope, sufficiently proved, and that the process by which the ellipticity of the planetary orbits was ascertained is not induction at all, was attempted to be shown in the second chapter of the same book. Footnote: see section 29 of this work, Book 3, Chapter 2, Part 3, and section 30 of this work, Book 3, Chapter 2, Parts 4 and 5. End footnote. We are now, however, prepared to go more into the heart of the matter than at that earlier period of our inquiry, and to show not merely what the operation in question is not, but what it is. Part 4. We observed in the second chapter that the proposition, the Earth moves in an ellipse, so far as it only serves for the colligation or connecting together of actual observations, that is, as it only affirms that the observed positions of the Earth may be correctly represented by as many points in the circumference of an imaginary ellipse, is not an induction but a description. It is an induction only when it affirms that the intermediate positions, of which there has been no direct observation, would be found to correspond to the remaining points of the same elliptic circumference. Now, though this real induction is one thing and the description another, we are in a very different condition for making the induction before we have obtained the description and after it. For inasmuch as the description, like all other descriptions, contains the assertion of a resemblance between the phenomenon described and something else, in pointing out something which the series of observed places of a planet resembles, it points out something in which the several places themselves agree. If the series of places correspond to as many points of an ellipse, the places themselves agree in being situated in that ellipse. We have therefore, by the same process which gave us the description, obtained the requisites for an induction by the method of agreement. The successive observed places of the Earth being considered as effects, and its motion as the cause which produces them, we find that those effects, that is, those places, agree in the circumstance of being in an ellipse. We conclude that the remaining effects, the places which have not been observed, agree in the same circumstance, and that the law of the motion of the earth is motion in an ellipse. The colligation of facts, therefore, by means of hypotheses, or, as Dr. Whewell prefers to say, by means of conceptions, instead of being, as he supposes, induction itself, takes its proper place among operations subsidiary to induction. All induction supposes that we have previously compared the requisite number of individual instances and ascertained in what circumstances they agree. The colligation of facts is no other than this preliminary operation. When Kepler, after vainly endeavouring to connect the observed places of a planet by various hypotheses of circular motion, at last tried the hypothesis of an ellipse and found it answer to the phenomena, what he really attempted, first unsuccessfully and at last successfully, was to discover the circumstance in which all the observed positions of the planet agreed, and when he in like manner connected another set of observed facts, the periodic times of the different planets, by the proposition that the squares of the times are proportional to the cubes of the distances, what he did was simply to ascertain the property in which the periodic times of all the different planets agreed. Since, therefore, all that is true and to the purpose in Dr. Whewell's doctrine of conceptions might be fully expressed by the more familiar term hypothesis, and since his colligation of facts by means of appropriate conceptions is but the ordinary process of finding by a comparison of phenomena in what consists their agreement or resemblance, I would willingly have confined myself to those better understood expressions, and persevered to the end in the same abstinence which I have hitherto observed from ideological discussions, considering the mechanism of our thoughts to be a topic distinct from and irrelevant to the principles and rules by which the trustworthiness of the results of thinking is to be estimated. Since, however, a work of such high pretensions, and, it must also be said, of so much real merit, has rested the whole theory of induction upon such ideological considerations, it seems necessary for others who follow to claim for themselves and their doctrines whatever position may properly belong to them on the same metaphysical ground. And this is the object of the succeeding chapter. End of section 63.